All right, then I believe we're live. Thank you everyone for joining this year's edition of the ML Family Workshop. I'm very thrilled to see so many people joining in spite of the pandemic, a remote conference, and Zoom calls fatigue. So thanks everyone for joining and being in the audience. We have many exciting talks today, and Martin is the session chair, so I'll leave it up to him.
Thank you very much. And for this first talk, Daniel Hillerström will be giving a presentation on composing Unix with effect handlers. Welcome, Daniel.
Yeah, thank you. Oh, it's you always, yeah, it should be recorded already. To tune into my talk on composing Unix with effect handlers, a case study in what I like to call effect handler-oriented programming. And the objective of this talk is really to demonstrate or convince you that effect handlers are worthwhile programming abstraction. And the way I intend to do that is by way of an example. I'll take Ritchie and Thompson's Unix operating system and show you how you can build that using effect handlers. In particular, I'm going to show how you can actually think about Unix in terms of standard effects such as exceptions, dynamic binding, non-determinism, and state. In this particular talk, we will not get further than the time sharing non-determinism. Moreover, I'm going to add a few self-imposed constraints, and that's actually just to drive home the point that effect handlers are a really powerful and flexible mechanism. So the first thing I'm going to impose is that everything I do in this talk has to be definable in the language. I'm not going to use any primitive effects such as printing to a console and etc. The second one is that any interface I define in this talk, I can never change. I sort of have to live with my legacy code. Let's dive right in with some code here. We'll begin by implementing some basic I/O, or maybe you can't call this I/O because we're only going to do the O part, the output. We're only going to handle writes here, but it'll get the point across. And just before I get too deep into it, I should mention that the language that I'm using here is the programming language Lynx. Now, the basic tenet of programming with effect handlers is that the doing is separate from the being, or in other words, that the syntax is separate from the semantics. And what that concretely means, I'll illustrate here by implementing the echo utility, which takes a string and prints that to standard out. I'll implement it using an effectful operation called write. So we'll see here how to do a write and what it means to be a write. So we have echo here, which is a function that takes a string, and it ultimately returns a unit. In doing so, it may perform the effects in this signature. In this particular effect signature, there's one operation present, and that's write, which is parameterized by the file descriptor we wish to write to, and the string contents we will write to that file descriptor. The operation itself returns unit. So now we can implement echo by doing or performing the write operation here. So in Lynx, you do it this way. You type do write. That's the invocation form for operations. And then we need to give it some payload. We have no1 file descriptor, standard out. And then we can supply the string contents that we've been given as input. This is an abstract computation. If you try to run echo now, the program will stop. There's no semantics associated with write yet, so we need to give that, and the semantics of an operation is conferred by its handler. So let's implement the handler down here that I call basic I/O. So it takes one of these computations that can do writes. The computation can return anything. Then ultimately the handler is going to return whatever that computation returned along with the current state of the file. So let's look at the definition of how we can implement this. Given a computation as input, in Lynx, the way you handle a computation is you wrap it in a handle, we apply the computation. Now there are two things to consider. We need to consider the return value of m and any invocations of write within m. Let's begin with the return value. So if we get an answer back, then what we need to return on the right hand side here is the answer along with the file, the current state of the file. At this point we don't have any file, so we need to build it up first. So what we can do to satisfy the type checker is to give it the empty string. So the file is empty at this point. Then let's consider what happens when a write occurs. we can ignore the file descriptor for now, since there's only one. We get the contents, here's to write, and in addition, we also get access to the continuation of write within M. And it's worth to remark here that the type of resume is a function that takes a unit and then returns whatever the handler returns, namely a pair consisting of the return value and a file. So you'll note here that this unit here matches exactly the expectation of write, which is supposed to return a unit. So the input to resume is going to be the output of the operation write within an M. The reason resume returns this pair here is because it's what's known in literature as a deep handler. That means the resumption or the continuation resume here implicitly wraps the handler around it when I invoke it. So what we can do now is we can actually invoke resume, and then we'll get the answer plus the current state of the file back. So let's try to do that. So if we get the answer plus file, resume like this, then what we need to do is we need to return that answer along with the next state, or the updated state of the file. So we can build the file up like this with string concatenation. So we sort of append the given string onto the file. So basically what I'm doing here is I'm using the implicit state given by the runtime to me, namely the call stack, to manage the state of the file. You can see this is sort of a silly buffered writing or something like that. Right, so I have an example to illustrate this in action here, the example 0. In this example, I install the basic IO handler, and then the computation that I run under it is echo hello, echo world. And now if you try to load this up in a links prompt, I have right here, load the file, I do example 0, and what we see here is we get the return value is unit from the computation, and then the state of the file is the two echoes concatenated, so hello world. Right. So that's rather basic. Another sort of basic thing is premature process termination, which we can model using exceptions. So in Unix, you'll have this exit system call, which takes an exit code and then terminates the process with that exit code. So the way we can model this is as a function that performs an exit operation that's parameterized by the exit code, and then it will return something of the empty type. So this is, of course, impossible, so that means the operation will never return, so we can think of it intuitively as an exception. The exit function itself will return something of polymorphic type, which is completely safe because exit will never return. The way you do that concretely in Links is you invoke the exit operation in an empty pattern matching expression. So switch here is your pattern matching construct in Links. So your camel programmer is, this is your match with, or Haskell, your case off. Now we then need to say what it means to perform an exit. So we have status here, another handler that takes one of these exit invoking computations, and then ultimately returns an integer, so indicating whether or not it's terminated with success, the given computation. Right, so we give the computation, we do as before, we handle it by invoking, by applying it. If it returns successfully, we just return the integer 0 to indicate success, like in Unix. If exit occurs, then we get access to the payload, the exit code. We also get access to the resumption or the continuation, which in this instance is completely useless because it expects as input something of the empty type. So we can actually never invoke this one, right? So we can elide this altogether. Right, so what we can basically do here is we can just return the exit code. So this has the effect of short-circuiting the remainder of the computation within M. Let's see here, I have an example to illustrate this. Example 1, so what we do here is we install first the basic IO handler, underneath that the status handler. And then the computation that we run is echo the det string exit with 1, and then we echo the string code. The point here is that we should never see code being written to the file. And indeed here, if we type example 1, we see here we get the process terminated with exit code 1, and the current state of the file is the string det. So indeed, we never see code. Right, moving on to something maybe slightly more interesting. In an operating system, you typically have multi-user support. At least you have that in Unix. And each user has their own environment. And each environment provides some user-specific variables. So we can model this using dynamic binding. And in my particular system here, I'm going to assume there are 3 users, Alice, Bob, and Root. And I'm going to assume there's only one environment variable, and that's the user environment variable, which contains a string representation of the inquiring user. So what I'm basically going to show here is how we can implement the reader monad or environment monad using effect handlers. So we will have we'll implement the utility whoami. And what it's going to do is simply going to invoke an operation called ask, which asks for the string representation of the current user. And the implementation here is incredibly simple. It's just going to invoke the operation, and that's all. So it's up to the ambient environment to now give a meaning to this ask operation. And let's look at how we can implement the environment. So here is the signature of the environment. It's parameterized by a user, that is the current user running, and it takes as a second parameter a computation that can perform these ask operations. The way we then implement the ask or interpret ask is that whenever ask occurs within M, we get access to the continuation, and then we simply just switch a pattern match on the user, the input that was provided to us, the user that we're running under, and then we return the string representation of that user by invoking the resumption with that string. So it's all quite simple actually, and I have an example here to illustrate it just briefly. So we install the environment handler, run with root as the user, and then we invoke the whoami utility, and you will see here example 2. If everything works, it should return the string root, and indeed it does. Right, so that gives us a separate environments, but we still have no way of sort of switching between the users, and you can do that in a multi-user system usually as Unix. And the way you do that in Unix is you use a substitute user system call, or SU, and we can model that using an operation that I call SU here, and it's parameterized by the user that we want to impersonate. So the implementation of SU here is of the function SU is simple. We just invoke the operation with the payload user. Then here's the handler for it, which is called session manager. So just as before, it's parameterized by a user. However, this is not. The idea here is that this is the initial user of the system, so the one that's we start as, and not necessarily the user running the current computation. Then it will take a computation that can now perform 2 operations: the ask operation and the substitute user operation. And the way we implement it is that we first install the initial environment, which runs the initial environment for the initial user, and then under that environment we run a computation that handles SU operations. So that's what you see defined here, and in particular this case here handles the SU operation. So the SU gives us access to the user prime, which is the user we want to impersonate, and the continuation of that operation. And the way we interpret this operation is as follows. We install another instance of the environment handler, this bit here. However, the crucial difference here is that it is parameterized by user prime and not the initial user we were given up here. And then the computation that we run under there is the continuation, resume here applied to unit. So this has the effect of overloading or shattering any residual invocations of ask within resume. So that means an invocation of ask inside resume will now get the string representation of user prime rather than user. Right, so I have an example to show this in action. Example 3. So we installed basic IO handler. Then we installed the session manager handler running as the initial user root. Under there we install the status handler. And then the computation we do is we first su as Alice, then we echo who am I, followed by echo space. And then we do the same for Bob and similar for root. And let's see here what happens. So now we have one process has finished and finished with execute 0. And then here we get the contents of the file. And we see here it has Alice, Bob, and root exactly in the order here that we invoked them. So we are seeing now we can switch. We have multiple users and we can switch between them. One thing that's still missing is multitasking facility, or the ability to run multiple things at once. And we can use non-determinism to implement multitasking, a form of multitasking. And particularly in Unix, the primitive for doing multitasking is fork, which duplicates its calling process. It typically returns an integer that indicates the process identifier for the child process. Here I'll make a simplification and just have fork return a boolean. So we'll take true to mean that it's the parent branch is returning to, and false if it's returning to the child. So we can implement fork simply as just an operation that is do fork that returns this boolean. Then the implementation of fork, or the interpretation of fork, is we can give that in terms of the standard non-determinism handler, or if you're familiar with monads, the standard sort of non-determinism monad. So it'll take one of these fork invoking computations, and then it will return a list of answers, because fork will cause this computation to duplicate itself. So there'll be multiple answers potentially. So the way we implement this is pretty straightforward. In the case that it returns, we lift that answer into the singleton list. In case fork is invoked, then we grab the continuation, and then we invoke this continuation twice. First with true to sort of explore or run the parent computation, and then subsequently with false to run the child computation, and then we concatenate those results together to form the final list. So we can have some computations here. So I have a computation called Richie, which echoes a quote from Dennis Ritchie. And I have a computation Hamlet that quotes some of Hamlet. Now we can plug this together and we can see it all in action. So example 4 here, we installed the basic IO handler. Then under there we installed the non-determinism handler. Under that we installed the session manager handler, and then the status handler. Then the computation immediately forks, and in the parent branch it impersonates Alice, and then she will perform the write the Ritchie code. The child branch will su as Bob, and then perform the Hamlet code. So let's see what happens here. Right, so now we have two processes that finished, both with execute 0. And then the state of the file here is now the concatenation of the two quotes. So Unix is basically a simple operating system, blah, blah, blah. So as you can see, there's no interleaving a computation, or maybe we got incredibly lucky and all the writes just happen to be in order, but I can guarantee that there is no interleaving a computation here. Everything still happens entirely sequentially. So one way to sort of get time sharing or give everybody an ability to run is to have some way of interrupting processes. And we can do that by introducing another operation called interrupt, which simply returns a unit. And the idea here is that when interrupt occurs, then we're going to transfer control from one process to another process. And in particular, what we're going to do is we're going to verify the processes here. And there are two states a process can be in, which is captured by this p state type here. Either a process can be done with some return value, some result, or it can be in a paused state, where we have a func here that can perform some effects E, and then it will return another instance of this p state data structure with the same result type and the same effects E. So a handler for this, which is called verify process here, will take computations that can perform interrupts and some other stuff. So there's some explicit effect polymorphism here. I will omit the details. And then it creates one of these p states with the return type and the additional effects that the computation may perform. Then the implementation here is rather straightforward. So in case it returns, we just tag the return value with done. In case interrupt happens, we grab the continuation, and then we wrap that in or tag it with a paused tag, and then I explicitly abstract over here because the resumption has to apply to unit, and the definition up here expects a func, an auxiliary function. So people who are familiar with this will recognize this as the resumption monad, and that's basically all that's going on here, but in direct style. Then using this p state, we now have a data structure that we can manipulate. We can write a little scheduler. So we write a scheduler here that operates or lists of these processes, or the states rather. So they will return some A, but in doing so they might fork, meaning they might create additional processes. Ultimately, we just return all the answers. So there's this list of processes, and the way you then go about and do this is you do some explicit state parsing, recursive function here that keeps track of the running processes and those that are done. And the one case that I want to draw attention to is the paused case. It says here, if the head of the process list is a paused computation or process, then what we do is we recursively perform schedule on the tail of the process list, but we concatenate that with non-det applied to this continuation we got. And remember, non-det is the thing that's going to handle any invocations of fork that might appear. And itself returns a list of answers. With this, we can then implement timeshare, which handles both fork and interrupt. It returns a list of answers. Before I have an example, we still need to talk about how we actually inject interrupts, because right now we have interrupts, but we have no way of sort of having them appear in code. One idea is to use sort of an external source to inject interrupts. That's what Daniel Arman and Mattia Pretnar, they have this very nice work on asynchronous effects. However, this depends on having something outside the language. There's some ambient environment that are going to inject these interrupts, and this is going to violate one of my constraints, so I cannot use this. This will not be definable in the language. Second idea is to actually bundle interrupts with other operations. So we could sort of, before we perform a write, we could perform this interrupt. So concretely, we could recall the echo. We could do a sort of echo prime here. Again, takes a string, and then it will perform an interrupt, and then afterwards it will do the write. So concretely, in the definition, you do interrupt followed by do write at the file descriptor and with string contents. This will work fine, and it works. However, it violates the second constraint, namely that it modifies the interface of the function. Now I had to change the type of echo. I had to introduce this interrupt, and in fact, I'll have to introduce it everywhere where I use operations, because any operation I want to actually be able to interrupt or yield from will now need to mention this. So I can't use this either. The third idea is to use another handler to overload the interpretation of operations. So here I have a handler called interrupt write, and it takes a computation that can write. And then what it does is that the handler itself will perform the interrupt, and the write, it will sort of replay the write operation. And you'll see here concretely in the code, if you look at the write case, it performs the interrupt here, and once the interrupt returns, then we invoke the resumption with whatever interpretation we got from performing the write. So this write here will not be handled by interrupt write, because we're now outside of that context. So something further up the context will have to handle it, namely basic IO, as I'll show you here, which is my final example. The time sharing example here, example 5. So what we do is we first install the basic IO handler. Under that, we install the time sharing handler. Under that, we install the interrupt write handler. And then under that, we install the session manager. Under that, we install the status handler. And then the computation is as before. We see here, if we run example 5, we get the following here. Again, 2 processes ran to completion, both with exit code 0. And then we get this state of the file is Unix is basically to be or not to be a simple operating system. That is the question. But whether to snowblind the mind to suffer, you have to be a genius to understand the simplicity. So as we can see here, the different echoes has been interleaved, and as a result, we have some new poetry, and I'll leave you to be the judge of the quality of this poetry. Right, so that's the final thing I wanted to show now here. I hope this was enough to convince you at least, or give you a taste of the power of effect handlers, and also to convince you that you can actually use this to retrofit legacy code with new functionality by just installing a new handler, oftentimes. I hope also to convince you that operating system can be explained in terms of handlers, and we can sort of see handlers as small composable operating systems. And it's done.
Fantastic. Thank you, Daniel. So there were a lot of questions, or some questions in the Q&A tab, and they have actually already been answered by Daniel. There seems to be one question popping up here by Matthew Fluid. It seems that you need a wrap X for each set of the effects X, but the behavior is completely uniform for each effect X. Can you provide a single uniform wrap function?
Yeah, no, I think that's a good observation. I think this is just an artifact of the language that I'm working in. So in Lynx, one thing I didn't say is that all the effects are structural. If I had sort of a nominal way, I could probably just have the compiler generate the wrappers for them. And you have sort of more like a function call every time. It could probably look slightly nicer. But yeah, I have not implemented that in the support in Lynx. But I think that is, yeah, for actual usability, I think that is a pretty nice point. Pretty crucial.
So I guess so I have another question that probably are related a little bit. So of course, and you also mentioned that at the very last sentence, I think, using it for building microkernels, where I could imagine that you could get kind of optimized code out of just using the handlers that were necessary for the particular program. Can you reflect a little bit on this?
Yeah, so whether or not you could optimize it, or you could.
Yeah, I guess with Lynx is not. I mean, there could be other things that where you could actually build microkernels and actually install them on.
Yeah, no, I definitely think that is possible. And a question that typically gets is, are we far off being able to write operating systems this way? And I think the only piece that's missing is we have some industrial strength language that would support effect handlers, and OCaml is going to bring them in a sort of near future. So maybe something like the Mirage project, which is basically these microkernels, they might be able to actually take advantage of some of these abstractions to get the things in direct style. So I think, yes, very much. I think it's possible, and I think it will be possible soon.
So related to that, a little bit comparison with the modules approach that are used in the Mirage OS. Is this an alternative in some way?
Yeah, that's another good question. The way I usually view these things is modules are rather static things, a compile time thing. That's usually how I think about them. I know you can do dynamic instantiations via functors and this, but handlers are, in the way I see them, entirely dynamic. So you can do many of the same things with handlers that you can do with modules. And I think, as with anything, it's sort of a balancing act to find out when it's appropriate to use what abstraction or what mechanism. So I think they can complement each other nicely. The thing that handlers give you is that you can sort of cross function boundaries, right? You can pry open this black box. This is what the limited control really gives you. And here you get a sort of nice direct style, fully typed, and stuff like that. So you get to do really powerful things. Whereas if you do the full module approach, I believe you probably have to do a bit of plumbing, pushing parameters around and stuff like that. It's a dynamic binding example, right? Illustration of this. You get to jump or your entire context to read the value of this particular variable that's bound in whatever dynamic context you're running in.
So another question that could pop up, how about formal reasoning about the system? Is that something where an approach like this will
yeah, so I hope so. I know other brilliant people be working on sort of formalisms for or logics for handlers. So I would certainly hope so. And one thing I've done in this example here, so I've taken some liberties. So I took Ritchie's and Thompson's paper and tried to interpret it as handlers, but I also took some liberties in that in interpretation. Like I went really hard for I want the standard textbook effects. I want to stand out as clearly as possible. If you want a little bit closer to Unix, you'll have to merge some of the things I did here into one handler. But the thing about the standard textbook effect, and this is where I believe they will be good for reasoning, is that they all obey like well-known operational theories. So I think there's a hope you could give a semantics to Unix, and hopefully not break too far off these standard effects. Then I think we can sort of if we give you an operational theory there, I think we can put something together that would give a handler semantics for Unix. Not something I've done yet, but it's just something I've started thinking about.
Okay, thanks. Let's thanks the speaker again.
Thank you.
And let's see the next talk. I don't have the overview here.
Breda, and I'm here to present you our
Camelier, yes.
work on Camelier, a deductive verification tool for OCaml. This is joint work with Antonio Ravara, also affiliated with NovaLinks, the computer science lab of Nova School of Science and Technology at Portugal. So let me start this presentation by giving you a quick recap about the history of Camelier. Camelier has been publicly or officially presented at this year's CAF with the publication as a tool paper with the same name as this presentation here, and it has also been presented as a tutorial on Sunday, an ICFP tutorial. So if you missed the tutorial, no worries, this presentation will be a sort of shorter version of this same tutorial. Okay, so let's start this presentation by looking at nowadays research on deductive verification. And so one can actually say it has been quite successfully applied for the verification of programs written in imperative languages. And one can cite a number of different research tools like Boogie, Daphne, Verifast, Framacy, Workhorse, and so on, which are used to verify intuitive programs. But what is somehow surprising is that deductive verification has been seldom applied to the functional world. So let's pick OCaml, for instance, as an element of the functional family. OCaml, for most of the time, it features a clear syntax. It has a well-defined execution model, or in other words, simple and well-defined operational semantics. And it's a multi-paradigm language, which means that one can very easily write concise, efficient, and type-safe code. Also, OCaml is the language of choice to implement software where safety and security are of utmost importance. For instance, proof systems, software analyzers, SMT solvers, or out of a more academic world, software like MirageOS, the Docker, parts of the Messenger at Facebook, and more recently the Tezos blockchain. So it seems like OCaml code is a good target for deductive verification. And yet, there is no easy to use deductive verification that tackles code written directly in OCaml. The two options nowadays would be to write the code in a proof-aware language and then extract it, which means that one would need to rewrite entire code bases just for the sake of formal verification, or turn into the use of an interactive tool, which is hardly the choice for the regular programmer. So our big goal is to build a deductive verification tool that OCaml programmers can really use. So, what do we need? What are the main ingredients that we need, and where should we go in order to achieve this goal? So, first and foremost, we need a specification language for OCaml. In order to annotate code. Then we need a VCGen to compute verification conditions from the input annotated program. And finally, since we are targeting automated verification, we need SMT solvers to be able to discharge these generated verification conditions. And so this is how the Cameleer project is born. Cameleer is a 2 years project founded by an individual Marie Curie Fellowship, and our main target, our big goal, is to build the first automated tool for the verification of OCaml programs. And so far, up to this point, we we have employed 2 main ingredients. First, we are using Gospel, the recently proposed generic OCaml specification language, in order to attach specification elements to OCaml implementations, and then we are translating our annotated OCaml code into the Y3 verification framework in order to conduct deductive proofs. So, very briefly, let me give you some details about the Gospel specification language. So, Gospel was designed to be an expressive specification language where user writes its specification in a sort of extension of first order logic. Okay, so it's mainly first order logic extended with algebraic data types, recursive definitions, and a flavor of high order logic. I'll give you a little bit more of details in a couple of minutes. It is a concise specification language, which is an improvement over directly using separation logic. Very importantly, Gospel is not tied to any particular verification tool, and we have also took care to provide the formal semantics to Gospel via a translation into separation logic. If you are interested and want more details, please check out our paper that was presented on Symposium Formal Methods in 2019. Okay, so in practice, Gospel, or we hope that Gospel feels natural to OCaml programmers, mainly because Gospel terms are written in a subset of the OCaml language itself, plus the use of quantifiers. In order to treat Gospel elements, we use on the background OCaml attributes and the PPX lib technology. So, for instance, this is an example of a function, the empty function, that is annotated with some Gospel elements. For instance, here we say that this function empty returns a new value of type t, which we call r, which has size 0. So imagine that we have a logical function called size, and we say that for all element x, its occurrence inside the new data structure is equal to 0. Gospel is a collaborative development with contributions by myself, Jean-Christophe Filiatre, Claudio Lorenzo, and Clément Pascuto. I provide you below the GitHub link for the public development. Okay, so now let's continue this talk with a more precise focus on the Cameleer tool itself. So first and foremost, I'll describe the architecture of the tool itself. Then I'll provide details about translating OCaml annotated code into the YML language, which is the language of the Y3 verification framework. And I will conclude providing some closing remarks and future work perspectives. Okay, so from a very high level point of view, how does Cameleer work? So in this diagram, on the left hand side we can see the OCaml dimension, and on the right hand side we can see the Y3 dimension. And what is very important here is that the full boxes represent what the programmer must write by hand, and the dashed boxes represent what is automatically translated. So what is clear from this diagram is that when using Cameleer, the programmer is always focusing on OCaml code, whether it is .ml files, OCaml implementations, or .mly files, OCaml interface files. Alright, and the verification or the proof part, which corresponds to the Y3 dimension, is always automatically translated by the Cameleer tool. So if we zoom in on this translation part, what we are proposing is in practice is that instead of using Y3 as of today, which means that one will need to write an implementation, an algorithm, a data structure, and so on, directly on YML, the verification and programming language of Y3, do the proof, and then rely on the Y3 extraction machinery in order to get correct by construction executable code, which once again means that one would have to write entire code bases just for the sake of verification. Now with Cameleer, what we are proposing is that the programmer writes or focuses on the OCaml implementation, annotates it with gospel elements, and then the Cameleer tool enters the scene via this automatic translation. But before, we use the ppxlib in order to recover an OCaml AST. And so this OCaml AST is automatically translated into a corresponding or an equivalent program written in YML, and when we get to that point, now out of the box we can use any tool available on the Y3 tool set. In particular, we are able to interface with many different SMT solvers, but also when needed with interactive proof assistants like Coq. So now that we get to this point, let me show you a demo of how Cameleer works in practice for the verification of a small OCaml program. So imagine that you are given the following task. Find the maximum element of an array of integers values. So that this one it seems like an easy task, but instead of using the more traditional approach of scanning the whole array from left to right, now we are going to do in a different way, and we are going to use two references. Let's call them X and Y. And X starts at the very beginning, or points at to the very beginning of the array, and Y points to the last element of the array. And so the idea is the following. Now we have these two references, and we are either going to increment or decrement. We are going to increment X or decrement Y. And how should we do that? So when X, or the value pointed by X, is smaller or equal to the element pointed by Y, we increment X. So this is Y. In the first step, X is now pointing to 10. Okay? So now on the second iteration, the second step, X is also going to be incremented, okay, because it's pointing to 10 and Y is pointing to 13. Alright, so now X is pointing to 73. So at this point, or when it comes to this case, so now we are going to decrement Y, okay, and now once again we need to decrement Y because it's pointing to -7 and X is pointing to 73. And actually we are going to decrement Y several number of times. Okay, so decrement, and now it points to 42. And at the very last iteration, Y is pointing to -1 and X is still pointing to 73. So Y decrements, and at this point the function returns the value of either X or Y, which corresponds to the maximum element within the array. Well, this simple function has a very straightforward implementation as an OCaml program. All right, so here we use a while loop to traverse the array using the two references X and Y. The array here is called A, and so other than the OCaml implementation itself, one can very easily spot specification elements in the form of gospel comments. Okay, so inside the while loop, we can see the loop variant, which ensures loop termination, but also loop invariant, which is a condition that must hold throughout every iteration of this loop. So the first clause in the invariantly simply states that we are correctly using references x and y, so x is always less or equal to y, and y can never go beyond the limits of the array, of course. So the second clause is a little bit more interesting. It says that every element either on the left of x or on right hand side of y, so for each of these elements, either that element is smaller or equal to the element pointed by y, or is smaller or equal to the element pointed by x. Okay, and so why this invariant is enough then to prove soundness of the function is that by the end of the loop iteration, we know that x and y are pointing to the same value, so we have scanned all the arrays, so every element on the left hand side of the final value of x is smaller to this element, and every other element on the right hand side is also smaller or equal to the element pointed by x and y. Also, we can attach a precondition to the max function, in this case that this function only works for non-empty arrays. This is a precondition, right? And so as a post condition, we assert that the result R is within bounds of the array, and of course the maximum property is that every other element within the array is less or equal to the returned element. So in order to use Cameleer to conduct the proof that this implementation adheres to the specification, it is as simple as writing Cameleer followed by the name of the OCaml file. So once we do this, we are immediately presented with the Y3 integrated development environment. On the left hand side we have our proof tree, on the right hand side we have the code. Okay, so once I click here, I can see the original implementation, right? And if I choose the task tab, I can see what Y3 has generated as a verification condition for proving the correctness and the soundness of this max function. All right, so this is quite a big formula. So first, before attempting to proving it, I'm going to use a strategy or a transformation of Y3, which is called split VC, which is going to split, as the name says, my verification condition into smaller ones. And for now, these are much simpler ones. For instance, this one states loop invariant initialization. This one is for safety. I mean, every index is within array bounds. And for instance, loop preservation and the post conditions, which are much simpler now. So if I choose this node here and I call my favorite SMT solver, for instance, AlterGo, so everything is green, so which means that AlterGo was able to discharge each and every one of the generated verification conditions for this function. In other words, the specification adheres to the implementation. Alright, so is it really necessary to always use the Y3 integrated development environment for such proofs? Well, the answer is that actually Cameleer provides us with a batch mode. Alright, and once you choose to use the batch mode, you only need to specify the prover that you want to use to try to discharge every verification condition. So in this case, I'm also going to use the AlterGo SMT solver, and once I press enter, you see that there is a bunch of valid printed in green. So it means that each and every verification condition is automatically discharged by AlterGo. So in the background, the batch mode is always splitting automatically for you. So this is also another way to use Cameleer when you do not really want to use the Y3 integrated development environment, for instance, for simpler proofs and for simpler specification. Okay, so continuing with our presentation, now that I've shown you how Cameleer works in practice, let me give you more details about how we are translating OCaml into YML. So, a couple of words about the subset of OCaml that we are currently targeting. We are currently supporting what one can call core OCaml, which roughly corresponds to CamelLite, plus support for functors. So in particular, this means that we are not supporting the objective layer of the language, neither some more type-oriented features like GDTs or polymorphic variants. We also have a limited support for high-order functions. This is a limitation or a constraint imposed by both Gospel and Y3, and in particular this means that we do not support, or we are not able to prove and give specification to higher order effectful functions, only those that do not perform effects. And also we have limited support for mutability. Now this is a constraint imposed by the Y3 verification framework. Okay, and in particular this means that we are not able to deal with mutable recursive data structures, because Y3 does not or cannot statically know every possible aliasing within the program, because Y3 does not feature any particular memory model. Our translation is defined as a set of inference rules, but today I'm going to give you an overview of this translation via a couple of examples. Okay, so the first one is a very simple even-odd function, which are two mutually recursive functions. Okay, and so the Gospel elements are written in those special comments that we have seen before. And so the first step that Camille is going to do is to translate these comments into proper OCaml attributes. Okay, and so now this is a valid OCaml program, which can be very easily translated into YML counterpart. Well, in this case, now what is important to note is that the specification elements are now part of the implementation itself. Also, it is very important to note that letrec on YML is limited to functions. So if you try to build, for instance, a recursive list using letrec, Camelier will complain. Now, moving on to how we deal with cycles, or for instance, while loops. In this case, we write the invariant also as a Gospel comment, but now the generated attribute changes a little bit of the location of the comments. So now it is attached to, or properly attached to, the while keyword. But now when we get to this part, it is also very easy to produce an equivalent YML code. Okay, so the next feature is how one can build logic and ghost functions. For instance, the Fibonacci implementation, textbook implementation, is not very efficient, right? Because of repeated computation. But it's very, very interesting as a specification function, or one that we can use inside other specification elements. For instance, we can use fib inside the post condition of the fib main function, right? So what I need to do is I need to attach a logic attribute to this function, and I also say that this is a ghost function, so it should be erased before compilation because it has no real purpose for executable code. Also, the fbox function here, the first argument is only an auxiliary argument in order to make the proof and the specification task easier. So it can also be erased before compilation. All right. So this can also be very easily translated into into YML. But now we see that the ghost and function keywords are used. Function is the keyword of YML that states that the fib function can be used, both in program and as well as specification. Now, imagine that we we want to declare a type of lists that are always non-empty. So what we do, we create a new record type, we call it non-empty list, and we attach a typed invariant that says that a self field always stores a non-empty list. And now we can build a function head where the first branch of the pattern matching always asserts to false, right? And so, luckily enough, on the YML side, we have the absurd construction, which has the exact same semantic as the assert false construction, which is already treated in a special way by the OCaml type checker. Also, typed invariants are readily supported by the YML language. Okay, so now more interesting is how we deal with the module language of OCaml versus the module language of Y3. In particular, the Y3 module language is not as expressive as the OCaml one. So imagine that we have this submodule mult inside a larger development within an OCaml file. We are now going to translate this into a scope on the YML side. And scopes are for namespace management only and should not be confused with submodules. There is no such thing as a submodule inside Y3. Okay, but even more interesting is how we deal with functors, because there is no syntactic support for functors on the YML side. So imagine that we have this subset of an implementation of lefties heaps that we picked off the OCaml containers library. Okay, so in this case, what you are going to do is that the functor make is going to be turned into a scope, and the argument of the functor will be a nested scope with the same name, E. And so, after defining E, we can conduct the proof, or the code is exactly the same as before. And this translation scheme is exactly the dual of the extraction mechanism of Y3, which means that if you want to extract functors from a Y3 implementation, you would have to write your code in the first way like this. Okay, so let me conclude this presentation. So up until now we have been able to verify an interesting number of case studies with Camelier. Most of the proofs are fully automatic, and some need lightweight interactive steps which are very easy to perform within the Y3 integrated development environment. We have put an effort to verify programs of different natures, ranging from ephemeral data structures, mathematical computations, sorting and searching algorithms, high-order implementations, and so on and so on. But up until this point, the most interesting example is the union find implementation, because it features a very nice specification and implementation, but it's a fully automatic proof, and the larger development is a small compiler of arithmetic expressions into a stack machine. Okay, so up until this point, we have built a deductive verification tool for a representative subset of OCaml, and we are very happy and believe that this is an usable tool to verify realistic case studies, as shown by the number of case studies that we have been able to verify so far. In the future, we would like to be able to produce a proof of correctness from OCaml into YML, one that shows semantic preservation, and we would like to augment our class of OCaml programs that we are able to verify. As a first step, for simpler heap manipulating programs, will feature translation into the Viper intermediate verification layer.
Thank you very much. I guess we have maybe time for a single question or two. Let's pick this. How close is the OCaml extracted from the YML translation of OCaml? Would it be a shortcut to providing correctness of the translation?
Okay, so yeah. So if I understood the question correctly, so you're asking about the proof of some semantic preservation of between YML and OCaml, if I understand it correctly. So that's that I did in my PhD. So in my PhD thesis, you can find a pen and paper proof about it. In terms of printed code, we made an effort to make this code from YML into OCaml quite readable. but it's still extracted code, so do not expect it to be the exact code that one should write in the first place. Yeah.
Let's just pick a single one, an additional one. Can it handle concurrent code with LWT, lightweight threads?
Yeah, that's a very interesting question. That the answer is very short, not for the moment, but that's something that we are really interested in trying to look at LWT library, and even perhaps in the future multi-core OCaml. Yeah, but not at the moment.
So just to follow up a little bit on, do you have uses of separation logic proofs in some of your examples?
I'm not sure if I understand the question correctly. You mean if I have something that I really require separation logic, or something that
exactly. So I could see from the examples that they don't really make use of separation of heaps and things like that.
Yeah, because we use this weaker notion where you separate using regions. So we assume that in particular that every function argument is separated by definition, and that follows the model of Gospel. But for instance, if you take a look at our Q data structure, a verified Q data structure implementation, actually last year Arthur Chaguerot gave a talk here at the ML workshop where he uses his tool based on separation logic to do the proof of the same implementation. And actually we do not need separation logic in that case, because we assume everything is separated by definition. So that's why we can continue with the proof. But of course, there are some examples even from the OCaml standard library where we really need separation logic, and we do not cope with those for the moment.
Okay, thanks a lot, Mario.
Thank you.
Thanks to Pika again. And for the next talk, we will hear about Hobbit, a tool for contextual equivalence checking using bisimulation opto techniques.
Hello, I'm Yuyang Lin. I'll be talking about our tool Hobbit and its novel technique to verify equivalence. Our contribution involves a number of techniques called opto techniques, which can take a sound and complete bounded model checking tool and extend it to perform verification of equivalence while maintaining soundness and completeness. Note that in this presentation I'll be focusing on the tool. For details on the technique, please refer to the technical report. Let me start by introducing our setting. We'll be focusing on contextual equivalence for higher order programs with local state. So by equivalence we mean a relation between terms that holds if the terms are interchangeable in any program context. These program contexts are precisely the challenge in our setting. To prove equivalence, we need to enumerate all possible contexts in which a term may fit. This is hard for multiple reasons. Firstly, one needs to accurately model what contexts are allowed to do in order to enumerate them. This requires a model of the interface between a program and its context. In other words, all possible actions that a program and its context can perform on each other. Hello. Secondly, there may be infinitely many contexts to consider, on top of plenty of redundancy between the contexts already enumerated. Lastly, local state allows for non-trivial function reentrancy in higher order terms, whereby reentering a function at different points in the computation tree may alter the result. To tackle the problem of equivalence, we shall be using symbolic environmental bisimulations, which combine environmental bisimulations with game semantic models. With symbolic environmental bisimulations, the notion of equivalence is bisimilarity. The interface between a program and its environment is modeled as a two-player game. The program itself is modeled as the proponent, while the opponent corresponds to its environment. In this game, actions between the proponent and the opponent are modeled as moves, namely function applications that query one player from the other and returns to said applications. This is thus a trace semantics, where each of the traces in our game is a sequence of moves. Moves in the trace are always interleaved as players pass control to the other player after playing a move. In the examples that follow, we will be using blue for the proponent and red for the opponent. Labels for moves will be underlined if they are from the opponent. and otherwise if they are from the proponent. Note that we shall be focusing on externally observable moves. In other words, we are looking at calls between the players, not so much calls within the same player, for instance by a recursion. Below we can see two examples. We have terms M and N, each with their own transition systems. For the equivalence example, we can see the proponent starts by passing its function labeled f to the opponent. The opponent is then able to call f with unit. The proponent answers this query by returning 5, and the opponent can then keep calling f again indefinitely. We can see these two terms are bisimilar. The next example is identical except n returns 4 instead of 5. We can see then that the transition systems diverge on the proponent's answer to f. Moving on to automatically proving equivalences, Hobbit is a bounded model checker in its core. It takes a bound and performs a depth-bounded exploration of the computation tree. Tools like these are precise, meaning no false reports, be it positive or negative, and they are also exhaustive in that they enumerate all paths in the computation tree up to the bound. In practice, these are good for inequivalences, as it is relatively easy to enumerate traces up to a bound. Without any extension, Hobbit found almost every inequivalence in our test suite. Additionally, inequivalences were found relatively quickly, taking less than a second each. In contrast, without extension, it rarely found any equivalences. The question is thus, how to deal with equivalences? One of the biggest challenges with verifying equivalence is the potential need to deal with infinity. For instance, the environment may repeatedly call with a changing state, which makes it hard to identify states that have been explored already. In the first example, we have equivalent terms M and N. Since N simply mimics the behavior of M, let us focus on M. M creates a reference x and then returns a function f that increments x. Since each call to f modifies x, every call occurs with a unique state which makes it difficult to detect identical configurations. Another cause of infinity is that nested calls may grow the evaluation stack indefinitely. For instance, in the second example, M returns a function g that creates a local reference x when called. The opponent is then able to call g with some function f as an argument and passes control to the proponent. Before returning, however, the proponent needs to pass control once again by calling f. At this point, the opponent is able to call g again, and as you can see, the opponent is allowed to nest calls indefinitely. Note that each nested call happens with a different f, here labeled f1 and f2. Also note that we're using this ref keyword for references. This is for a simpler presentation of the theory. An extension to use OCaml-like general references is also possible. Our task is therefore to finitize the exploration of the bisimulation game. There are many approaches to make it easier to identify identical configurations that have been seen already. In first place, we need to remember every configuration and check new ones against old ones. However, they will rarely match as names used may be different, so some kind of normalization is needed. Additionally, because we are in a stateful setting, differences in unused references may exist too, which calls for garbage collection. In the example, we can see how garbage collection could help. M creates a new reference x that is dereferenced but never used again. Without garbage collection, every call to f creates a new x, which makes it hard to identify identical configurations. With garbage collection, however, every x is collected once it becomes unused. As we can see in the transition system, the last configuration explored is identical to the first opponent configuration, which tells us we can stop the game. However, memorization is rarely enough to finitize the exploration. This is where optotechniques come into play. These are powerful theoretical techniques used for handwritten proofs. These tell us that if certain conditions are met, for a set of states that are already part of the bisimulation, we can obtain a larger set of states from them. Notice that we can explore infinitely many states by applying optotechniques to a finite set of representatives. In Hobbit, we implement multiple standard and novel optotechniques. Some of the most impactful novel up-to techniques are the following. Up-to separation, which is inspired by the frame rule in separation logic. Up-to function reentry, which avoids reentry to functions that are effectively pure. And up-to invariance, which uses state invariance to abstract the state. I will now go through examples to illustrate every up-to technique. The intuition behind up-to separation is that one can independently explore two functions if they manipulate mutually exclusive regions of the store. A particularly useful result of this is that it suffices to explore a function once if it manipulates only its own local references. Take for instance the following example. M contains a function that takes another function as an argument. It creates a new reference before calling the function plus to it. Because calling the external function passes control to the environment is allowed to nest calls to M indefinitely. Because each call adds a new reference, it is hard to find a loop. You can see this happening in the transition system without separation. First, the proponent returns its function, now labeled j. The opponent calls j with some function f1. The proponent creates a reference x1 and then has to call f1. At this point, the opponent can branch either by returning or calling again. In either case, we are led to an infinite bisimulation game because the opponent is always allowed to call j with a new function. With separation, however, since j only manipulates local references, after j is applied once, we can safely drop j from the bisimulation game, as it suffices to explore it once. As we can see in the bottom figure, this results in a finite transition system because calls to j are prevented. In practice, this was the up-to technique that had the most impact in reducing times taken. For equivalence, this was a reduction in time by close to 3 orders of magnitude, going down from over 1,000 seconds to 5 seconds for all tests. Up-to function reentry is based on the intuition that we can skip nested calls to the same function if the function can be proven to effectively leave the state unchanged. This includes symbolic operations where constraints before and after the call can be shown to be equal. The following example is very similar to the one we just saw before. The difference is that instead of manipulating only their own local reference, all function calls now manipulate the same shared reference, which prevents the use of garbage collection and separation. Without reentry, the opponent is able to repeatedly apply j with a new parameter, leading to an infinite game. With up-to reentry, however, calls to j from within j are prevented as j does not modify the store. In the bottom figure, configurations labeled S1 are identical. This means that after preventing the second call to j, we reach S1 and the game stops. In practice, this had the third largest impact, reducing time taken by over 2 orders of magnitude. Finally, up-to state invariance works on the intuition that a constantly changing state can be abstracted to a single symbolic constant if a predicate exists that captures and holds for all previous and current behaviors observed. With this, configurations are abstracted into classes of configurations for which some invariant holds, again allowing us to explore potentially infinitely many configurations using only few representatives. Note that we do not try to automatically guess invariance, as this is a separate large area of study. Instead, we provide the framework for user annotations, which could in the future be extended to be automatically inferred. For this reason, while verification of equivalence using a given invariant is fully automatic, the technique requires a user to write an invariant, which is notably hard, as coming up with invariants requires understanding the problem to a potentially similar depth as when manually proving equivalence. The advantage is, of course, that the proof is automatically verified. Following, we have an example showcasing a similar use of invariants. Again, we have equivalent terms m and n. M creates a reference x and returns a function that increments x before checking that it is greater than 0. Without invariance, we can see in the top figure that the opponent can call f repeatedly, meaning that x can increase indefinitely, which leads to an infinite game. Now consider the invariant shown in the next figure, which states that there exists a w such that the referencing x is equal to w, and w is greater or equal to 0. We provide this invariant as an annotation to the function, written here inside curly braces. In the bottom figure, we can see that the constant stored in x is replaced with a symbolic constant w, which must validate the invariant. Each configuration then carries this constraint around, which must remain valid throughout execution. Because x now holds an abstracted value, the configurations on this abstracted value represent a class of configurations. In the figure we can see that with the help of invariants, the last configuration explored is in fact equivalent to the second proponent configuration explored, both labeled S1. This lets us end the bisimulation game. I will now proceed with a demo for equivalence. Here we have an example adapted from Meyer and Siever. Although we do not have general references, we are able to simulate them by encapsulating them as a pair of read-write functions. Function lockeq implements a standard location equality test. The function in M takes a function q. This function passes the function almost add to the opponent. Inside the function body, a reference x is created. This reference is then encapsulated by two read-write functions, which are there named locx. The two terms are equivalent because the opponent can only increase x through the function almost add. Since the opponent can call this function unboundedly many times, the game is infinite. However, the annotation applies to the state invariant w mod 2 equals 0. In other words, it's checking if it's even, and separation drops repeated calls to the outer function. This makes the transition system finite up to permutation of symbolic constants. Running this on Hobbit, we can see this is the case, taking only a few milliseconds. Next, I will demo an example of inequivalence. This is a simplified version of the withdraw function adapted from the infamous DAO smart contract. This simplified version simulates withdrawing 1 unit of currency from a total balance available of 100 units of currency. The two terms are almost identical, except for the parts underlined in red. The difference is in the update order. The first term calls send before updating the internal balance, whereas the second term updates the internal balance before calling send. The balance is returned so we can check if the same updates have occurred on both sides. Calling send passes control to the environment, which allows the environment to call withdraw again. If the internal balance is not updated first, the reentrant calls to withdraw bypass the check that there is sufficient balance available. Running this on Hobbit, we can see that the bisimulation fails. Hobbit finds a failing trace, where the opponent in M is allowed to re-enter withdraw and keep decrementing the balance. In contrast, N cannot make the same move, and the traces diverge. To briefly go over our experiments with Hobbit, we tested Hobbit on a total of 173 examples. These involve 2 programs being checked for equivalence. Every example ran on an Intel i7 laptop and was timed out at 150 seconds. Examples were divided into equivalences and inequivalences. 105 examples were equivalences, roughly 3,900 lines of code. Without up-to techniques, only 3 of the equivalences were found, taking over 2,000 seconds. With up-to techniques, we saw a dramatic improvement of 72 equivalences found, taking under 6 seconds. For inequivalences, we had 68 examples checked, roughly 2,300 lines of code. Without up-to techniques, 65 inequivalences were found, taking over 500 seconds. With Opto techniques, we were able to find all inequivalences taking around 20 seconds. Agreeing with our theoretical soundness and completeness, no unsound result was reported, and inequivalences could be found as long as there was sufficient memory to explore the game up to the required depth. A link to our tool and the technical report can be seen on screen. Finally, to end this presentation, I'll go through some of the related work. First, there are other tools for contextual equivalence for stateful higher order terms. Of these, the most advanced is Siteki. This is based on logical relations with pushdown systems and heuristics. It is generally incomparable to Hobbit as it can prove many equivalences Hobbit cannot prove. For instance, problems involving wall bracketing of observable moves. However, it also fails to prove some equivalences Hobbit can, and additionally provides guarantees only on the subset of a camel it covers. In our tests, Siteki was generally slower than Hobbit as it produced horn clauses which are a lot harder to solve than the SAT CNF formulas Hobbit produces. That said, there were many examples where Siteki was able to prove equivalence very quickly, whereas Hobbit struggled or was unable to prove equivalence. The differences show the techniques are different and generally incomparable. Still, Hobbit imposes less language restrictions than Siteki, and thus proved more equivalences in our tests. The second class of tools are those for first-order C variants with global state. Again, one can say these are incomparable, as these tools are very optimized for internal term transition, which tools like Rev do better than Hobbit. However, Hobbit handles a harder problem, not just because we focus on observable external transitions, a concept that is often not even present in the first-order case, but also because global state is a simpler setting. In addition, technology to handle internal transitions does not seem to be incompatible with our technique. For these reasons, we believe the technique behind Hobbit to be promising, as it not only handles problems that state-of-the-art tools cannot, but also serves as a framework to produce equivalence verification tools relatively easily by extending boundable checkers of simple design. This concludes my presentation. Thank you very much for your attention. If anyone has questions, I'd be happy to open up for discussion.
Thank you very much for the presentation. We have a number of questions in the Q&A bar here. So the first one by Antonio Rivera. How do you deal with silent divergency? Is M equivalent to M semicolon infinite loop without effects or visible actions?
Hi, can you hear me?
Yes.
Yes. So this was mentioned just at the end of the presentation. We detect the divergence that is annotated by this special div term at the moment. We hope to incorporate techniques to extend support for other kinds of internal infinite loops.
Okay, thanks. And we have another question here. How far do your methods apply for pure, that is, pure context, those without side effects?
I'm not sure what you mean by how far do your methods apply?
So I guess whether some of your examples are, maybe I can expand a little bit on the sizes of things that are maybe not using side effects, or.
Yeah, just think of pure languages, for example, and can you prove the equivalence shown on the screen, for example?
The equivalence on the screen. This
applied twice.
Yes.
You're calling the same function once or twice.
In this case, the observable moves wouldn't be equivalent, I think, because the context can the context is being given control twice.
Yeah, but in pure languages they are equivalent.
I see. In our case, I think it wouldn't be an equivalence.
Okay, thank you.
Okay, thank you.
The observer is impure, by the way. So.
There's another question here. I wonder what is a typical sort of programs where we would want to use a tool based on this approach?
So these would be these would be programs with higher order behaviors, in my opinion. Things that I can think of are any kind of programs that, when I say higher order behaviors, I mean that the control is passed to the environment, right? So programs where you have a context which is unknown, right? And say you're refactoring code or you're making changes to the program. You may want to check if the same program is still performing the same behavior, and the kind of program that it has is the kind of behaviors that it has is higher order behaviors caused by the context. So in this case, for instance, a program that calls a library, and to call the library, it needs to pass control to another player, let's say in the game. So it has another component, it's passing the control to the operating system, for instance. Just mentioned before was the DAO example, where the higher orderedness is not very obvious, but it was caused by the need to pass the control from the smart contract doing the withdraw to the user's send function, which is a kind of a contextual behavior there.
Okay, thanks. So just another question. In case you have, I guess one uses of this kind of tool would be to see whether you have an imperative version of a function, whether that is equivalent to a more functional style implementation. Is that do we have examples that can prove these things, whether things with an accumulating parameter is maybe similar to something with keeping local state?
Yeah, so that's an interesting question, because if you want to deal with the equivalence between a functional version of a imperative program, you would have to deal with internal recursion, something we currently do not focus on. But it's not something that cannot be handled. We have some examples of showing that the sorting algorithms are equivalent if you use, let's say, as long as a finite, just as a disclaimer, because we do not finitize recursion, but as long as they are finite, you can prove that a one that uses arrays would be equivalent to one that uses tuples, for instance.
Thanks a lot. So there was also a question earlier. I saw that whether there are any correctness proofs, and I think you mentioned that briefly as well. Is that something that you can reflect on, the theoretical correctness of the claim that there are no false positives or false negatives?
Yeah. So there's on the technical report, you can see some of the proofs. We have proofs of the soundness and completeness. So this is based on a complete technique. You have a bound, but it's a complete, exhaustive enumeration of all traces. So as long as you have as long as you have a complete base bounded model checker, you can extend it using the sound techniques, these OPTO techniques. And since they're sound, they do not affect the correctness of the report.
So it would be a no false positive or negatives.
Maybe we can just make one more, answer one more question by Edwin. Is equivalence defined only on the result? If one implied uses a local hash table and thus has mutation, but otherwise produces the same result, would it be equivalent?
So equivalence is defined on the it's a by simulation based on the observable moves. So by observable moves, I mean what the observer can see, right? In this case, if you consider the game between the program and its environment, the observable moves are moves that pass control between one and the other. For instance, if I have a program that calls a library, calling the library would be an observable move. So there will be equivalence of the moves that occur between the components. This includes returns, by the way.
Okay, let's thank the speaker again, and that this talk finalizes this session. Thank you.
Thank you.
Thanks, everyone. We'll take a break and then we'll resume in 30 minutes. Thanks to the speakers and session chairs. Okay, apologies. I had some issue with AirMeet and I had to reload AirMeet because a bug was preventing me from seeing the list of people. All right, I'm promoting the session chair. Bob.
Hi
Hey,
there,
Bob.
can you hear me?
All right, you're live. Everyone should be able to hear you. Thanks for being the session chair. I'll leave the stage to you. You can introduce Jacques, and then I'll go try to find Jacques' video as well. You do that.
Okay, I'm sorry there's no picture, or at least I can't see a picture. I came up with a picture. Anyway, welcome to the second session at the ML workshop. And this session is entitled Compiler and Language Correctness. And our first talk is about formalizing OCaml GADT typing in Coq. And I believe the speaker is Jacques Garrigue. So hopefully this will now start. And if you have any questions during the talk, then please enter them in the Q&A tab under Conversations in AirMeet.
I'm going to talk about formalizing OCaml GADT typing in Coq. This is joint work with Xuan Ruiqi. Principality of GADT inference is known to be difficult, but in OCaml, the type system has proven to be principal thanks to a notion of ambivalent types, which allow to detect ambiguity escaping from a branch. Here we see two examples based on a classical witness. In the first example, we are receiving a witness that a is equal to int and use it to type this if expression in which both branches are returning x. And in the case of OCaml, it is assumed to be principal, and this is returning actually a in both branch. On the other hand, GHE rejects that as ambiguous. On the other hand, if the if expression is changed to return 0 in one case, since x was supposed to be type A, well, the if expression itself is typeable, with a in one case, int in the other. Both are compatible since we have the equations, but since we cannot choose which one we should be returning, this is deemed ambiguous. How is it done? This is types that rely on GADT equations are represented as ambivalent types, which are a form of intersection types. And ambivalent types are only valid when equations are available, but the relation of equations is implicit. And what we are doing here is, well, first we are adding the equation to the environment. Using this equation, we can compare x and 0. That is, x is of type A, but actually it can be seen as type int. And in both cases, we're returning x. And since we are returning x in both cases, actually the return type is just a. On the other hand, here, since we're comparing x with 0, it has to be both a and int. And as a result, we have a current type such that we are receiving something of type alpha, returning something of type alpha. In the other ambiguous case, what happens is actually, since one branch is returning something of type A and the other of type int, we get an ambivalent types of type A and int, which is not valid once we leave the scope of the equation, and we get an error. Actually, OCaml and Haskell differ in their handling of unification under GADT equations. In Haskell, unification under a GADT equation cannot involve variables from outside. This is the outsiding algorithm. On the other hand, in OCaml, this is allowed as long as the equation is not required for the unification. This is ambivalence. The point is that relying on ambivalence is sound with respect to in-place unification, because it tracks whether local unifications are still valid outside. And also, it can ensure principality of inference, because alternative types are going to be rejected. The idea is that in this example, while we could actually in the type system decide that this x is to be seen as int. This will not be not just int, but actually it wouldn't necessarily have to be a and int. And as we've seen here, if the return type is a and int, it will be rejected as ambiguous. So the only possible types is going to be a. Of course, we can still use type annotations to hide the ambivalence by separating in our return types. Here, for instance, we have in one case we decide that the return type is a, in the other case we return that the return types indeed they are both valid. And while here we write the annotation inside, which is correct with respect to type system, OCaml of course allows you to write it outside. Is it really principal? Well, when looking for reduction rules validating subject reduction, we came upon the following example, where using here two witnesses, one says that a is equal to b arrow b, and the other that a is equal to int arrow int. And we realized that when you do that, actually according to the order in which you use the witnesses, applying g to 3, which necessarily requires using one of the equations, is going to return a different type. In one case, we're returning a b. In the other case, we're returning int. Well, clearly, there is a problem. And by looking carefully, we found a bug in the theory. That is, the ambivalence of g is not propagated to a result of the application of g to 3 and failing to detect the ambiguity. The bug was not really hard to prove, to fix, at least on paper, but we want some guarantees about the correctness. And since we have already proved the soundness and principality for another fragment of OCaml that use a graph representation of types, this is the structural polymorphism about polymorphic variants and object types, actually we thought that we could reuse that for ambivalent typing, which is also a type system based on graph types. Here, how does it work? It's basically that when you have a judgment is also using a kinding environment, which you can see as a graph, that is a mapping from variables, which are node names, to the kinds that are going to describe the nodes. And actually types then are just pointers to something inside the graph. And by enriching the information in kinds with real variable passes, we can represent correctly ambivalence. Principality is still going to be hard to prove, but subject reduction is already a good benchmark for a well-behaved type system, so this has been our first step. Here are the technical part. So the idea is that we want to encode ambivalent types, and here we are going to encode beta to gamma and a. And the way we encode it is through this graph and with a pointer alpha. So alpha is an arrow type with domain beta, codomain gamma. And the ambivalence is denoted because we also indicate that it can also be seen as having type A. And beta and gamma are the children of alpha. They are just variables, but there is a well-formedness constraint which requires that they should get actually the rigid variables. So they get children of the rigid variables. So beta is going to be a.dom and gamma is going to be a.cod. Now looking about all the types we have, actually there are two kinds. There are the graph types, which use this kind of constraints. And there are also three types that we are going to use for equations to make the theory more manageable. Well, three types are basically used only for type annotations and equations, and the graph types are used for everything else, kinding environment, type schemes, typing environments, and substitutions, which are just mapping between variables. Since our types are just variables, they are seen as pointers into a graph. Of course, to make it work, we need some notion of well-formedness. So we have many well-formedness judgments. One is just talk about the kind being well-formed in the kinding environment. In particular, the restriction about children of a node needing to inherit rigid variable paths is part of this notion of well-formedness. In turn, since kinding environment is multi-layer recursive, we define the well-formedness of a kinding environment and the well-formedness of a typing environment. And we also notion of validity of a substitution between two kinding environments, which is basically saying that the substitution theta is mapping a morphism of graph. Another judgment we need is an embedding, how to embed a tree type into a graph type. Our terms, well, they are just the classical one, extended with type annotation, witness introduction, rigid variable introduction, and witness elimination. And witness elimination, for simplicity, will require explicitly to indicate the equation we are introducing. Now, our typing judgment, they are going to use the environment we've described. So the equation environment, kinding environment, typing environment, and the dance environment M as type alpha, which is actually something described inside the kinding environment. And if a typing judgment is available, then this implies that a K is well formed under Q and gamma is well formed under K and Q. Now, an example of embedding is the first program we've seen. This can be encoded as this program here. And the main change is that since we do not allow type annotation abstractions, we must either use a let or use the fact that witness elimination as an explicit annotation. So this way we've kept the annotation. Since we don't have if, we just define add something to the environment. So the if pos, which is for all beta into beta to beta to beta. Well, in expanded forms as a graph type, this gives something like that. Okay, here are some of the typing rules, and the one we'll be using to type these examples. The first one is witness elimination. Well, the idea, if you have, well, basically, if alpha 1 embeds the equations between tau 1 and tau 2, and M1 as type alpha 1, meaning that it is a witness of this equation, then we can use it to introduce the equation tau 1 equals tau 2 and use it to type M2. In practice, when you use it, we will use the GC rule, which allows to remove some kinds from the environment. The var rule relies on substitution to do the instantiation, and the app rule shows how you decompose a type in the kinding environment. So alpha is supposed to be an arrow type with domain alpha 2 and codomain alpha. So how does it work for detecting ambiguity? Let's see first for first example. Basically, what's happening is well, we've eliminated the witness, so we have the equation a equal int, and in this environment, in order to type if pos to the app rule, we are going to need actually to embed all those. So we need to add all these variables to k. But the GC rule allows to remove everything that is not accessible from gamma and alpha. Well, when I say not accessible, it's transitively from gamma and alpha. So actually all the internal nodes can be removed of the application. Not only internal rows of the applications, but also the first argument of x, which is supposed to be of type int, disappears in the result, since the result is just the type of the second and third argument. So the idea is that the second and third x are going to be typed as beta. The first x is going to be typed as something which is going to be ambivalent of a of int, but this we can remove with GC so that we finally can use the rule use to finish the derivation. On the other hand, if we consider a minimal derivation for G3 in this, which is an example corresponding to the problematic example we were describing, what happens is that, well, we are adding here the equation a equal into int, and we are typing j of 3. But the problem is the result of typing j to 3 then needs to be an ambivalent type of int and a.cod. And since this is the real type, we cannot remove it with the GC rule. So the ambiguity is staying around, and this is going to be rejected. Now to our code development. It is based on a certified implementation of ML with structural polymorphism and recursive types, a work I did a while ago, which was itself based on Arthur Scherger's development using locally nameless cofinite quantification. We've been careful to make it manageable, for instance, by avoiding unification in the type system by interpreting Q as the set of its rigid unifiers. Well, other clever choices. And as a result, we could eventually finish proof of subject reduction for the following rules. Well, the first three ones, beta, let, and delta, are traditional. But the other three are more unusual. In particular, these two ones are about decomposing type annotations, something you don't need usually in type system, where type annotations can be discarded. But here, since our type system is specifically one which is intended for inference, if we discard type annotations, the derivation will no longer be valid. So we need to keep the type annotation. In this case, it's easy, decompose the one on the argument and the result. But if this is a rigid type variable, which happens to be equal by an equation somewhere else to an arrow type, then we need syntactically to decompose it. And this can be done, as we explained, by annotating the argument as rDOM and the result as rCode. Last, if we have a trivial witness, it happens that we can actually remove it. So, what is the relation of all that to principality? Well, subject reduction and principality are independent properties. So for ML-like type system, principality is rather a combination of two properties. One is monotonicity, the fact that the type derivation is still valid using a stronger typing environment where types are more polymorphic, and the existence of a most general unifier, which means that unification of types is going to admit a most general solution. An interesting remark here is that, for instance, the outside-in approach in GHC is not monotone. So we can say that actually that type system actually is not strictly principal. It enforces that the derivation is always R principal, but the type system itself is not. So this is completely unrelated to subject reduction. However, the existence of MGU relies on the ability to decompose types, which is also exactly what we needed to prove subject reduction for annotated applications, explicitly in that case. So while subject reduction in itself says nothing about principality, the mechanisms we added to the type system to do that are the ones that will allow unification to work. And it's actually surprising that we didn't realize from the beginning that the way unification was doing was deficient. So what remains to do? Since we work on subject recognition, you could think proof type soundness. However, actually, using this type system to prove soundness is not a really good idea. One problem we have actually is that the rule for the introduction of rigid type variables does not really commute with the other reductions. So we need an explicit type system to prove soundness. And if we're going to prove to use an explicit type system, translating into a more classical one is probably the way to go. Actually, there are already some formalization of type soundness of JDT described here. The other one, the one we think is also essential, is to prove principality. This is hard. A first step is the existence of most general unifier, and we said we think we are in good position to do that. Last, there is also the soundness of type inference as another role of Anvilas to ensure that. It would be interesting to prove it not only for the type system we described here, which is explicitly geared at principality, but even for non-principal versions of the type system, because maybe it will allow us to see that even if there is a bug of principality in OCaml, this doesn't cause a bug in soundness. Actually, the bug we have described today seems to have no impact on soundness, because it doesn't change the detection of sharing. So further applications, graph types are also used inside OCaml to enforce the principality of first-class polymorphism of first-class modules. So here is an example for first-class modules. If you define this way a function that takes a first-class module of such a signature and then unpack the first-class module as an explicit module and apply it, this is typable, even though we didn't write the signature directly at the point we unpack, because the information on the annotation is propagated to the use point. On the other hand, if the information comes from somewhere else in a way that is not deemed to be principal, this can be detected and you get a warning. And the basic idea behind that is that the type is known if it is not shared with the type environment, which is exactly the same technique I described for ambivalent types. So the extension should be, at least in theory, straightforward. In practice, many lines of code. We've also been investigating other approaches to soundness. And how to make OCaml type inference more robust. One is a direct approach by making the internal structures of the OCaml type checker abstract and having unification follow precise laws. Well, ultimately, the idea is that the type inference algorithm should look like its formal definition. And we've been making some progress, at least to make unification be closer to its logical counterpart. This is joint work with Takafumi Saikawa. Another one is indirectly by translating the type annotated source tree, which is the result of OCaml type inference, into Galena programs in Coq and relying on Coq's type soundness to guarantee OCaml's type checkers correctness. So this is actually a way to guarantee that each type check program was correctly type checked. This is not a general check on the type checker itself. But it is interesting to have this kind of double guarantee. The description of those can be seen on this page, and also where is also the description of what I talked about today. Thank you very much. I'm ready to take questions.
Okay, thank you, Jacques. Are there any more questions? There was one question in the Q&A, but I believe it's been answered. Does anybody else have any questions? I was, here's one.
Well, it's currently not. So this is handled in OCaml. This is not handled specifically in this formalism because, as you can see, actually, this formalism is not about really full GADTs at this point. It's only about equality witnesses. We didn't try to do anything about proofs that an equality is impossible inside this formalism.
Okay, thank you. I had a question about, you mentioned there using Coq as a kind of reference for when it's for type soundness.
Mm-hmm.
Is it possible to use your formalism to derive in some way a reference type checker?
For concerning the one I presented today, well, actually, this was already the case. That is for polymorphic variance on objects. Well, in some flavor, we could derive already a type checker. Doing the same for this framework will require redoing unification, which should not be that difficult. But also, redoing type inference. In itself, the algorithm itself is not so complicated. Proving fully a principality, my experience is that can be hard. So if we want a full specification, this is going to be some work.
Okay. And you mentioned translating to Galena. I mean, that sounds difficult for all of the features of OCaml, like row polymorphism and so on.
Yes, but the more it's difficult, the more it's exciting. So trying to already started for the simple parts. Well, the idea is that, usually people are translating, when you translate to Coq, often you translate the things that are more or less already in Coq, then it, of course, it works well. But the idea will be to encode things that do not fit so well in Coq. So that's where it gets complicated.
Okay, I mean, I think this will be our last question from Leo White. I don't know how to get it onto this. There we go. You mentioned that formalism is based on an earlier one that includes polymorphic variants. Does this new formalization include both GADTs and polymorphic variants?
Actually, so the way the formalization is done, it allows polymorphic variants inside the programs that contain GADTs, in theory, but it doesn't allow polymorphic variant in equations. Well, there is still really a problem. So I talked about the fact that the types in witnesses were trees, and the types of terms were graphs, and how to handle graphs inside the witnesses is still an open problem. Well, it's done in OCaml to some extent, with some limitation with polymorphic variants. Even at the theoretical level, I do not have a full theory of how to do that correctly and principally.
Okay, thank you very much. So it's now past. I think we'll thank Jacques again.
Thank you.
And move on to the next speaker or next video.
Hello everyone, I'm Juan Lacida Ouedraogo, a PhD student at École Polytechnique, and my PhD subject is about the implementation and the verification of encode source optimizer for driverless subway systems. And today I'm going to introduce to you CoqLex, That is an approach to generate verified lexers. To put everyone on an equal footing, I will re-explain what a lexer is. A lexer is the component that is in charge of producing tokens from source code. For that, it has to handle its location in the source code. A location can be defined as a record containing the line number, the column number, and the absolute position. The absolute position is the number of characters that have already been read or consumed. Lexical analysis can succeed or fail. When it succeeds, it produces a lexem, that is the substring that the token encodes. It also produces the token and also returns the remaining string from the source code and the position after the lexical analysis. But when the lexical analysis fails, it has to produce an error message, the remaining string in the source code, and also the current location. A lexer can just be defined by a function taking a string and a position and returning a lexing result. A correct lexer is a lexer that correctly consumes the characters and correctly updates its position. So between the input string and the output string, there is a relation. We can say that the output string is a substring, is a suffix of the input string. As we know that the position is moving from left to right and from up to down, we can formalize this relationship and say that the position in the input position is maybe is less than the output position. We can also generalize a relation between positions and input and output string by saying that the output string is the input string where the n first characters have been ignored or removed, with n equals to the difference between the absolute position number of the input string and the output string and the input string. So we can generalize it by saying that a correct lexer is a can be written in a record containing the lexer function and the correctness properties that we would want a lexer have. To implement lexers, we can either do it by hand, that is from scratch, like it has been done in CakeML, or do what people usually do, use a lexer generator like Lex or OCaml Lex. Generators use a particular description language to implement or to generate their lexers. They use the concept of regular expressions associated with actions. Actions are just arbitrary codes, and regular expressions are patterns used to choose which action will be executed or interpreted. Let's give a look to an example to the selection of to the action selection. The action selection just follows two rules. The longest match rules. That is, for example, if we have an input like A, I, F, and A, we can see that the first regular expression can match just the two first characters, so it has a score of 2. But the second one can match the whole string, so it has a score of 3. So the action that will be interpreted is action 2. We also have priority rules. It happens in case of equality. For example, if the input string is just I and F, you can say that we can see that the first regular expression has a score of 2 and the second one has a score of 2. So we take the first one that comes in the order. So the action 1 will be executed. Coq-Lex, our software verification lays on the verification of its components. The first component that has been verified is the concept of regular expressions. For that, we just reused the implementation of Takashi Miyamoto of regular expression for Coq. This implementation implements Brozovsky algorithm, and it defines regular expressions as following. We have empty regular expression that never match any string. We have epsilon regexp that only matches empty strings. We have SHA, a regular expression that matches a particular string, a string form with made with just one SHA, a particular SHA, which one is given as parameter. After that, we have concatenation, disjunction, clean star, negation, and conjunction. In addition to that, to that definition, we have the definition of the following functions. We have derivations that the derivation function that implements what transformation happens to the regular expression when it consumes a character. We also have the NU function that returns true if and only if the given regular expression accepts empty strings. And finally, we have the match function that returns true if and only if the regular expression can match the string given in parameter. With that, with those definitions, the author proved that the whole implementation satisfies the actions of clean algebra. But in order to compute the score, we had to implement a function for that. So we implemented match score function that takes a regexp and a string and return a natural number option. It returns none if and only if no prefix can be matched, and it returns n if some n if n is the length of the longest prefix that the regular expression can match. This is its implementation is source code, and we can notice that we have to analyze the whole string in order to have our score. Verification is made by proving all these properties, saying that when we return none, it means that for every prefix we cannot match any prefix of S. We can also say that if there exists a prefix that R can match, we give a score. We can also say that the score, when a score is given, the score is always less than the length of the string. And when we give a score n, it means that the n first characters, the string form made with the n first characters of S is matched by R. And finally, we prove that our score is the maximum, is the highest one. With this function, we can now implement the election. But to implement the election process, we have to define what a Lexer specification is. So we made like other generators by defining a Lexer with a list of regular expressions with associated action. But we oblige the user to set a final action that is an action that is only executed when the input string is empty. So an elector is a function that takes a list of regular expression associated with action and a string and gives back an option of two elements. The regular expression selected, the with its associated action, but also its score. We then prove that the couple regular expression and action is in the list, and it is the longest. It is the one that have the best score, and the one that follows the priority rule. Now we have to define what atomic action, what an action is. As we cannot make just side effects on the position because we are using coq, we had to implement or define the list of possible actions. We have at first the position handler that can help to modify the position. We only allow the modification of the line number and the column number because the absolute position is handled, is moved or changed during the election process. After that, we have a call. We have the possibility to call another reglex. We can make a recursive call on the current lexer. We can return a tool or raise an error. An action is a list of atomic actions. While we're implementing the interpretation of our actions, we faced some problem with the termination proofs and notice some special cases. For example, we have this simple example. Let's consider this specification and with a C as input. So with the first couple, we have a score equal to none. But with the second couple, we have a score equal to 0 and a recursive call. In that case, it means that at the beginning, the lexer has been called with C as parameter, and recursive call causes, and the fact that the score is 0 means that the input string won't change. So we have a recursive call with exactly the same parameters that definitely lead to a looping case. For usual lexer, most of lexer generators just loops because the error is due to the user specification. But in coq, we have to handle those cases because we cannot define functions that loops. So we raise a special error when we discover this kind of these cases during the execution. So we have different types of errors. We can have a user raise error when raise error atomic action is used. We have empty action error when action is empty. We don't know what to do or what token to produce. We also have the no token error. It happens when the action is not empty, but the user never returned a token. We have the loop error when a loop is detected during the execution. And we have no match error when the election says that no regular expression has a possible score for that. It means that for every regular expression, the match score always returns none for that string. After that, we notice that it can be useful to keep a variable that in what we can put everything we want during our lexical analysis. So we changed the definition of lexers and added a parameter, a type store. This type is parametric and is defined by the user. Finally, we implemented a constructor of reglexer that takes an elector, a list of regular expression associated with action, and an action for end of file or empty string processing, and returns a reglex. As a summary, we can generate. Up to now, we have everything to generate reglexers from Lexer specification, that is a list of regular expression associated with action. We prove that our election system is correct. Our regular expression interpretation is correct, and we also prove that our score computation is correct. Then we now have to implement a generator that will take a file written, a human readable file written to describe the Lexer, and to produce a Coq file that really implements this Lexer. So defined like this, a generator can be seen as a compiler. So it can have it has the same architecture. It has a Lexer, a parser, and a code writer. The Lexer in our system is directly a rec Lexer and written in Coq. The parser is written and generated by many with Coq switch that helps to generate verified parser, but the code writer is directly written in OCaml, and this is not verified. When we give a specification file and we to our generator will generate a Coq file that generates the Lexer corresponding to our specification, and also gives some files that helps for extraction and to adapt to use our generated Lexer like OCaml Lexers. The description language is quite simple. We have the header. We can set the token type, the store type, and the store default value, and those things are just the header is just copied and pasted here, and the type here is copied and pasted here, and the token type is also copied and pasted here, and etc. So to define a Lexer, we have to use it's this particular syntax. We say rule, the name of the Lexer, then parse, and that then we list we have to list our regular expression associated with actions. Actions is exactly a list of atomic actions that are just copied and pasted here, but regular expressions are interpreted, so we can write it more simply. The trailer is also copied and pasted. With that description language, we are able to implement a JSON parser, a JSON Lexer, and a mini OCaml Lexer that we use to compare the performance with OCaml generated Lexers. This way to generate code have some limitations. The first one is that we cannot when an entry point is defined, it cannot call another entry point that is defined after it, because in Coq we interpret instructions one by one, and we do not handle the generation of mutual recursive Lexers. We can see that we try to have a similar a description language that is similar to OCaml Lex, except that the user sometimes has to set the type of token and the type of store. And the second difference with OCaml Lex is that in Coq Lex, we just interpret regular expressions, while in OCaml Lex, regular expressions are compiled into deterministic finite automata, and during execution, they use the software uses optimized data structures that are implemented in C. So as we can guess, OCaml Lex is too much faster, is around 10,000 times faster than Coq Lex. But in order to increase its performance, we try to find some optimizations that helps us to go from 10,000 10,000 times from a factor of 10,000 to a factor of 500. For one of the optimization is to have sample estimators. Estimators is that if you remember at the definition of the score computation, we had to read the whole string in order to have a score. But estimators help us to estimate the maximum score that a regular expression can have. So when the estimator is proven, and we prove that, we can just instead of reading the whole string, we can just read when the maximum score is n, we can just read the n first characters instead of reading the whole string. And a second optimization was to use simplifications. For example, we know that the score of empty regular expression is always none. The score of epsilon regular expression is always some zero. So in that kind of using those properties or those equalities, we can just re-implement the score computation in order to make it faster. For improvement and future works, we can just improve, try to increase the performance of our Coq-Leg generated lexers by maybe redefining regular expressions in order to make them faster or more adapted to what we usually do. We can find some more optimizations for score computation. We can try to convert our regular expressions into automatas, and maybe we can change the way we translate or extract code in order to use more built-in data structures. We can also try to simplify the description language in order to make it user-friendly. We can try to find a way to handle mutual recursion. And finally, try to detect loops before execution. Try to analyze, make a static analysis on the regular expression on the lexer specification, and try to detect the possibility of looping cases. So thank you for your attention, and I'm ready to hear your questions.
Okay, thank you very much. It's time for the disembodied floating hands. There we go. And when Lazida is here to answer any questions, and I see there's one question in the chat already from
Yes.
Matthew Fluid. Here we go. So it's about the looping example.
Yes, we can detect it statically, but this is work, and in our case, it will be simpler if we can use automata in order to have particular example of looping cases. But when we just interpret regular expressions, it can be quite difficult to detect that statically. Yeah.
Okay, and as a follow-up, I mean, there's many reasons for statically verifying the lexer, but is it possible to find definitions of lexers which are bad in some way, like they're not doing what the specifier intended? Like there's some actions that never fire or something like that.
Yes.
Do you think you'll be able to verify things like that?
Yeah, in my particular case, in Coq and with our definition of regular expression, for example, when we detect a static, a possible looping case, how can we, what kind of message can we say to the user in order to make sure that he understands that in that case it can loop? We have, for example, to give, we have to give an example of possible inputs where it will loop, isn't it? Yeah. But but in our case, it's quite difficult, particularly because in our regular expression we have negation, and conjunction, this makes it very difficult. Yeah, but for future works, maybe we can change the definition, our definition of regular expression, in order to make it easier. And yeah.
Did you actually find the negation and conjunction useful?
No, negation and conjunction are not really important, or how can I say it, mandatory. But in some cases, yeah, we can use it. And as I was doing a prototype and or scientific work, I wanted to keep all those possibilities. But if the software is to be used by professionals, yes, we will have to delete these cases in order to improve its performances. Yeah.
I also noticed you had the store passing translation to maintain states during the lexing, right? So you pass the store through. Could you make it a generic monadic lexer? So they could, for any monad, you can generate a lexer.
Oh.
And then you can do actions in that. So then you could do something like IO actions while lexing, for instance.
Oh, I didn't think about that now. I just wanted to do something simple, but
right.
Yeah, for later, yeah. And if you're interested, maybe you can reach me and we can try to.
Yeah.
Like that.
So I think OCaml Lex has something like.
Yes. Yeah.
Okay. Yes. And there's a comment about using negation and conjunction to eliminate rule priority. Yes.
Yeah.
It's just I implemented a simple lexer generator thing which had the negation and conjunction, and they're surprisingly difficult to use, I found.
Yes. Yes, but because for example, we cannot prove when we keep conjunction and negation, we cannot prove that a regular expression is never matched. For example, we cannot prove that they're always equivalent to empty. Yeah, this is a particular difficulty here, and I think that when I will work on it later, I will remove those cases. Yeah.
And I guess a final question, if no one else has one. What's the kind of biggest language you've done? So I'm imagining a useful thing for this would be for ComCert, where you've got to lex C and then do that. Is that something you plan to do, or?
Maybe if the work is really usable, but the performance nowadays now the performance are very bad. I think it's around 1,000 not 10,000 slower than OCaml Lex. So I think there is work to do before using it really. And but to test that if it is really useful, I try to re-implement a lexer for Ada, and I succeed, but it is very, very slow.
Okay. So to the point where it's sort of
yes,
visible pauses slow. Right? Yeah. Okay. Well, I think it's time for the next talk. So thank you very much again.
Thank you again.
A round of applause. And the next talk. Okay, so the final talk in this session is code extraction from Coq to ML-like languages. I guess the video will be starting soon. So by Daniel Anakov.
Hi everyone, my name is Daniel, and I'm going to present our work with Meter and Bus on code extraction from Coq to ML-like languages. Before I start explaining our approach, I would like to say what code extraction is. Proof assistants feature expressive languages often based on dependent types, which allow to write specifications of programs directly in types. That facilitates correct by construction programming, which is important in new domains such as smart contracts and web programming. And we would like to leverage the power of dependent type in these domains. But implementing a dependent type programming language is hard. Maybe we can somehow use existing proof assistants which already feature dependently typed languages. But how can we obtain a program from the formal development? This is precisely what code extraction is all about. It's about producing executable code in a conventional programming language. And such functionality is available in many proof assistants such as Coq, Agda, Isabelle, and so on. And a common extraction target are functional programming languages. Specifically, we will focus on the Coq proof assistant. And for this proof assistant, one have a support for extraction to OCaml, Haskell, and Scheme. And general idea of this extraction procedure is to find and identify computationally relevant bits and turn them into a box, which could be further eliminated by optimizations. Therefore, proofs and types appearing in terms become boxes and further they get eliminated. And the underlying theory of such a transformation is developed by Pierre Letouzy in his PhD thesis. But unfortunately, this is not sufficient for what we have in mind. In particular, we would like to target new languages, such as, for example, languages for smart contracts. And moreover, current Coq implementation of extraction itself is not verified. But there is a very nice project called MetaCoq that adds metaprogramming facilities to Coq and also formalizes large portions of Coq's meta theory. Moreover, it features a verified erasure procedure, which is a crucial ingredient to extraction, and that's what we're going to use to build our pipeline. Here is our pipeline, and let me guide you through it. Our development is inspired by the use case of smart contracts, and we're going to talk about this use case later in the talk. And it's done as a part of the Consort smart contract verification framework. For now, we can think of smart contracts just as ordinary programs in Coq. So, green items on this slide correspond to our contributions, and items marked with a star correspond to verified procedures. So we start by developing a program in Coq from which we can obtain a template Coq representation using quote facilities provided by MetaCoq project. Essentially, it allows us to get an abstract syntax for the original program. On this abstract syntax, we define various transformations along with the procedure that generates proofs that the transformed terms are equivalent to the original ones. From the template Coq representation, we obtain a representation in core calculus of Coq called Pickwick, which is essentially a version of calculus of inductive constructions. And precisely for this representation, MetaCoq features various meta-theoretical theorems. From Pickwick representation, we obtain a so-called lambda box T representation using the verified erasure procedure of MetaCoq, and also our procedure for extracting types, which as a result gives us a calculus of array programs extended with typing information, which we use as an intermediate representation. On this intermediate representation, we perform optimizations. In particular, we remove unused arguments of constants and constructors. From the intermediate representation, we can produce code in concrete syntax with several target languages. We currently support 2 languages for smart contracts and 2 general purpose languages. And today we're going to focus on Camel Legal and Liquidity, which are Camel inspired languages for smart contracts, and the Elm language for web programming. We also integrate our development, our optimization path with the Certicoq, which is a certified compiler for Coq. The trusted code base includes the usual of Coq, plus quoting facilities of MetaCoq, and pretty printing and the runtime of target languages. As I mentioned before, smart contracts were one of the motivations for the development, and let me briefly introduce what they are and give some examples how we use our extraction pipeline for smart contracts. The smart contract technology is tightly related to blockchains, and you can think of a smart contract as a program deployed on a blockchain, and a blockchain in this case can be seen as a replicated database, and smart contracts are particular kind of stored procedures for this database. And what is so special about these smart contracts? They are designed to manage money and various assets. Therefore, typical applications include auctions, crowdfunding, multi-signature wallets, and so on. And after deployment, the contracts are immutable, meaning you cannot modify the code. And the execution of a contract is reversible, meaning that the transaction you cannot roll back a transaction even though it might contain some mistakes. And it's exemplified by several examples that even small flaws might lead to huge financial losses. And the recent attack to Poly network resulted in $600 million stolen. Many modern blockchains employ the functional programming paradigm for smart contract languages. In particular, in this case, contracts or smart contracts become partial state transition systems that take some information about who calls the contract, user-defined type of messages, user-defined state, and return new state, and a list of actions, or probably fail. So that's why it's wrapped an option. And there is a special piece of software that is responsible for executing these actions in this list. And these actions could be transfers from one account to another or calls to other contracts. In this work, we consider two OCaml-inspired languages for smart contracts, namely CamlLego for Tezos Network and Liquidity for G Network. Since we considered new target languages which are different from the conventional targets such as OCaml and Haskell, we also discovered several new challenges. In particular, it's well known that the type system of Coq is very expressive. That means that extracted programs sometimes cannot be type checked in the target language type system. Therefore, it solves in standard extraction by inserting unsafe type coercions, but they're just called unsafe, right? Because potentially it can lead to some issues, but given that we have a guarantee that dynamic semantics of our terms is preserved, inserting such coercions is usually safe. But unfortunately, such coercions are not available in our target languages. Moreover, there are certain restrictions from the languages regarding data types. For example, both in CamlLego and Liquidity, only non-recursive data types are supported, and collections such as lists, for example, are given as primitives. Also, in CamlLego, it's not possible to define polymorphic types in functions. Only, again, the ones that are provided as primitives are polymorphic. And the recursive definitions are limited, the recursive functions are limited only to tail recursive definitions. It has the following consequences. Some extracted code won't be well typed, and we have no opportunity to force the type checker to succeed due to the absence of mechanisms such as OGMagic or unsafe curves. And currently we do not support non-tail recursive functions. Moreover, since many definitions which we use in Coq, such as lists, for example, cannot be expressed directly in the target language, we need to apply so-called remapping, which basically means we say that list in Coq corresponds directly to primitive list in common legal liquidity. And the same happens with the functions defined on these lists. And basically the same applies to all collections and also to arithmetic operations. And so how do we address these challenges? First of all, we provide a certifying pre-processing step that performs some transformations such as inlining specialization and generates proofs that the transformations don't break semantics of the term. And precisely these transformations can be used in many cases to produce code that actually type text. Moreover, we allow for configuring a translation table that precisely designed to solve this remapping problem, saying that certain Coq data types correspond to primitive types in the targets. Before I talk about examples, I will briefly introduce a particular kind of dependent type that we will use for developing a smart contracts and our web application. So it's called subset types, and essentially these are types with a predicate. You can think of it as a Coq version of refinement types. In Coq itself, it's defined as an inductive family with one constructor, inductive family called sig, and a constructor called exist. And the constructor takes a value and a proof that some predicate holds for this value. So you can think of inhabitants of this type as a value proof pairs with two projections. First projection can be used to get value out of it, and second projection to get the proof. We use curly braces notation for our sig type or for a subset type, and here's just some examples how it can be used. For example, we can encode a type of strictly positive numbers using this definition, or type of non-empty lists. Moreover, Coq provides program environment for managing proof obligations, and that helps to work with subset types and makes writing programs in Coq using subset types convenient. Moreover, it's convenient for extraction as well, because the second component is a proof, and proofs are erased by the extraction procedure. So let us consider a simple smart contract, which we will counter, and as I said, it's just an ordinary function in Coq, and in this case, this function takes a user-defined message type, which is increment or decrement, and a storage or the state of a contract is just modeled as an integer number. And the goal of this contract is to react on increment and decrement messages and update return new storage. So to implement the main functionality, we implement two functions, inccounter and deccounter. Let us consider how inccounter function works. So we use subset types to encode invariants. In this particular case, we say only positive increments are accepted. Moreover, the return type is also a subset type that ensures that new storage, the updated storage, is indeed greater than the old storage. And we can use, again, we use program environment here, and we can use inc parameter as it was just a value, and program environment will insert constructors of the subset type and projections if necessary, and also will show us proof obligations in case it cannot prove them automatically. That can be resolved using tactics. In order to call inccounter function from the entry point, which is our counter function, we need to perform data validation. That's what we do here, and then after validation we use the results to construct the proof. In this case, the proofs would be necessary in order to call encounter function. Here's the result of extracting this counter contract to liquidity. And the signature of the contract, the entry point, extracts with no surprises. Basically, type of messages becomes a variant type with two constructors, and storage becomes an alias now to an integer type of integers. The interesting thing happens here, so the logical bits corresponding to proofs are erased, and the signature, the sig type becomes just a wrapper around the value. Let us jump to a next use case, specifically extraction to Elm and example web application. So Elm is a general purpose functional language that is mostly used for web programming. It is based on Hindu type system, and it's actually a very nice extraction target because many features that are usually found in functional languages are present in Elm. And our intermediate representation, lambda box t, is very close to the constructs available in Elm. But it still lacks ability to convince a type checker that the code is safe. So for us, we are able to identify that if one writes programs in Prenix polymorphic fragment with subset types, that it leads to well-typed Elm code. But we can actually go further if we use our pre-processing step in the pipeline to inline the specialized definitions. Then we can handle higher kinded types. For example, we can use monads, and then after unfolding, it will still result in well-typed Elm code. So let us consider an example web application which is inspired by the Elm guide, and so it can be found also online. Basically, it's an input form with the user and password, and it stores list of users after performing some validation. It stores the list of users on the client side. So we define the logic of the app in Coq and use dependent types to encode some model invariants. That's how our the model for our web application is defined. First of all, we define type of stored entries, which consist of a name and a password, and afterwards we define what does it mean for the entry to be valid. And a valid entry is an entry with a non-empty username and a password which is longer than 8 characters. Then the model is a list of users such that each user is represented by valid entry. Moreover, this list does not allow duplication of usernames. The model also contains a list of errors that we populate after performing the validation step, and it contains a current entry. So the entry type is not given here, but you can imagine it as is raw user input, which we have not validated yet. User valid entries has an advantage that whenever you write a function on these entries, you know that you will have to preserve the model invariants, so you never break the validity of them. And since you always work with entries which already carry proof of validity, you don't need to for extra validation in any other part of your web application. Moreover, at the entry point, since you need to, in order to populate data to the model, you need to construct a valid entry. At the entry point, it forces you to construct the proofs, meaning it forces you to think about validation and basically follow the constraints that you specified in types for a model. And the nice thing about this user list, basically, if you go back to the previous slide, so the users are list of valid entries with no duplication. That basically forces us to store only valid entries as a state of our application. So in the course of the development, we use again program environment for convenient programming with subset types, and we also use monads, and after unfolding the definitions, it results in well-typed Elm code. Therefore, we verify application logic, extract code, then append the views. And the views, it's basically the code that is responsible for rendering HTML, and it contains calls to the entry point of our model. The example is available in Ellie, which is an online IDE for Elm, and you can find the link in the abstract. There are possibilities for interesting extensions to this work, and thanks to the reviewers for asking these questions. We actually can go a little bit beyond verifying just a model. We would be interesting to verify how the interaction part works. Basically, so the views, they call methods, updates methods of our model, and we can model this. We can create a model of Elm runtime in Cog and verify properties of interaction between the view and model. And this model is actually quite similar to something we already developed for smart contracts as part of the Consort framework. And I think with maybe some tweaks, it would be possible to adapt it to web application verification for Elm. And to conclude, we presented a pipeline for extracting programs from Cog to functional programming languages. And the pipeline is implemented completely in Cog, allowing for verification of various parts of the pipeline. And currently, the most crucial parts of the pipeline are verified. Moreover, the pipeline offers the possibility of extending the pre- and post-processing steps with new user-defined transformations. We also showed examples of applications of the pipeline to smart contracts and web programming. The main takeaway of this talk is that one can use the Cog proof assistant and our extraction to bring the power of dependent types to your favorite functional language. So basically it just boils down to adding a pretty printer to your language at the very end of our pipeline. Thank you for your attention, and our development is available open source on GitHub as a part of a Consort framework, and please go ahead and add new target languages. And I'll be happy to answer your questions.
Okay, thank you very much. And Daniel is here to answer your questions, should you have any. So please enter any questions into the Q&A tab. I guess I had a starter question about what's the experience like if you stray outside the subset that's translatable? Does it give you an error in terms of your original program or in terms of some post-processed or pre-processed program?
We had originally, so our first approximation was to catch the untranslatable types during the erasure phase, this type erasure procedure reported as an error. But at some point we decided to follow the same approach as Pierre-Letouze. Basically, we just have a special term we emit because we can deal with it used during the optimization phase to actually produce some well-typed code. So currently, this is works like this. So you basically do your best effort yourself to unfold the definitions that might be problematic from the typing point of view in the target language. And well, if you don't succeed, you will get an angry error message from the compiler of the target. So currently, that's how it works. How it can be resolved, one can add an additional translation step, right? For example, if you extract to Elm, Then you formalize the Elm type system, right? And then you identify the subset of Coq that sort of matches it directly.
So how extensive are the translations you can do? So if I had a monomorphic ML, if that makes any sense, can you fully monomorphize the source program?
Potentially, yes. So currently what we have is quite simple thing that, so basically we just do inlining and a bit of specialization. So we have some heuristics how to specialize code, but not too much. But I think monomorphizing functions, I think won't be problematic. It can be expressed as a pre-processing step that preserves convertibility. So basically you will get a terms. Well, you just substitute types, basically push them to the leaves, and that should work fine. So I think adding a function monomorphization step won't cause any problems. But monomorphizing data types, that would be problematic because you need to generate new types. I mean, providing proofs that you still get the same program is a little bit problematic. But we were looking at it. It's a very good question. I think so it's extensible to the point that everything that is convertible after your transformation can be easily added to a pre-processing step, and you will get proofs of convertibility by automatically.
So by converter, you mean Coq's definitional equality?
Yes, so definitional equality of Coq. Yeah, so.
Okay, so that's easy, but doing something that requires a proof is.
Yeah, if something goes a little bit further, then you will have to either modify your procedure that generates the proofs, or provide maybe a special case for your particular transformation.
Mm-hmm. Is there any support? So the point here seems to be partly generating code which fits into the target language's ideas, but also generating human-readable code. Is that a goal? And if so, do you translate things like comments and documentation and things like that? Is that possible with MetaCoq?
Right. So currently, the kernel. So the MetaCoq supports only like kernel syntax. Yeah. I think by that time all the comments and they are gone. So I don't think you can retain this. But it probably could be. I mean, we also collaborate with MetaCoq people, right? So I think this also could be added, right? So as a collaborative effort. But currently, so it's very small Coq kernel, and so basically it contains only terms.
Okay, I don't have any more questions. I think I guess I suppose one kind of question is, in general, what's the correctness criterion? There's complex ones like full abstraction kind of for compiler correctness. I guess that's quite hard here to specify without a full model of the target language.
Yes, exactly. So this is very important problem. So for example, with Elm, it looks like, at least like informally, right? It's less problematic because if you look at the this Pickwick representation or kernel representation, it's very closely matches to what Elm has, the constructions in Elm. But of course, there are some non-trivial things, like for example, crazy shadowing rules in Elm. So you have to, generate names of variables, and they can't shadow anything. So you have to be very, very fresh. So right. This is different from Coq. So there are many subtleties. So even in this case, the next step, and I think it's just pluggable to what we have from this lambda box T representation. Right, so you define a separate translation step to your target language semantics. It could be formalized separately, and then you provide a proof, and then you just hopefully like plug it in, and then you get a whole pipeline. So we also hope that maybe someone will be interested to take a concrete language. You go all the way to producing the
because I was thinking a target language that has exceptions and so on, then passing in higher order functions gets tricky.
But maybe if you have exceptions in targets, you just never use them, and because you can need a code in subset, right? I mean, I think having a lot of features in targets is not much of a problem because you're not embedding it. But true. So we use exceptions kind of to represent inaccessible branches, for example, right? So given by the false lim. So they kind of use this informally, some kind of side effects, or we use like loop forever in Elm because there are no exceptions. So yeah, so of course that could be also modeled more fairly, right, giving even more guarantees. But we hope that so this pipeline is like admits some plugging in formalizations, so that just will improve the results.
Okay.
In terms of guarantees.
Okay, well, thank you very much. And I believe that's
Thank
the
you.
end of this session. So another round of applause. More floating hands. And this is the end of this session of ML. Now it's, well, lunchtime, I guess, half an hour, at least here. And the next thing will be the invited talk by Don Syme in about half an hour. I don't know if Jonathan wants to make any other announcements.
No other announcement. That's great and exactly what's lined up. Please come back in 30 minutes for Don's keynote. I'm going to hit the break button on the session. Thanks, Bob, for chairing. That was great.
Thank you.
So close my Slack. Close that.
How come you're using Slack? Okay, we're live and everyone can hear us now.
Lovely.
All right. Okay, well, let's wait a couple more minutes since I think because I clicked resume late, people are starting to join only now.
Got it.
Yeah. Oh wait, why is Daniel still on the stage? Okay. All right, Daniel. Yeah, so I'll do the Q&A at the end, and I'll just select questions from the Q&A and show them on screen, and you can like answer them, and hopefully we can hit the 90-minute bar, and Sam Lindley will be very happy once we get to 90 minutes.
Yeah.
All right, I think it's getting pretty filled up. Hi, everyone. It is my great pleasure to welcome Don Syme for the keynote for this year's ML workshop. Don is well known for F#, the design implementation of F#, but also the stewardship of the community at fsharp.org and creating really momentum and bringing functional programming to a community that normally would not be aware of functional programming. So I'm particularly excited that this year we're fulfilling the premise of the ML Family Workshop, which is to welcome members of the entire family. And now I will leave the floor to Don to tell us about the history of F#. I was looking at the Wikipedia page, and it's been, what, 16 years since the first version? Time flies, doesn't it?
Since version 0.1, I think that's about
yeah.
That is about right. Yep.
All right, the floor is yours.
All right. Thank you very much, everyone, for coming along. And thank you, Jonathan, for the introduction and for the invitation. And just looking at who's here. Oh, we got Claudio. Hello, Claudio. Looking at all the various people. Andrei Felinsky is here. We have Joseph and Didier, and waving to you all in the audience. Sam, I know some of you I've never met, but there are Adam, good to see you from Google Research. Great to have you along as well. And yeah, I wish we could all be together in person another time, but it's also kind of convenient to be able to do this online in this kind of format, and I'm really am enjoying it as well. So thank you for the invitation to give a keynote or here, invited talk, I guess, is so I recently got the opportunity to write a history paper on F# for the HOPL for History of Programming Languages conference. And HOPL is only run every 10 years or so. So it's the sort of thing you put a lot of effort into trying to write the paper. And when I was asked to give an invited talk here at the workshop, I thought, well, I'd actually better talk about the things coming out of that paper because it's so relevant to the ML family of languages and the various research that's come out of that. there are plenty of much more technical talks I would have loved to have given. I was thinking just, in the last half hour, I was thinking I would love to just give a sort of deep dive on the inference procedures used in F# as they have evolved over time and why certain technical decisions were made, and also sort of, that would be the sort of more normal thing perhaps to be giving as a technical paper. So this talk is nothing like that. This is not a technical talk. It's a much more soft history talk in many ways. And so it's also kind of from a personal perspective, from one angle on the ML family of languages. There are other angles. I mean, Xavier gave a talk yesterday, which I didn't see, unfortunately, but on the last 25 years of OCaml that is highly related and intertwined. Then there are also talks on the history of standard ML, and also history of Haskell, and also there are other relevant talks from across this spectrum. I think all the Hopl talks from this iteration of Hopl are available, and the papers are also available. They're all recorded and all available. Just look them up on Google. Okay, so it's a meta talk about a meta language, maybe even meta talk about a meta paper of a meta language. And it's loosely based on the Hopl 4 paper, and it kind of, in the way the paper I wrote was kind of constructed. It kind of takes an arc from the 1970s through to today, and mentally, now that very conveniently kind of fits into my lifetime. So there are always reasons for kind of choosing these kind of things. The 1970s are real to me. I was alive then, and the 1960s are in the far distant past. And so, starting around the 1974 is a very convenient thing for me. And I kind of think of it as starting from three guys get together. They are all guys, Milner, New, and Morris, Lockwood Morris, and Malcolm New, and Robin Milner, and start making a programming language. And here we are today, after this amount of time. Now, history is always written extremely selectively and with a purpose, with choosing various narratives for particular reasons. There were reasons why I did that in the fsharp.org paper. It's nice to be kind of just explicit about that. And I think I've covered the narratives. They may be narratives I've kind of forgotten to do. One is, these things are a personal journey. You stick with these technologies. You get involved in these technologies for, well, whatever reason. Accident is the main part of it. I was at a university in Australia, and I had a supervisor called Malcolm Newey, who was one of the people who was one of the founders, first three people to create the ML family, the very first version of ML. And so I wouldn't be involved in that probably if I hadn't had that kind of personal interaction. And I think we all of us who've kind of been involved with this would have a similar kind of aspects to our kind of stories. But there's also a need for communities, highly technical communities, to have their own origin mythology, their own journey, their own perspective on time about where a language has come from, or what is it for, what's its kind of journey into the future. And so when one is writing a kind of history, one also has an eye on the fact that it's a history serves a purpose to motivate us about the future. Another theme that kind of comes out in the paper is that even in programming languages, things don't just happen. It's not just a technical or mathematical discipline. Even mathematics is things don't just happen. Things in some sense happen to people, to communities, and they act and they react and they change or reject or other things in kind of very human kind of ways. And there can be some element of creation in that. There can be rejection. There can be a sort of denial, a stubbornness, cooperation, subversion, there can be a lot of opportunism in some kind of aspects. And these things are certainly real in the way kind of technical developments happen even in our kind of field. And perhaps we're not necessarily that explicit about that, but it's certainly, when you look back over time, you can see these things kind of coming out. So another theme, a narrative, is this question, sort of, and it's this recurring narrative. What happens when computing traditions with very strong belief systems, and by that I'm meaning things like the functional programming community, those who with belief in mathematics and theory, for example, collide with other traditions, sort of more the system, the being. I'll get to this a bit more later, but when you're at a place like Microsoft Research, you're very aware that there are very different traditions kind of coming into the same space. For instance, the systems tradition, where in a sense, the system that you're creating, the machine, these days, say maybe a cloud data center, that is the object of focus, and its performance and its systems characteristics are the kind of the center of the belief system of the people who are involved in that part of the industry. And there's quite a collision that happens when people who turn up who say, hey, I want soundness. I want things to be formally correct or something. These kind of traditions collide. And that can happen in industry, and it can happen in academia, it can happen just on the web these days as people are having a conversation. And I think perhaps in educating people in computing, we could be a bit more explicit about the different themes and the different traditions, because our students, I mean, I'm not an actual university lecturer, but when I think of the sort of things that maybe I would have liked to have been taught is like, there are very different perspectives on computing all coming into the same kind of spaces today. Another theme is, it's a similar thing about what's the interplay between academic research and industry concerns in computing history, and how it plays out in programming languages. And F# is just an example of that. There are many other examples of that coming out both in this talk and more broadly. Now, more closely to home in the history of the ML family languages, there are actually a lot of, when you look back in the history of the ML family of languages, there's actually a lot of contradictions built in right from the very start of the history of ML as a thing, as an idea, as an effort. And there's a question of how one resolves and sort of makes progress from contradictions, sort of the dialectic that kind of happens in that. And I just want to draw out some of those things and how they played out in F# from my experience. And perhaps most beautifully, I think, or the most important thing for me, and I talked about this right from the start of the paper, is there are these remarkable things that have sort of held true in programming language design, or in what stands the test of time, what is the golden thread, and it's really quite remarkable to me that the core experience of programming in say Elm, or programming in OCaml, or programming in F# is actually in some ways very similar to what was being envisaged by the people who founded the first, who created the first thing we call ML. And when you consider how much change there has been in the computing industry over that time, it's really kind of remarkable a thing. And it's always a thing I come back to is, what's that core experience we're trying to deliver and support and make practical. Okay, so talking about contradictions at the heart of the ML family of languages, we're here at the ML workshop, and a lot of the papers, of course, about theory and about soundness, and that's a huge part of the history of the ML family of languages, applying logical techniques, formal techniques into the programming language design kind of space. But that's not how ML started. It may have been started by extremely theoretically minded people, but this paper is actually, there's a lot, which is a short note written by Robin Milner in 1982, looking back to the start of ML around 1974. And it's this thing that ML was for a more or less specific task. That is, ML was created for a purpose. ML was right from the start a practical language for getting stuff done. And there's quite a few comments all the way through this that kind of capture that. For instance, the section on lazy evaluation, it says, yeah, we decided this for no other reason than our inability to see the consequences of lazy evaluation for debugging. Okay, there's right at the start is utterly pragmatic concerns built into the heart of the ML, the very first version of ML. And he says, remember, we wanted the language which we could use rather than research into. Their initial concern was not to create a site for research at all. Okay, their initial concern was to support their own productivity, their own programming. And they made various decisions, various compromises through that process. And we'll talk about a couple of, we'll get back to these a little bit later on, but you can see that right from the very start, these questions of purity versus practicality, logic versus pragmatism, you know, they come to the fore, and they're quite willing to say practicality and pragmatism trump purity and logic. And you know, that is there at the start. Now, there is this incredible kind of thing that happens at the start of ML. And one of the reasons, I think that the thing about ML is it kind of serves to unify a set of interests during the 1970s and early 1980s of people who loved purity and loved logic, loved kind of formalism, loved well-constructed ideas, mathematically formulatable ideas, and it kind of served to unify them into a tribe of people, and that tribe creates things like Standard ML. It creates things like Edinburgh ML. It probably gets a lot of research grants for various kind of activities during the 1980s. It also allows a group of people to come together to say to the American research funders, hey, we've got this thing which is, you know, we believe is beautiful. Here's a collection of researchers who will all agree with each other that this is worth doing, and then Standard ML gets created and so on. But one of the reasons why it's able to unify is because it's this coincidence of pragmatism and purity and logic. It's these two things kind of come together into a quite sort of, some people say it's a kind of local maximum, or a kind of just a point with a particular utility, and that's enough to kind of draw a whole crowd of people together. Now, if we roll forward to the 1997, the agenda wasn't actually that successful during the late 80s and early 90s, and we'll get into more about why. But in 1997, various people involved in functional programming right across the spectrum began to be honest about where they were at. And that is that no one was using, relatively speaking, no one was using their languages, and they start to be honest about why. And I had been one of the people using these languages during the 1990s, and as many of the people at this workshop, us older people here, and I was part of the tribe of people who were using these languages, but and I was experiencing them as being extremely productive. You know, just, you know, when I was using OCaml in the 1996, 97, when I was using Moscow ML around this time, they're just immensely productive systems. And I couldn't, as an individual researcher doing a PhD and other work, I couldn't imagine not programming in this kind of system. It's just quite unbelievable how low productivity these solutions like C++ or other things that people were using actually kind of were. So it was always a bit of a shock that no one was using these languages, relatively speaking. And if you want to go back in time and take a good look at this paper about Phil's sort of impressions as to why that was true, it had a huge influence on the development of F#, and it's worth going back for any researcher, any PL researcher who aspires to make something that gets widely used. It's worth going back and taking a read of this paper and having a good long think about what it actually means to make something usable by a broad enough range of people in practice. I do love that paper. Okay, so but things have changed. Just to say, you know, we roll forward to today, and certainly typed functional techniques are used absolutely everywhere. There's, in some sense, ML owns the world in a sense, in that all these languages are trying to reach something that we kind of, this combination of types and generics and immutable data being much more prominent, and transformation, the programming centering on transformations of immutable data. These map, filter, reduce up there, real Python in the top right hand corner. This stuff is absolutely everywhere, totally normal part of the programming language spectrum today. So we have won in a very real sense of that. Also, strongly typed languages are everywhere. Just putting a few of them up. Strongly typed functional programming languages. Whether you call TypeScript a strongly typed functional programming language or not, I don't mind. Certainly, JavaScript is a functional language in many ways, and TypeScript is a sort of the strongest typed version of that. Also, Reason. We've also got the F# and OCamls and Swift and so on. So this is absolutely these languages are immensely practical, completely different space to where we were in 1997. So if we roll back to the 1980s and 1990s, let's just unwrap a little bit about what happened in the 80s and 90s, and who were these people, who were the functional programming tribe. And I've just shown some of the history. We've got Robin Milner, people like Larry Paulson developing Isabelle. It's strongly intertwined with the history of these theorem proving systems right from the start of LCF with Robin Milner. So then there's these semi-commercial implementations of things like standard ML that then get used in systems like Isabelle. And even today we've seen several talks interacting about the interaction between Coq and OCaml. And so there are also other pragmatic languages like Clean, and of course the development of the Glasgow Haskell compiler, less intertwined, kind of managed to separate off away from the theorem proving kind of world, and took in a role more on the kind of parallel programming role initially. But this was the kind of the world as it was, the relatively small world of strongly typed functional programming. And then something happens in 1986 to 1998. And this thing, which I've just used this stock graphic of a tsunami, which is not real, just computer generated, but it is this object-oriented tidal wave hits the world around in 1986 to 1998. Depending on when you start this kind of process, it was sort of exponential kind of thing, really. You can kind of start in 1986, 87 with his first OOPSLA conference and this sort of small talk, and also then Objective-C, which is not a language we talk about much in academia, but it had a huge impact across Silicon Valley in Apple's kind of rise to prominence. And then in Microsoft academia, and then it comes along. So the thing is, what happens when you get hit by a tidal wave? Okay, and I think it's generally true that the functional programming tribe and the researchers who at the time who had seen their languages as being the future at that point during the late 80s and early 90s, they kind of knew their ideas were good enough to be the future of where programming languages headed. But they get hit by this thing, which completely wipes them out in many ways. And there are various reactions to what you do when you get hit by a tidal wave. So one reaction is just to give up. Okay, you actually stop believing, in some sense, in functional programming. There are plenty of people, for instance, who maybe stop believing in formal verification. They do a PhD in formal verification, and later on they decide maybe that doesn't work. So you just find something else to do and something else to believe in, and that's a perfectly reasonable kind of approach. Just because you start working in an area doesn't mean you have to kind of. It's only technical work after all. You don't have to believe in it forever. So another approach is to kind of reject, and this can be a very, very good approach sometimes, retreating to the fort, focusing on foundations, focusing, for instance, on pure and functional, focusing on various calculi. You might go and invent some new calculi, and in a way, Robin Milner does that. He doesn't actually continue to push ML that hard. In a way, he kind of during the late 90s, he kind of says, actually, we're going to do the pi calculus. We're going to look at some really, communicating mobile systems. We're going to look at foundations for those. You might go back and create theories and logics of objects. Yes, you might. So there were many people who also, you can kind of look at Haskell itself as kind of a retreat to the fort and focus on sort of pure and functional, the Agdas of the world and many other systems continue to push along this kind of line, and that is totally fine. There's a lot of amazing research has been done, and it allows people to be quite self-defining and not just to focus along certain dimensions of work. So another approach is to say, hey, I'm not that interested in functional programming anyway, or there's this very pure thing which is functional in theory, and I love that, and I'm going to let there be a pure world, and I'm going to let there be a dirty world. There's going to be a world of God and a world of the devil, in a way. And the world of the pure world is where we prove things, and the ugly world is what we prove things about. Okay, we might be verifying C++ code or device drivers, for example. So we're going to accept that the world is constructed in really horrible and bug-ridden kind of ways, full of null pointer errors or whatever else. And we're going to spend our time using theory and functional programming to actually verify this stuff. That's obviously got a long history because of the association with functional programming with these theorem-proving systems. And I've just got some examples of how this plays out with people I personally knew. There are many, many examples across the PL landscape of taking this kind of approach. Another approach is this one, where you say, oh yeah, right, it's great. I love Java. I don't like Java, but I like the JVM. Okay, I like the idea of there being this standard industry standard virtual machine. That's something I can get my head around. Let's get my favorite language and go and run it on those object VMs, usually with a lot of skepticism about the nature of those object VMs. Okay, so just using them as a kind of runtime target. Again, kind of saying we have this pure world, which is our language, and we have those object VMs as well. It's a means to an end to get stuff to happen. So some examples, Claudio, I saw in the audience, worked on the SML.NET compiler, which is very much in this mind. We also thought, so we got involved in doing quite a lot of this work at Microsoft Research through something called Project 7, which is talked about in the paper a bit more. There are many, many examples of this. I've called out MLJ as an early example in the 96, 97 kind of time frame, to take standard ML and get it running on the Java bytecode. It seemed crazy at the time in a way. And that was in the days when the Java was all about delivering stuff into the browser, which obviously got de-emphasized later on. And so the idea of bringing this on more pure, cleaner languages, you can see the attraction of, so if we're going to write applets, we may as well write them in something like standard ML. Okay, another approach is kind of the rational deconstruction of pulling things apart bit by bit, and to say, and I'll get onto this more later because it's strongly used in F#, is to try and rationally deconstruct functional and object programming and say, well, what is functional programming anyway? Is it just lambdas, okay? Or is it type classes? Or is it functors, or is it, what are the primitive calculi we're kind of using, but also what are the actual language constructs? Does it include pattern matching or not? Does it include discriminated units, etc.? And also to rationally deconstruct object-oriented programming, and so we've got this thing called this tidal wave that's hit us. But what are they trying to do? They're trying to do existential, so they're trying to do sort of nominal typing or structural typing, and we can maybe do that better if we just pull it apart in the right kind of ways. And part of that agenda is to try and seek a synthesis between two worlds. Instead of keeping the worlds separate, like I was saying, you might try and let your worlds merge. And one approach is to make functional languages more object-oriented. And there are many examples of that. Dylan is a bit of an example, not strongly typed. OCaml and Haskell or F#, but there's actually many more. But they're still starting with what we would recognize as a functional programming, strongly typed functional programming language, and then seeking to add sort of objects to that. The other approach is to go for the object-oriented languages and to kind of integrate more functional language techniques. And so one very important part of the history is a thing called PIZZA, which was done by Odersky and Wadler in 1997. So you can see the dates. Yeah, the object-oriented tidal wave hits around 1993, and then it takes around 4 years for people to kind of really digest that and kind of synthesize that and then come up with a response to that. Okay, they get over their denial phases and they kind of say, okay, right, we will think about what we're going to kind of do. And they add things like generics. But it's interesting, they're still using the language of the functional programming community, parametric polymorphism. But what they actually mean is generics, which is, and then you see they add these other things, algebraic data types. Again, they don't even say unions, they just say algebraic data types, etc. Okay, they seek a synthesis. Okay, lots of other examples of that through the history. Scala, it derives from its efforts, from this kind of effort. Absolutely. You can see it in Java, C# and C++ more recently. Things like C omega are also part of the kind of history that was fairly close to from my perspective. Okay, meanwhile, so that's the world of these object-oriented tidal wave and the academic, this small tribe of strongly typed functional programming kind of people. Meanwhile, in that bit of history, we had, there was Microsoft and there was Netscape, and then Java came along, and then there were lots of lawsuits. And so Microsoft itself, one of the monopoly companies in the industry, is getting wiped out or hit very hard by this object-oriented tidal wave. It also, these things don't just play out amongst academic communities, but actually Microsoft was also kind of having to deal with this in its own way, and it did its, and part of its resolution of that thing was to create Microsoft.NET. And it also created Microsoft Research, and Microsoft heads to Cambridge. So let's talk about that. So Microsoft Research is founded in Cambridge, and one way to look at it is all the tribes of computer science. I mean, 500 or 800 people are employed by Microsoft, and they're top-level computer scientists and entry-level people like me coming out of university and so on. And in a way, I look at this as kind of the worlds of Robin Milner, that tribe, and the industry concerns of Bill Gates collide full on. There are many other collisions are happening as well, but this is one particular collision, and it coincides with the start of the .NET effort at Microsoft. And so what do we do? Well, we play various versions of that game, those responses that I described before. One of the things we did is to put generics, parametric polymorphism, right into the heart of the strongly typed intermediary language, which is the .NET IL. And in a way, I think this, from my perspective, we were kind of breaking through the nominal class-based this dominant ideology that everything had to be an object, and there was no other way of looking at how to model how to model information except inheritance, class-based inheritance, all completely nominal. And so to bring in parametric polymorphism into the core of the system and get it into C#, to get it into even Visual Basic has this, and provides a really strong foundation at the core. And at the time we said it puts .NET 20 years ahead. And I stand by that because Go, for instance, is still absolutely struggling with generics today, what to do with generics. And in the end, the system we have in .NET and Java still don't have it in the JVM, and it really makes a difference from many usability perspectives, performance perspectives. This was the sort of thing we wrote at the time. We were kind of saying, hey, there was this thing called COMPLUS. Well, it doesn't matter what that was. One of the early names. Okay, sorry, just checking. My connection may be interrupted. We'll see. And we said, get serious about language innovation.
We can't see screen sharing anymore, I'm afraid.
Let me re-share my screen then. Got it. Thank you for letting me know. Are we back on
now?
Okay, great.
Yeah.
Right, so we are here getting serious about language innovation, and we're kind of pushing on the industry buttons that they were only going to be able to compete with C# and to make it a kind of strongly technically compelling language if they actually innovated with it and got ahead of the game. So we were kind of pushing Microsoft's buttons that it hadn't done enough innovation in the past, that it was time to actually do this properly. So we landed .NET Generics, but then from our perspective, when I say our, I mean the joint researchers at Microsoft Research in Cambridge, it still wasn't what we wanted. It was still too verbose. It was kind of unusable, in some sense untrustworthy, if you consider just null pointers absolutely everywhere. And there's still this open kind of question about, well, what to do about this? I mean, sample after sample just kept showing this. Just we started doing early prototypes of I did of things like F#, and you just get these code size reductions of like for like code, and the C# code being full of null checking and the like, and it's just not where we wanted programming to be. So a later example of that I like to use, it was written up by a guy called Simon Cousins. It's from an application in the UK energy industry, just to show we're not making this stuff up. I'm rolling forward a few years here, and he wrote a blog post called "Does the language you use make a difference?" And he did a couple of versions of that. I think you can, that particular website link at the bottom is no longer available, but if you go to the fsharp.org history paper, you can find the links to the archive versions of these blog posts. And in this kind of world, the C#, people using C# 2.0, 3.0, compared to people using F# for pretty much the same kind of problem. And you can just see the kind of line count differences here, 56,000 lines of braces or 3,000 null checks and so on. So at the time, I was using a lot of OCaml. It's by far the best practical language at the time. And F# 1 was kind of born from this obsessive, perhaps overly obsessive, I'm not sure, desire to make sure that I personally would have a language I wanted to use, and that sort of strongly typed functional programming in the OCaml or the CamelLite tradition. CamelLite was always my mental starting point, not the O in OCaml, even though I'd actually been using OCaml. And to make sure that was a viable option into the 21st century. Okay, so this was the sort of slides we presented around Microsoft, binding us, just kind of saying, yeah, it's nice and simple. For that to do all these different things, and you get nice type inference with a sort of just as safe as C#, actually safer than C#, with the succinctness of a scripting language. Mentally, I was thinking of there being this beautiful racing car called OCaml, French and sleek and kind of wonderfully constructed, and saying, yeah, let's keep as many of those qualities as we can, but we're going to run it with an industrial grade truck engine called .NET. Now, actually, that's not my mental model these days, just to be clear. I'm just trying to capture how I was thinking at the time. I actually think the .NET runtime is a superb basis for a functional programming language. Certainly a great basis for F#. I don't have any complaints, almost no complaints about the .NET runtime. It just gives us so many wonderful practical things that we need. But just to say, that also captures a lot of my respect for OCaml as I was using it in around 2003, 2004. Okay, so the approach we took was starting with core OCaml. So try and stay true to the functional programming principles and try and make it always possible to whatever else we added for whatever purpose, you could always come back to core OCaml, which was the sort of core productivity experience of ML as it had been developed in the 1970s. So just to make sure that golden thread stays true for the using F#. So we used, we had a fair amount of CAML code that we could use to kind of pin down the core implementation. And we say, we want this stuff to always continue to run because it's a great way to program. And that we know for sure. And whatever else we do on top, we make sure that core productivity experience is always maintained. And then we interoperate, we reuse this VM and ecosystem. This actually means that F# kind of has this exosystem in a way, that it kind of lives inside the .NET ecosystem, or at least initially does, and now also in the JavaScript ecosystem. And so that is interoperability is a major concern for the language right from the word go. Okay, we deconstruct object orientation when we find a synthesis. We learn from C#, and we, in the sense that we say we're going to put in IDE tooling, developer tooling, right from the start. We're going to have a REPL from the start, but above all, the language is going to pretty much assume that you've got a richly tooled development environment, which is now kind of standard. And we deliver it, we apply it in industry. Microsoft and Microsoft Research will act as kind of a long-term home for the thing. And then we iterate and we improve. And that's been pretty much the approach all the way through. So if you kind of think, well, what does that mean in practice? If our starting point is core OCaml, or core CAML Lite, or the core of the ML programming language, then what directions kind of can we go? We don't automatically assume anything. We're not starting with standard ML, like say SML.NET started with. We're kind of just reducing down to this expression-oriented core that we know is productive. And then we kind of look in various directions. And now there are, in the history of the ML languages, there's been a tendency to go in some directions more than others, okay? So for instance, there's been, in the 1980s, there was a tendency to go towards formalization in creating the formal definition of standard ML. So, but there are 6 or 7 or 8 or 9 different dimensions to programming languages in a way, and you can kind of move along those dimensions or explore in different dimensions. And so I've tried to brought out 6 of them here. So, and what do we do in these different dimensions? So if we just think about, parameterization, well, of course we have functional abstraction and parameterization for the lambda, right? But do we kind of venture into this functors, parameterized large components? And no, we don't do that. And I've got lots of answers written up on the web about why functors aren't in scope for F#, or why they don't seem to find the utility that they might find, or also some skepticism about their sort of utility, even if they're theoretical, foundations I fully kind of appreciate and love. So that's kind of one space. In the kind of, we obviously start with this core immutable data by default, algebraic data, but we actually do embrace kind of functional objects as a way to kind of get enough encapsulation, and we're also getting some interoperability from this kind of space. We go in the direction of nominal objects, some of it driven by interoperability concerns, some of it by outright just access. So a great way to get existentials in the language. But we don't go into the kind of structural objects kind of space. We've got a little bit more like that in recent versions, but initially we through a thing called anonymous records, but we don't do that by default. On soundness, okay, initial focus. We want initialization soundness. The let keyword is trustworthy, right? That there are no nulls. You know that if it says let x equals y plus 1, then x has a value everywhere in its scope and it's well initialized. There's this kind of, in the functional tradition, there's this kind of, along this dimension, you get sort of more and more extreme, which is sort of soundness is supreme, sort of the idea that if there's one unsoundness in your system, then the whole world kind of collapses. And from a logical perspective, that's true, but it's not true in the pragmatics of programming. And then there's an even more extreme, which is that languages sort of don't exist unless they have a formal specification. They have no reality, sort of mathematical reality, or they're just nonsense. And that's not the approach we take in F#. It's a kind of fine, kind of extreme position, and I appreciate why people have that, but it's not where we were. So let's put that in that kind of grayish kind of color. On types and type inference, we start with types. What are types for? And this goes to the heart of things like .NET and Java. Types are for modeling, for domain modeling. Types are for performance. Types are for correctness. Types are for interoperability. So that thing that types become for interoperability between languages is the fact that we incorporate that into F# means a lot of other things change about types. We have to kind of accept what we get for interoperability with regard to our view of types, but it means maybe we can't use types for the purposes that other people might use them. We want to keep Hindley-Milner, and this is a major design decision in F#, because we want that core ML experience, which involved Hindley-Milner type inference. We absolutely kind of want to keep that, and Scala doesn't keep that. In fact, almost no other languages. Elm does, but very few other pragmatic languages that attempt to combine with object programming kind of keep Hindley-Milner, and we modify it for objects. When you're not using objects, you still get Hindley-Milner, but when you do use objects, things kind of change a little bit. You need more type annotations. We also add things like types for fast generic in math, but we don't go towards type classes and that kind of parameterization and type level computations. Types for logic and proof, that's out of scope for F#, so we kind of limit our exploration along that dimension. Now, there's another dimension I'll get back to more on computational modalities, and that's things like list comprehensions, monadic notation in a language, or more generally, you might have queries, async, monads, monoids, applicatives, and compositional computation notation. That is an area we do push quite a long way on in F#, and a lot of that is covered in the history paper. There's a section on the kind of history of that. I'll get to that a bit more as well. So on interop, we did take a radical design decision that F# types are .NET types, .NET types are F# types, and especially for the early versions, we've modified that a bit to have a richer system in F# which reduces to .NET types. And we also took this view on type providers and sort of metaprogramming for which I'll just mention a bit later on as well. Okay, so you take the parts off here in gray, and that's sort of more or less the exploration of where F# kind of lands in each of these dimensions. Okay, so along the way, there are reasons why we made some of those decisions, and that involves facing some of these kind of contradictions that are built into the strongly typed functional programming tribe. And I gave that these sort of contradictions: purity, practicality, logic, pragmatism, and this idea that as you have contradictions between an idea and its kind of opposite, or it's what seems to be its opposite, you kind of do this Hegelian dialectic thing and say, well, let's try and find a synthesis. Let's try and find a way forward out of this set of contradictions. And I like this approach. It's obviously, philosophically a very strong approach in the 1800s. And I think it's an important sort of the foundation of how we do research in this kind of area. So one of the contradictions was to do with objects. And if you go back to that paper, even in 1982, Robin Milner is completely aware that they don't have notions of encapsulation or abstract types really built into these versions of ML very well. That applies to both pattern matching and also just objects in general. And in my point of view is that practical type languages need to have cheap and effective type declarations for encapsulation, and they may as well be called objects. Previous MLs had awkward variants of that, abs type, and then the kind of module and functor system is pretty awkward for doing it's not what you call sort of cheap and cheerful for that. So we do put in object programming into F#. It's sort of modified Hillman-Milner type-directed name resolution, nominal, subtype, friendly, inference. It tries to be focused on delegation as much as possible and tries to be friendly with regards to expression-oriented programming. This is what object programming kind of looks like in F#, just in case you've never seen it. You have the type, you're still defining types, and you're still using let in the middle. You can have all the let of functions and whatever else you do. And then you publish an interface, you export an interface to the object with properties and methods along the way. So that's fine. So you get this ergonomic simplicity of encapsulation. Works very well with type inference all the way through. And things are still immutable by default. So you're not buying into the sort of the mutable state view of objects. So along the way, we kind of also deconstruct object-oriented programming. And this is kind of a list of all the sort of things that kind of are in OO as you get it in the world of .NET and Java. Or it's .NET, but it's more or less the same for Java. And so you pull it apart into all the different pieces and you kind of think, what do we want? What don't we want? And you more or less, you scratch your head for a very long time and you have a lot of arguments with people. And then you kind of, those things can be broken down into different areas. So some are just about making it a better language for writing and designing software components. And that's a major focus for .NET. Some are about making it a better language for implementing code. Some are about just participating in the interop standard, and some just are not needed at all. So more or less, we break it down into these, which is you embrace these ones in green. You use these blue ones kind of are in the language, but you try to use various techniques. Only use them where necessary, use them where tastefully, just sparingly. And then the red ones are like, yeah, they're in the language, but don't do them, right? You know, these are going down the rabbit hole. You can do these things by various ways, but you kind of strongly restrict that both culturally and kind of technically. And there's some things that are just completely not supported, like, you know, wildcard types or aspect-oriented programming. Okay. So yeah, so you love these. We encourage people to love a section of object programming, to tolerate some other aspects of it, avoid some, and then completely forget about a chunk of the rest. So part of that is that I really don't like the term object orientation. I actually want the industry to stop using the word object orientation and just start using the word object programming. And that is because object programming is good. You know, there's lots that's positive about it. Succinct coding, convenience, ergonomics, good naming, encapsulation, small composable abstractions, expression-oriented object implementations, delegation, closure, and above all, you're making relatively simple things out of potentially complex objects. You can wrap up a bunch of objects, encapsulate, and make something fairly simple. Whereas object orientation is just stifling, right? It's objects as a single dominant stifling paradigm. It's absolutely pointless waste of time on hierarchical classification, animal, cat, dog, abstract jelly bean factory. And you get these large cumbersome abstractions with many holes and many failure points based on declarations. And above all, you make complex things out of complex foundations. If you're using hierarchies and implementation inheritance, you can only make things more complex by inheriting from something. And so the F# approach is nowadays to embrace object programming and make it fit with that core ML programming, but absolutely not to embrace full object orientation, except maybe if you're in a project that is already using that technique. But that's where we land. Okay, and in a way, we're trying to get back to this sweet spot of programming. I do like this slide. It's quite challenging to people, which is that the sweet spot of programming is functions and data, or which from our perspective is functions and data plus just enough types to support the action of programming productively. And in this slide, it's kind of down the left is code complexity increasing. And you start with this kind of code of functions and data, and then you start going crazy about object-oriented programming. You're using abstractions, interfaces. I might need to change something later, and design patterns and so on. And then you come back to functions and data after you get enough experience not to do most of that stuff. And then you do the same thing all over again when you come along the functional kind of dimensions of applicatives or category theory and purity for absolutely everything, and returning exceptions as data for absolutely everything or something like that. And then after a while you come back and you land at the place of sort of functions and data. And that is always the kind of sweet spot that we're trying to choose, and we're just kind of subjugating objects into that notion of data. Objects are a perfectly fine notion of data for many purposes, and we can write functions, or we can write data, and some of that data is objects, and we have enough types to look after things. So another contradiction built into the ML family programming languages came in when pattern matching was added. And there's this big problem built into pattern matching, which was known fairly much straight away, which is that pattern matching over concrete representations is in practice a software engineering catastrophe. And it was a contradiction in all functional languages. And I think F# was one of the first to really address this problem in 2006. Scala was addressing it about the same time, and Haskell eventually does it with view patterns. But Robert Milner knew this, right? He says, if you read the thing at the top right, he says, ML does not adopt the clausal form of function definition, which is found convenient by Hope and Prolog. How can we possibly do this when we want this to not just imply primitive constructors, but the constructors of user-defined abstract types, that is objects in some sense, or that is abstraction. And and then he says, well, this was the versions of ML before they added pattern matching, and he knew it was wrong in some sense, it was wrong to add it without addressing this kind of problem, but they added it anyway. And F# has a way of addressing it, and in my eyes, it's a way of resolving that contradiction. There's another contradiction built into the entire world of functional languages, which is this idea that lambda is everything, lambda the ultimate. We all worship the lambda. I still do. We all do. And but lambda's not the ultimate, right? Because we use these computational modalities to extremely good effect all the time. And you might say, well, that's just lambda combining with monads or something. But we, if you need to digest this into your language design to kind of say, actually, we're going to embrace computational modalities, whether that's monads or applicatives or list comprehensions or queries or whatever else, and support those right from the start. And that might be tasks, various takes on DSLs and so on. And if you take these 5 different C# features, for example, C#'s going full on in embracing various computational modalities. It has query expressions. It has collection initialization. It has these async methods. It has iterator methods and async iterator methods and so on. In F#, they all become one kind of construct. It's a fairly sophisticated construct. It has to be to encapsulate all of these, but it's still just one thing with one set of rules and fairly natural rules, which is where you put a modality of some kind around some code, and then that, and so that's some examples. You might get seek plus a yield effect. You might get query plus a yield effect, or a list, or an async sequence, or a coroutine. Okay, so just some examples. So where you previously had code like this in OCaml, which is you're in the modality of generating lists, okay, you would instead use the F# thing for list here, and you would you'd then just use for loops, right, and if statements for your filters. So you just got a generator, and yield bangers for yielding many things. And the code is really nice to debug. It's really nice to read, and it encaptures many. It's like list comprehensions on steroids in a really positive way. It's one of the most positive features of F#, I think. And you can have whole chunks of your program written in these modalities, and it's very easy to transform your code from one modality to another to make this an on-demand list. You just use seek around it instead of using the square brackets. Okay, so this thing about putting computational modalities into languages played out quite a lot during the sort of co-evolution of C# and F#, and there's influence from the outside. So you have things like Snowball and Icon iterators coming into, via Microsoft Research, coming into C# in 2.0. Then F# kind of says, oh, yes, we can do that too. And we put in like async await and comprehensions and computation expressions and sequences. And that's influenced by a whole lot of work from the functional programming world and the theorem proving world as well. And then in the meantime, C# says, oh, yes, we can put in queries, and it does it via a completely different mechanism. And we, in F#, we just say, okay, we've got this one mechanism. Let's just make computation expressions, which is the unification of all of these things, support queries as well. And we also do asynchronous sequences. And then C# says, oh, look at what F# is doing. They're doing asynchronous programming. Isn't it nice? Doesn't it make parallel programming or concurrent programming really simple? And they put in async await, and it's influenced by other systems. And then async await actually are now escaped out of this world into the world of Python, C++, and Java. And so there's direct heritage from MLDonkey or these various things in the functional world directly through F# to C# through to Python, C++, TypeScript, and others. And in the meantime, C# doesn't stand still. They kind of look at asynchronous sequences in F# and create asynchronous iterators. In the meantime, F# already has that, so we put in support for a slight modification to allow you to do applicatives in the same kind of way. So there's the history of how that develops. And it's actually a really sweet part of F#. I encourage people to take a look at that. There was also a contradiction between typed code. Just noticing my hour is coming up, so I'll be for another 5 minutes or so. So between typed code and external data, and that leads to F# type providers, and it's about external interop, a metaprogramming system for external interop. Okay, so the more recent history of F#, there's a lot I could say. I've kind of tried to focus on those origins. I share my screen again. Okay, so the more recent history of F#. So 2010, F# kind of lands in a tough part of the industry, I would say. The kind of enterprise programming that companies like Microsoft support with their programming languages can be extremely conservative. There can be some very progressive parts of it, and we got lots of people started using F#. But there are also, extremely conservative enterprises which where there literally nobody knew anybody who had ever done anything in any functional programming language. Certainly not a strongly typed language like OCaml. And so it was in retrospect quite a tough part of the industry to land in. And the other thing is it was also Windows dominated, and of course Windows had to. It's not in a sense until 2014, 2016 that I think F# actually becomes fully real and normal as a language, because we're finally cross-platform. We finally have a great Linux story, and this corresponds to the industry move to the cloud, where using Linux becomes totally normal. And we're fully open source, and just so in some sense, F# properly begins there, because we're finally a normal language with a normal cross-platform open source existence. And that's been a wonderful transition. Okay, and then we've done a whole lot of versions of F#, which I won't get on. So today, what is F# today? Its core position is as a typed functional programming language for .NET and JavaScript. Trying to capture that simplicity of experience of that was there in the first versions of ML, and is sort of staying true all the way through. It gets delivered wherever C# does. It's delivered in what's called the .NET SDK, and it's really good performance characteristics. And it's sort of sweet spots are for web client, for mobile, for server, for cloud, and it's also got some good technologies for deep learning. Okay, I'll skip the last part on that. Just some slides about if you want to use it and get going, you just type .NET new -lang F#. We do .NET build. The tools are everywhere. If you want to get going for the web backend, you just get some templates and create your first app. If you want to get going with the front end, it's sort of similar thing, get some templates and create your first JavaScript application with F#. And if you want to do the full stack, there's this wonderful system called Safe. You get some templates, you start, and you get going, and you can deploy through to whichever cloud you wish. One lovely vignette from the paper is about this building, which is the Louvre Museum in Abu Dhabi. And the code that computer generated the parts for the roof, written by an Austrian engineering company, is actually a 3,000-line F# script. And I always like to look down on the satellite photos of this building and imagine there are lambdas encoded in the roof parts of this iconic museum. And I'm looking forward to the day I can actually go and visit this museum and remember that strongly typed functional programming is part of physically creating it. And you can read about that in the history paper. The influence of F#, we lived right next door to the C# team, and it led to many direct influences both ways through the various people I've mentioned here. Some of them went to work onto TypeScript as well. And if you look at the features of C# in this big long list, then the ones I've highlighted are all pretty much strongly influenced by F#. You can see down the bottom left, tuples and deconstruction, pattern matching, local functions. These things are ML, right? They're strongly typed expression-based programming. There's one down here, just hidden down the bottom, nullable reference types. So the nullable is on the decline in the C# world, or nulls. And from one perspective, they finally corrected the $1 billion mistake. Surely the real cost of that mistake is like up 100 billion or something when you consider the lost productivity in the software tech industry because of nulls. And so we are really making the industry move ahead one way or another. F# has had a bunch of other influences. I've mentioned some of them along the way. Okay, so just to recap, the programming world has corrected the dominance of the 1990s. The object-oriented tidal wave has come and gone, and we're in a much happier place now. A whole lot of techniques have occupied their place as practical core techniques in nearly all programming languages. The idea that no one uses functional programming is completely, permanently consigned to history, and F#'s been part of that story all along. And for me, that golden thread of the idea of a language is to support the use of functions and data through just enough types and just enough verification or just enough whatever else is going on. But functions and data is with this sort of sweet spot. I think Milner, Newey, and Morris kind of saw that in 1974. It's what they needed for LCF, and it stayed true all the way through the history of ML. And thank you. And I'll be very happy to take some questions. Sorry to go over by 5 minutes.
Well, thanks, Dan, for a most exciting presentation that really did cover so many facets of the design and history of F#. That's a very happy audience. You're being showered with emojis flying in every direction.
Thank you.
All right. There's plenty of things I want to ask, but I'll start with the audience. Sam has a first question.
Great.
Oh, no. I said Sam. Okay. If you were starting a similar exercise now, but targeting WASM, do you think you'd arrive at a language like F# or something different?
I personally wouldn't be targeting WASM because I wouldn't know what its interoperability exosystem is yet. If it's JavaScript, then I'll just still target JavaScript because F# would be different if we targeted JavaScript originally, without a doubt. Since this absolutely affects the syntax all the way through, it would end up much closer to TypeScript, just without the incremental typing, probably. Let's take another version of that, which might be of interest to people, is what happens if you're targeting interoperability with Python as your core of your system. I think it's an open question, and it's exactly the kind of question I want people to engage with from this talk, is what would it mean to create a language which actually can utilize all the assets in the Python ecosystem. And Python is beginning to be more typed. It's beginning to be more buttoned down around the edges. So it's possible to do that. There is, in fact, an F# to Python compiler as part of the Fable effort. Yeah, I don't know the full technical details, but yes, the choice of exosystem to locate in is absolutely crucial. And you can get too close to these systems as well, in that these systems change over time. They evolve, and .NET has evolved, and sometimes we've been a bit too close to .NET, and as it has improved and evolved, it's kind of, we've had to take the sharp corners with it along the way. Yeah, so I don't know the technical details to that answer, but the answer is yes, we would arrive at something much like F# in that it would still include that core ML programming experience. So large chunks of F# would stay exactly the same from my perspective, but around the edges, there's a lot of difference.
All right. Next one. Gabriel has a question.
Yeah. So C# 4.0 introduced this dynamic type thing for sort of gradual typing. It's kind of it is possible to do this in F#. It is not actively used in practice really at all in F#. Yeah, boy, when I hit C# code that uses that, I hate it. I hate it so much. I'm really furious when people use that as part of, unnecessarily use it as part of a DSL design.
Cool. Moving through the questions, this one already got an answer from Gabriel actually in the chat with a link to the reference documentation for computation expressions.
Yep.
Do you have anything to add?
Well, just to say they're absolutely user definable. If people are interested, you can type in my name or dsime and applicatives, for instance, if you're interested in how to do applicatives in F#, and that particular kind of computational modality. But yeah, no, they're absolutely configurable in quite a number of interesting kind of ways.
Great. Next one, Matthew.
Okay, so what did .NET get right so that it worked well for F#? .NET was a relatively more static system than Java right from the word go. I think when Java becomes big in the industry in 94, 95, and the Microsoft engineers kind of are looking at Java and they kind of see this, what is effectively kind of a cut down type Smalltalk kind of system, and lots of virtual dispatch everywhere. And they say, actually, we want something, our experience in writing code tells us we need, and delivering production operating systems and applications means we need something much more static because, for instance, we need to patch these programs with security fixes or bug fixes, so we need a much more static world. So right from the start, .NET took a substantially more static approach, sort of culturally, than Java. And that goes through its library design. And they also took a very different approach, I think, a more cut down use of, say, object-oriented overloading. They kind of restrict down in a number of ways. And all of those things help F# as F# starts. Now, then, of course, we feed in generics into .NET, and that is absolutely the foundation from a performance perspective. And I talk about why that's the case. The fact that we use code expansion for based on type representations for generics means that we don't get any implicit boxing all the way through. More recently, the .NET, I don't know, the .NET garbage collector is very good. The .NET native code compilers are very good as long as they allow the possibility of JIT at runtime. The willingness, the .NET people have a willingness to put things like tuples into their core library fairly early on, which did help us. there are some things like debugging that the .NET virtual machine and profiling, the APIs the kind of foundational machinery for doing those things works extremely well, and we often actually have more capabilities than we actually exploit for F# today. And especially, I guess, from the garbage collector. The garbage collector is just great it seems to be great for functional workloads. And I actually think it's a bit of a myth of the functional world that somehow these .NET-like garbage collectors aren't good for the programming. They're very, very good. So,
if I actually may interject for a related question, when you think about OCaml, when it targets the its backend, the backend and the runtime system of OCaml are extraordinarily untyped, right? With a completely universal value representation and that completely uniform GC representation. And my understanding is that .NET, as you just said, is much more typed and much more structured. So how come you didn't get an impedance mismatch, seeing that you share so many traits with the original spirit of OCaml?
So there are some places we do get that impedance mismatch. One, for instance, is the fact that core CAML included structural comparison and structural equality.
Yes.
And it's based on revealing that internal representation effectively. And we actually have that in F#, and we pay the cost for that very badly in technical features. When you really, there are ways you can constrain those features come with performance overheads that may not be expected for people. We do a lot of work in the compiler to reduce out those performance overheads, but boy, it's a lot of work, and you can still fall into holes here and there. So but more besides that particular manifestation of that, actually, .NET's an interesting system in that the key thing is that .NET Generics handles polymorphism with respect to all those varied representations. Okay. And that's the key. And it allows, for instance, our integer types aren't 31-bit integers like they were in CAML for a while, but they're 32-bit integers, and lots of positive things end about how the core ML implementation actually plays out in practice. Yep.
Yeah. Okay, so it was really the whole generics work that unlocked the ability to do F#.
Yeah.
Okay.
There are some technically adding GADTs is harder because we don't have that built in, and we don't have sort of notation of existentials in quite the way. Claudio is here. He's actually done papers on that back in the 2000s about how you can get most of that kind of effect. But when you're having the other thing is higher kind of types is not present in the design of F#, and that's because it's not present in the design of .NET. And also type classes, there's an interplay there, and there are also interoperability concerns here. Do we put in type classes into F#? Yeah, we could do that, and we have a kind of some type class-like mechanisms with regards to generic arithmetic. But if we do, and C# does that as well, then we're going to get a really bad interoperability problem because they're not going to do it the same way as us. So we have to really do it the same way. And so I'm okay with that, actually, because there are pros and cons to type classes anyway. But that core question about representations and what mechanisms sort of deal with that, is it the runtime system or is it the language? And what are your representations of values? That's all playing out through those discussions.
I see.
Have we considered? Considered.
No, I was just saying Sam had a question.
Yep, considered adding support for effect handlers, as in multi-core OCaml. So not really, because sort of effect handlers became more in vogue after most related parts of F# already settled. So, I mean, I've considered it. Yeah, every time I see a talk on effect handlers, I'm impressed with the work and I kind of consider it. And computation expressions could interact very nicely with effect handlers as a sort of syntactic mechanism. I haven't. I mean, no. We in terms of actually pushing that onto programmers, know. It always seems to be beyond what the programming world will consider palatable. The parts of the industry we're trying to address, it would seem to blow the complexity budget. I might be wrong in that. Someone else can prove me wrong, I guess.
Next question.
Okay, yeah. So this is so there's a question about you get exposed to nulls through using .NET objects, and in theory, .NET objects can be null, and that's absolutely the case. Now, the .NET libraries very rarely used null, and they almost never return null values. So this is not a serious problem in practice, okay, in using F# code because of the design considerations of the .NET libraries. Now, you can get exposed to them through serialization, and that is an important area. So the other thing is that this business of C# getting null reference types means that every single .NET library coming through the system, in fact, they just announced that they have completed the process of annotating all the core .NET libraries, and it's a very large framework with nullability annotation. So the first time in industry, a set of significant libraries which actually contain so much functionality, let's just point out, say, Unicode or globalization or whatever else, they're all coming annotated with nullability annotations now. F# doesn't yet incorporate that information because, as I said, it's not much of a problem, and F# values are nullable, not nullable by default for F# defined types. So when I say the problem is solved, I kind of take a long-term point of view in the sense that we are on a path where the number of nulls in the industry, or that $100 billion mistake, is kind of going down. The amount of future, the costs into the future of those kind of mistakes in industry. So we're on a path to seeing that change in the basis for programming in the industry, at least in our part of the industry. Oh, okay, yes. So I didn't mention that in the history of F#. So F# does have a unit of measure types put in by Andrew Kennedy primarily at Microsoft Research. And yeah, they're really nice. And they are a sort of very additive to the system in that we make sure you never see these things unless you start to use them. And so it's a sort of feature that people either use or they don't. And there are some people in industry who use them a lot. And so I'd probably, at a guess, about 5% of F# users, 3 to 5%, would be using unit of measure types. Now, there's two variations on that. One is whether you're just using simple kind of tagging of types, but effectively it's kind of colors on types. Or are you actually using the algebraic properties of units of measure? So meters times kilograms equals kilograms times meters. I would say probably only like 0.5% of F# users would be using the algebraic properties of unit of measure types. But when they get used, they happily give talks about how important they are and how crucial, for controlling complexity. There is a problem here, which is that numerically intensive computing has gone very much in the direction of tensors. And tensors these days don't even carry static dimension information about the number of dimensions, for example, let alone the size of the dimensions, let alone the unit types for the information carried in those dimensions. And in fact, those tensors are often carrying a complete grab bag mix, where the first 10 elements of a tensor are in one unit of measure, and then the others are in other units of measure. So there, in other words, as much as I really like the feature in F#, its utility is kind of reduced by the way numeric programming is done in practice in industry today, and I don't think anyone has a good solution for that. I know Adam Paskey, who's worked on PyTorch, is here, and he would be very aware of these problems as well, and how they play out. So yeah, no, there's a lot of unsolved problems in AI programming for the practical rollout of types in AI programming.
I think we finally reached the end of the question list. That was a lot of questions. This is great.
Okay, my pleasure.
I think we only have 7 minutes left of a break before the next session. So how about we all give everyone a breather before the next session restarts? Thanks again, Don, for this really great talk. It's been a pleasure listening to you, and I hope to see many more F# submissions at the ML workshop in the coming years.
Yeah, we will look forward to that, and thank you very much as well. If anybody's got any follow-up questions, I'll be looking at the chat, or send me a message on AirMeet, or just contact me privately. Okay, thanks very much.
All right, thanks. Bye-bye.
Hi, can you guys hear me?
Yep, we can hear you, Benoit. You're live.
So maybe we should wait for people to join in.
Okay, Benoit, so basically you can't do the thing with the questions, so you just need to rely on me to follow your cues and put the questions live and mark them as answered.
All right.
And I'll take care of bringing the right people on stage and playing the videos. And you just need to give me like 1 minute because the user interface of Airmeet is terrible and there's like 100 videos that are not sorted. So I need to do a linear search every time to find the right video. It's terrible.
Sure.
Okay. And we have, for the last talk of your session, Benoit, Keigo will present live or play a video live. So I'll just put him online.
Okay, thanks.
All right, you're all good. Benoit, I'll let you handle the session and I'm going to disappear. Thanks.
All right, so welcome to the next session, which is about language and library design. The session is composed of 3 talks, and the first one will be given by Jonathan Sterling from CMU, and the topic is a meta-language for multi-phase modularity.
I apologize. Is the video supposed to appear, or?
No, that's my fault. There's like a lot of videos.
Okay, I wasn't sure if I was supposed to do something.
I'm scrolling to find yours. You're on.
Okay, great. Is modularity. I'm John Sterling, and this is joint work with Bob Harper. Software engineering is about the division of labor between users and machines, between clients and servers, between different programmers, and between different modules. Tension lies between abstraction, which embodies the division of labor, and composition, which embodies the harmony of labor. PL theory as a discipline is a particular approach to deal with this tension. In PL theory, we advance linguistic solutions to the contradiction between abstraction and composition. In this talk, we will focus on one particular example of this contradiction, the tension between separate compilation and inlining. Separate compilation is a simple idea, which is to compile each program unit as a function of the other units that it depends on. Separate compilation is attractive for a couple reasons. First of all, compilation is easily parallelizable. Even if one unit depends on another unit, they can both be compiled at the same time because they will both be compiled as a function of the things they depend on. Separate compilation is also attractive from an aesthetic point of view because it enforces the modularity of program units. In principle, even a compiled unit could have its dependencies replaced without changing the overall behavior of the program. Separate compilation also has some problems, especially in regard to composition. First of all, separate compilation can impede the inlining of definitions, which can prevent the compiler from exploiting implementation details. For instance, if the compiler knows how a given piece of code is going to be used, it may be able to generate more efficient code. The main alternative to separate compilation is whole program analysis in the style of the Milton compiler for standard ML. This works great, but it is very slow and it takes a lot of memory. We would like to put the choice in the programmer's hands as to when and where abstractions get broken for the sake of efficiency. In order to make what we are saying precise, let's discuss program units. Programs are divided into units, which are classified by interfaces that represent their imports and their exports. For example, we may consider the idealized interface to a fragment of the os.filesys module in standardML standard basis library. It imports some basic data types, including the option data type, which is a functional form of exception control. And it exports an abstract type representing a cursor into a directory, as well as some operations for interacting with this cursor. Interfaces, as we have described them so far, support only importing and exporting abstract types, that is, types whose identity is not known. To support type synonyms, such as type dirpath equals string, we need to add more structure to the language of kinds. Stone in 2000 introduced singleton kinds to support exactly this revelation of representation details. Given a kind k and an element C of k, the singleton kind k maps to C is the type of elements of k that are equal to C. That's a bit of a mouthful, so let's look at an example. We could have exported a constant dir path of singleton kind type maps to string. This has the effect of exporting a new type dir path that is equal to string. In other words, dir path and string are interchangeable in this context. The inlining problem that we discussed earlier is similar, but there we want to reveal representation details to the compiler, but not to the programmer. Singletons, however, reveal implementation details to both. This points to a need for a controlled version of the revelation of implementation details. In ML languages, when you define the same algebraic data type twice, it's actually a different type as far as the type system is concerned. This is called generativity and is reflected in the language of interfaces by the way that the unit is depending on an arbitrary implementation of the option data structure. As Harper said in his 2013 ML workshop talk, algebraic data types are actually abstract data types. Here we are abstracting over a type constructor option together with two term constructors, sum and none, and a function implementing a case analysis principle, which will be the target of the elaboration of pattern matching. This is good for modularity, but it's actually terrible for pattern compilation. If we had a lot of nested pattern matches, we would certainly want these to not be implemented by calls to various functions, but instead implemented by a real pattern compiler. Therefore, inlining the fast path representation is not optional. We saw earlier that singleton kinds can be used to expose the representation of a type. Both Stone and Leroy propose to address the inlining problem for both types and runtime values by adding an analogous singleton type connective. Then, in an interface, we could expose not only the definition of a given type, but also the definition of an element of that type. Unfortunately, this solution is too naive. Singletons reveal representation details to both the programmer and the compiler, which defeats the purpose of introducing abstractions in the first place. The reason we even bother with abstractions is to hide distracting facts from ourselves and from our future selves, who tend to be more ignorant than our present selves. This provides protection from representation coincidences. For instance, an integer that encodes the name of an instruction is not to be confused with one that encodes the length of a packet. A more advanced use of abstraction is to exploit representation invariance. For instance, a batched queue has better amortized complexity than an ordinary queue, and if your code only uses the queue operations, you can be sure that it will not depend observably on the difference between a batch queue and an ordinary queue. Likewise, polymorphic functions between lists can only permute, drop, and duplicate elements. Therefore, there are only so many things that can be incorrect about such a function. For a more extreme example, any polymorphic function into a constant type is itself a constant function. Therefore, abstraction simplifies both programming and verification tasks. While programmers introduce abstraction to protect ourselves from representation details, compilers have the exact opposite needs. Compilers need these representation details in order to generate efficient code. We've seen two solutions so far. One is the use of singletons a la Stone and Leroy. This has the benefit of allowing inlining, but it breaks the programmer's abstractions and therefore makes reasoning and programming more difficult. On the other hand, one can simply break all abstractions during compilation after type checking, in the style of Milton. The Milton approach is very good because it preserves programmer abstractions during type checking time and produces very efficient code. Unfortunately, it is very slow and it can make your laptop get extremely hot. We propose a unification of these two ideas that puts the decisions, as far as trade-offs are concerned, into the hands of the programmer, negotiated by a phase distinction. Types do a lot of things, but I think that it is worthwhile to pay attention to what Reynolds said types are for. Type structure is a syntactic discipline for enforcing levels of abstraction. Our experience tells us that programmers and compilers are working at very different levels of abstraction. The programmer is introducing a lot of abstractions to protect themselves well from themselves, but the compiler is eliminating these abstractions in order to generate efficient code. Unfortunately, our type systems do not cleanly account for this interaction. We claim that the classic ML family phase distinction provides crucial insight to actually implement Reynolds' dictum in a programming language. Traditionally, the phase distinction expresses the non-interference of runtime code on static code. Historically, this was a pivotal notion in the development and design of ML languages and their module systems, and there have been a lot of takes on it in the literature since it was first introduced. But do we still need it? First of all, runtime values increasingly have a static identity, even going back to the strong structure sharing of SML90, as well as the singletons in modern Haskell and the path-dependent types in Scala. Furthermore, while in the past it was unclear how to compile partial and effectful code in the presence of dependent types, there is not presently any obstruction to doing so, as we can see from the experience of the Lean 4 and Idris 2 implementations. Therefore, we fear that the original motivations of the static dynamic phase distinction hold very little force in the year 2021. On the other hand, we have found that other useful phase distinctions abound. For instance, logical relations and parametricity arguments evince a phase distinction between syntax and semantics. This observation lies at the heart of the recent proof of normalization for cubical type theory by myself and Carlo and Julie, and the recent proof of normalization for multimodal type theory by Gretzer. Bob Harper and I have also used this observation to give the most succinct proofs of representation independence for ML modules that has appeared in the literature so far. There is also a phase distinction between program behavior and program complexity, which you, Grodin, Harper, and I have used to design a cost-sensitive logical framework that can be used to reason about the cost and behavior of programs at the same time. Similarly, Melius and Seilberger have shown that there is a phase distinction between computation and specification, reconstructing the semantic aspects of type refinements. And in this talk, we are considering a phase distinction between compilation and programming or development. The inlining problem was in essence that singletons break abstraction now, but we want to postpone that to compile time. We will write C for a token representing the compile time phase, and introduce a generalization of the singleton types of Stone that we considered before. In particular, we will introduce a partial singleton type, tau C maps to E, which is the largest subtype of tau that becomes equivalent to the singleton tau maps to E at compile time. That is, an element of tau C maps to E is going to be an arbitrary element of tau that, if you were in the compile time phase, would have to be equal to E. C is just one of many phases, which we'll arrange into a partial order with a top element. The top element represents now. The total partial singleton, that is, the partial singleton for the top phase, is just the ordinary singleton type. The last change that we have to make is that judgments will now be indexed in a phase, and they will support a contravariant action along the phase partial order. The purpose of the action is the following. If you have an element of a type now, then it corresponds to a compile time element. Let's look at an example of how we can maintain abstraction while supporting efficient representations. We consider a unit that imports abstract types representing the DNS protocol. For instance, we have abstract types for header IDs, opcodes, and so on. These are revealed to the compiler to be unsigned shorts, unsigned cars, and so on, but not revealed to the programmer. Then we have a header type, which is transparently the product of all these other types. In our unit, we export a parser that turns bits into headers. We can easily prove that the parser does not observably depend on the representation of opcodes, etc. However, compilation proceeds by reindexing along the phase transition from now to compile time. Because the header IDs, opcodes, and so on were given by partial singleton types with supports in C, we actually now have a definitional equality between header and the product of all these low-level types, unsigned short times unsigned car times blah blah blah. Therefore, the compiler easily has enough information to choose an efficient, unboxed representation without breaking programmer abstractions. As we have seen, the phase distinction between compilation and programming is but one of many possible phase distinctions, all of which have identical formal properties. Therefore, we advocate future-proofing ML core languages by indexing them in an arbitrary phase lattice O. There is type structure that corresponds to this phase lattice. First, we have the partial singletons for breaking abstraction in a given phase. Then, we have a phase modality for code that only exists in a given phase. We also have a sealing modality for erasing code from a given phase. The sealing modality generalizes the way that sealed modules in standard ML do not have any static component. Finally, one must impose a correctness condition that governs the interaction between its modalities, called fracture. Any type tau can be reconstructed as a subtype of the product of its phase modality with its sealing modality. This language can be seen to reconstruct all semantic aspects of existing phase distinctions, as well as refinement types as found in Liquid Haskell, parametricity and logical relations, and even security typing or information flow control. The debugging problem for functional languages seems to be another pain point that a phase distinction might address. Because we don't have usable debuggers, we tend to use printf debugging for almost all of our problems. Unfortunately, printf debugging tends to be incompatible with abstraction. Let D represent a debugging phase. Then we can add the following computational effect primitive to our language, a debug function that takes a debug phase string to the unit type. First of all, we can prove that for any two debug strings, their debug statements are observationally equivalent. Then from a given abstract type, we can export a debugging function that turns some data into a string. For instance, we could have a debug phase dump header function that turns a header into a string. Debug phase code can be stripped at compile time. In particular, we would change the compilation procedure to reindex not from now to the compile time phase, but from now to the meat of the compile time phase and the negation of the debug phase. A similar approach can probably be used to account for profiling data. One of the annoying things about profiling is that when we add counters to our data types, our code can now depend on the values of those counters. Using a combination of the sealing modality and the phase modality, we can give an account of profiling that ensures that code does not observably depend on the number of times a given function has been called. As I have mentioned before, several applications of our phase distinction metalanguage are already well developed, including the new approach to parametricity for ML modules, the normalization proofs for cubical type theory and multimodal type theory, and the cost-aware logical framework, which is a form of proof-relevant type refinements. Our next steps include developing the connection to security typing and information flow control, studying the elaboration of high-level modular constructs to the metalanguage, including a prototype implementation in the CoolTT theorem prover, and adapt the approach to logical relations to handle step indexing. Thanks for your interest in our work.
All right, thanks for the talk. Don't hesitate to ask any question you might have in the Q&A tab. Meanwhile, I have some questions. So you talked a lot about the sort of improper implementations of inlining in current implementations of ML. So do you see any path using your work that would lead to a better implementation of inliners in ML languages?
Right. So to preface this, I'm not a compiler engineer, so many people in the room will be able to speak to that more accurately than I. The work that Bob and I have done especially pertains to accounting for the behavior of inlining linguistically, as opposed to something that happens after you get out of the language and you start doing like bit munging. So from this perspective, I think that we would be able to explain what is happening when a tool decides to mix separate compilation with abstraction breaking. And I think that because the syntactic and semantic aspects of the phase distinction language that we are using are somewhat forced, I think that it would provide a good guide to designing such features.
Okay, thank you. So Jonathan, we have a question from Neil. What do the models for the debugging phase distinction look like?
Right. So maybe I can answer a slightly more general question. If you have a particular lattice of phases, like what kind of models do you expect for this? And the debugging phase distinction would be one example of that. So the generic case is where you pick some lattice or some poset of phase distinctions, and then the most universal model for this setup is the presheaves on that poset. Here you get the classifying topos of a filter on your lattice or whatever, for instance. And what the utility of this model is that it gives you a type theoretic language that can interpret ML that has a generic filter, that meaning propositions corresponding to being in each phase. Now, there are many other models corresponding to any other setting that has such a filter, but all of these can be recovered by restricting this universal one. So I like to think of this very concretely as just type theory or set theory or whatever, but just indexed in this lattice.
Okay. Thanks. So I guess like here with your debugging thing, you have like sort of a 2-point lattice. Like is that what it looks like?
Yeah. So like the Sierpinski space would form like a example of how you would model this the most simply. Yeah.
Okay. And then sorry, I'm just trying to like think through this. So if you have a type, then in your pre-sheaf model, it's like every type becomes 2 sets with like some sort of function from one to the other. And right. How should you think about those 2 sets? Like, one is the one without the debugging information in it, and the other one is?
Right, so there's actually 2 ways to do this. In the slide, I described an approach where the stuff, the debug phase stuff is like on one side and the entire thing is on the other side, and you could also flip it around, and I think in order to figure out which is the best way, we'd have to try both. It basically corresponds to like, do you want to have the thing you're trying to model be in the open subspace of Sierpinski space or in the closed subspace, and those behave differently. So I think both can work, but they behave differently because when you get rid of one part of it, you're either looking at like a co-heighting negation or an actual negation.
Okay, and I guess like, sorry, I'm still thinking like your compiler correctness theorem would say something like the meaning of your non-debug program, half of your program is unchanged by your optimizations, rather than saying the meaning of the program is unchanged. Okay, thanks.
Right. Sure, thank you.
Okay, thank you. So we now have a question from Gabriel.
Okay. In traditional module systems, phase distinctions also correspond to different languages. Term, type level terms versus type kind level terms. Here you have a single level, but we can classify later phase terms from earlier phase terms. Yes, so this question pertains to the what some people refer to as the static dynamic phase distinction, or the compile time runtime phase distinction that appears, I believe, in pretty much all ML languages so far. And yeah, so like one way to deal with that is the way that has been dealt with so far, where you actually have a distinct grammar of static stuff and runtime stuff, and then you have type structure that mediates between them. And another way to deal with this, which I think dates back to only the paper of Bob and I, Logical Relations as Types, is to just have a single language, but then have various judgmental modal notions that allow you to distinguish extrinsically from things that have the property of being static or compile time, and things that have the property of being dynamic or runtime. These 2 approaches are equivalent, and they can be related by a like phase splitting translation. So we prefer this extrinsic approach because it gives rise to simpler syntax, but the difference is not really consequential.
Okay, thank you. And we have a last question, it seems, from Leo White.
The notion of type for inlining systems are often richer than the type system of the source language. Can your formalism account for having different type algebras at different phases? Right. Yes, we haven't explored this direction very much, but one thing that you can do is, in principle, you can actually have each phase have a totally different type system, and that can be accommodated, for instance, by having, like, let's say at one phase you've got a type that doesn't make any sense at another phase. That can be accommodated by making that type turn into the unit type at the other phase. This can be used, for instance, if you are trying to handle, say, type refinements, where you have a much richer type structure at the specification phase that is refining a much coarser type system at the computation phase. So there is a lot of flex in here, and the modalities that I discussed, the phase modality and the sealing modality, are the ingredients to enable you to negotiate the differences between the expressivity of the different levels.
All right, and Sam Linley now has a question.
Have you thought about adapting your formalism to account for running code in different locations? That's a fascinating question. It reminds me of, for instance, like the work on ML5 by Tom Seven and so on, and I'm sure other things as well. Short answer is we have not thought about this, but it sounds very interesting. I don't want to say more because, well, maybe someone in the audience will want to figure it out, because I have no idea. It sounds really cool, though.
All right, I have a last question. We still have a few minutes left. Have you seen any use, any need for phase polymorphism, that is abstracting over phases? And how hard would it be to include that in your development?
That's an excellent question. So in like ML programming, I'm not completely sure if I have any immediate use cases, but I have used these phase distinctions for a lot of different stuff besides programming, and there it's very useful to have polymorphism over phase. For instance, in the so we've used the phase distinction meta language to prove normalization for cubicle type theory, and there's a lot of very subtle constructions involving phases there, where you have a very subtle way to glue together two types, but you're gluing them together so that the overlap is only occurring in a particular phase, and so on. And this is done using a subtle use of the phase and sealing modalities. Now, I need to do this all the time at different phases, though. And so in my dissertation, for instance, I define general constructions that are polymorphic in the phase, and then you can just instantiate them where you please. Semantically, this corresponds to, in addition to having the usual kind of types, to have a kind of phases and behaving somewhat like a subobject classifier, if that's the language that is familiar. So this can be done, although it may be a little tricky integrating it with the kind of partiality that occurs in ML. So I don't want to make strong claims about that.
All right, thanks. Maybe one last question. Can you expand a bit about the link with information flow control type systems that you mentioned?
Yes. Yes, the idea is that every security level corresponds to a phase. So you just render those as phases in the phase meta language. Now, then the sealing modality, which I regret didn't have much time to discuss here, that can be used to classify information, to hide it from a given security level. In particular, you can use it to hide it from all security levels strictly lower than a given one. Using this modality and its equational properties, you can then prove non-interference theorems that express the fact that like some low security client is not able to observably depend on a high security bit.
All right. Thanks a lot. Let's thank John again.
Thanks, everyone. Appreciate you coming.
So our next talk will be given by Gabriel Scherer, and the topic of the talk is unfolding ML data type declarations without loops.
Gabriel Scherer, the fellow on the right, picture on the right, and I'm going to talk about unfolding ML data type declarations without loops, which is joint work with Nicolas Chatin, the fellow on the left. And this work was done as part of Nicolas' internship supervised by me. So in this talk, we are going to talk about an OCaml feature that we wanted to implement. This was Nicolas' internship's topic. And as part of this implementation work, we discovered a more general problem that applies to any other programming language, that is how to unfold recursive type declarations in a not terminating way. And I'm going to explain first the feature and then the more general problem and how we solved it. So the feature is an extension of constructor unboxing. Since about 5 years ago, OCaml allows single constructor unboxing. So if you have an algebra data type with a single constructor and a single parameter, you can add this unboxed annotation to add that at runtime, the constructor is not used. It's compiled into the identity function. It's not represented. This makes the representation similar to a type alias or synonym, but the type is incompatible. You have to explicitly use the constructor. This is nice. Actually, for most programs, not representing the constructor, not boxing the value, does not make such a performance difference. But in some rare cases, it is important. And it satisfies people who want to write zero-cost abstraction. So they want to know that their costs do not occur any change in the runtime representation. And then last year, Jeremy Yallop proposed an extension of this form of constructor unboxing, where you could unbox one constructor among several others, or even several constructors in the same time. So here is an example. I define a type of big numbers as either actually a small number, which is just an int type of OCaml, which is 63 bits wide, or a big number, which is represented by a GMP integer, GMP being a library for big numbers. And this representation is nice because if you know that the two inputs to your addition function, for example, are small, you can use the in-language addition, and that's faster than calling for the GMP addition. But to get actually a performance win out of this, you want to unbox the small constructor to make sure that the small integers are represented just as primitive integers and not as box values. So in this case, it makes a big performance difference. And the reason why it makes sense to forget about the small constructor here is that the two set of values, so integers on one side and this big of GMP.t, are disjoint. So OCaml uses a tagging scheme. Many languages do that, and the details vary. In OCaml, there is one bit in the value that tells you whether it's an immediate value or a pointer to a block on the heap. So even if you forgot about small, you can use this tagging bit to distinguish the two cases. So now, to allow for this feature in general, we need to define a check that is to accept unboxed annotations and to reject some of them that would be problematic. So that would be problematic because if you forget about the constructor, in their case, the values on both sides would not be disjoint anymore, so there is a risk of miscompilation. So to check that two types have disjoint representation, we use an abstraction of the set of value, which we call the head shape. So we first define the head of a value by two information. So first, whether it's an immediate or a block, and then a number. Z in this talk represent machine integers. So the head shape of an immediate value is, well, it's an immediate and then the value itself. And the head shape of a block is a tag. So in OCaml, when you have a block on the heap, it contains some information, the tag, that is a sort of runtime type information that is used by the garbage collector and also by some runtime services such as comparison and serialization. Okay, so for example, the foo literal string, the head shape would be that it's a block and that its tag is string tag, which is 252. So the tag is fits in 1 byte. And now we define the head shape of the type as the set of heads of any of its values. So in particular, if you have two types whose head shapes are disjoint, then its values must be disjoint because heads are a function from values to a smaller representation. So in the bignum example, if you do not use any unboxed annotation, well, then the small constructor will be represented by, with a block, the tag 0, and the big constructor will be a block with tag 1. But if you do use the unboxed annotation, so this is accepted because the compiler can check that the shape of small of int unboxed is just any immediate value, so it's the shape of an integer. And the shape of big of GMT is all the values in the set are blocks of tag 0. Okay, so the two head shapes are disjoint. This is easily checked, so we allow this definition. So in particular, the disjointness you need to implement pattern matching. Okay, so before in the usual standard compilation strategy, the pattern matching compiler to check whether we are in a small or the big case would know that it has a block, get the tag, and check whether it's 0 or 1. With the new compilation strategy, we have to look at the shape and we say, oh, actually the shape of some small constructor, which is unboxed, is just immediate. So I can check whether I have small or big by checking this tagging bit to know whether I have an immediate or a block address. Okay, so we can still compile pattern matching definitions, and the fact that we use heads as the argument for disjointness means that at runtime we only have to check the heads of the value to tell which constructor we have, which guarantees that okay, they are disjoint and there is a efficient runtime way to check disjointness and to compile pattern matching. So the high-level idea is that constructors are a way to enforce disjointness of values of hypertrophic data types, and that any compilation scheme that preserves this disjointness is admissible. So now comes the question of, okay, so at compile time you see a definition that contains some unboxed constructor. You want to check statically that this disjointness criterion is preserved. So you need to compute the head shapes of your types. How do you compute the head shape of a type? Here is an example. I have a type alpha tree. So the trees are n-ary trees, and when I have a node, I have one value for each subtree. Okay, so it's just a bizarre form of tree used for this example. So a tree is a node, and the node contains a lazy sequence of pairs of a value and a subtree. And because I mark this node constructor unboxed. Okay. So to compute the shape of an int tree, and let's go in the other type definition. A sequence is either nil, the empty sequence, or a func. So it's weirdly lazy sequence. It's a func of that will once first give me the first value of the sequence and then a subsequence. And then I have some type foo that is either an int tree with some unboxed foo constructor or something else. So I want to check that the foo definition is valid. So I need to compute the shape of foo of int tree and then the shape of the rest and check that they are disjoint. So to compute the shape of int tree, what I natural thing to do is to go look up the definition of tree. Okay, I see that it is a type with a constructor that is unboxed. So the shape of int tree will be the shape of whatever I get by expanding this sec constructor. So I go a type int times int tree. So now I need to go look at the definition of sec, and I see that there are two constructors. There is nil, or there is this next of blah blah blah. So I can recursively compute the shape again. And at this point, so nil is the constraint constructor, no parameter, and the representation is OCaml is as the immediate 0. And the thing on the right is a function type. So I do not need to compute the shape of the argument. There is some shape of functions, so specific tags which did not function and nothing else. Okay. So now I have computed the shape. One thing that is worth noticing is that the core operation I made is to, look at the head constructor of the type, go read some definition, and in this definition, replace parameters by type expression. And this is precisely a beta reduction. So actually what I'm doing is I'm computing some normal form with a call by name reduction strategy in presence of arbitrary recursive definitions. So it does not look like the typical syntax of function programs like lambda terms, but actually these are terms that with well-defined beta reduction. And what I'm doing in this example is repeated beta reduction until I end up on some sort of normal forms, which are types whose shape I can decide without looking at the shape of their subtypes. Why do I say that it's called by name? Well, look at, for example, in this example, into int3 sec, I will go and expand the definition of sec before trying to normalize the argument. For example, int3 here, I don't need to touch, I just expand the head thing. So this is the call by name reduction strategy. And as you probably know, computing a normal form of a term in presence of arbitrary recursion is not, well, some terms do not have a normal form, some terms loop indefinitely, and a priori it may not be decidable whether a term terminates or not. So here is an example, it's a synthetic example, I'm sorry. So the type T contains an unboxed occurrence of U, and U contains an unboxed occurrence of T. So if I try to compute the shape of T or U by using this approach of repeated expansion, so at compile time when checking the program, I would loop infinitely. So the question is, how to compute this normal form without looping? Yes. So normal form of a type modulo type aliases and these unboxed constructors. So this is useful to compute the shape of a type, which is what we need to do in our particular program. But it's also useful in other type analysis in the OCaml compiler, notion of immediacy and so on. And it's a problem, I think, of general interest. So any language could want to do some analysis based on the normal form of type expression after unfolding definitions. Okay, so it's a more general problem. The first idea is to say, let's forbid cycles in a very simple way. So ML family languages have type synonyms or type aliases, and these are typically not allowed to be recursive. They cannot refer to themselves, or you cannot have a mutually recursive nest of aliases because that corresponds to, if you want after expansion, to infinite type expressions. More precisely, when you have a cycle in a mutually recursive set of types, that maybe some of them are aliases and some are algebraic data types, well, each cycle must go through at least one constructor of an algebraic data type to be accepted by the language. So we could use the same approach here to consider unboxed constructor as just synonyms, and to say that these unboxed constructors do not count as cycle breaking in this sense. The problem is that this is too restrictive. So in the example that I used before, for example, this criterion would reject the type definition. You would say, okay, tree is used within its own definition, and there is only an unboxed constructor between the definition and the use type. So this is a cycle I reject. This is not so good because if I did not use the unboxed annotation, this would be accepted. And the idea is that users start from existing type definitions, declarations, and then I want to stick the unboxed annotation in some cases where it makes sense from a compilation point of view to get performance benefit. And they don't want the code to start being rejected for a totally different reason of cyclicity. And here, actually, if we expand the definition of sec, or if we at least we look up the definition of sec and we reason about it, we will see that the occurrence of A3 inside A3 is not problematic, okay? It will not create an actual cycle when expanding the definition. So there is no good reason to reject this definition, and it would be problematic in practice. So this static criterion that works without expanding anything, we reject. Then there is another idea that comes naturally, which is to, okay, just do repeated head beta reduction, but keep track of the set of types that you have seen in this reduction sequence, okay? And if you reduce, you expand a type, and you get a new type that is the same as one of the type expression you had before in your reduction trace, well, you have found a cycle and you stop, okay? Of course, if you do see something that gets repeated, you really have a cycle and you really should stop. The problem is that there are some definitions for which that will loop and for which you will not see a cycle. These are called non-regular recursive definition. So here I have this alpha bad example that is a loop of alpha times alpha bad. So if you take int bad, you expand it, you get int to int bad. And you expand it again, you get a larger type. And you will get an infinite sequence of larger and larger types that never repeat themselves in the sequence. So your criterion does not prevent non-termination. So this fails. And then an idea is, I do not get the same expression again and again, but I get the same constructor at the head, the type constructor bad, that repeats many times, which is probably the sign that there is a cycle. So instead of tracking whole expression, I should track head constructors. Okay. The problem is that this is too restrictive. Here is an example. I define a ID type, which is a parameterized type, which is equal to its parameter after some unboxed ID constructor. And then I define the type foo as foo of int ID ID. And this, if you try to expand it using this termination checking strategy, you will stop thinking that you have seen a potential loop. Okay, so you start with foo. You haven't expanded anything yet. You expand foo, so the expansion trace is foo, and you get int ID ID. And now you will expand ID, and the expansion trace is now foo ID. And the type that you have is int ID. So the head constructor ID already occurs in your expansion trace, and so the algorithm will stop and say, oh, there might be a cycle here. But in fact, there is no cycle, and you rejected a perfectly valid definition. So this example is very synthetic, but in practice, it will occur that some type definitions are used as auxiliary definition to add some extra bit of information. And these auxiliary definitions, they could show up twice along a cycle, okay? And there is no reason, along a definition, there is no reason to forbid them. And they will be used in actual programs that people care about. So this criterion is too restrictive. And then the final iteration of this approach, which is the one that we used in the end, is to say, instead of tracking the set of constructor expansion that I made at the head of my type expression, I will track an expansion context for all sub-expressions. Okay, so let me show you with an example. I took this ID example and I made it slightly more interesting. So now we have int delay here, and delay is just something that expands in one step to ID, which again expands to its parameter. Okay, so just a small wrinkle in the definition. So I start with foo, and this expands to int delay. And for each sub-expression, so here int, which is type expression, I remember that it occurred first when I expanded foo. And then int delay, the whole sub-expression int delay, it occurs first when I expanded foo. And then int delay, this whole sub-expression, it occurred first when I expanded foo. So the parenthesing is a bit subtle here. And so now I have an expression, type expression, and all sub-expressions are annotated with the idea of where are they coming from. And when I expand this delay, so alpha delay expands to alpha ID. So the alpha int foo delay foo I keep unchanged. And then this ID here, which is some new part of the term, I remember that I got it by expanding foo and then delay. So each time you do an expansion, you add a new constructor to the trace of the new parts of the type expression that you get. And then when you expand ID, you get alpha, so you get exactly the parameter. And here, nothing new appeared because of the expansion to ID. So there is no ID. There is no ID left in the trace. So then what we get is what we had at the second step, in foo, delay foo. And when we expand this delay, which is now in head position, we get ID in the expansion context foo delay. And when we expand this vanishes and we get in foo, which is a normal form. So here, it's the same idea of tracing expansions, except that the trace that we store on each sub-expression remembers when it first occurred in the expansion sequence, and not where we are, what the expansion we have done right now. And this difference accepts this example and makes the check much more expressive. There are more recursive definitions that are accepted, while remaining terminating. If you have an actual batch cycle, instead of these two inoccurrent occurrences of delay, it will show up in the trace and you will stop detecting a loop. So, oh yes, Stephen Dolan remarked that this algorithm is actually the same as the one used by the C preprocessor, CPP, for to guarantee the termination of macros, macro expansion in C. So if you want to find a very unreadable, informal textual description of this algorithm, go read the C standard draft. Proving the termination of this algorithm is surprisingly tricky. So it was done in GitHub. So Nicolas and I thought of a proof and we wrote it as a GitHub comment. And then Stephen Dolan found a bug in it, and we proposed a new proof. And then he found a bug again and again. And I think at the third or fourth iteration, I complained in frustration to Irene Valsperger, who proposed a stronger argument, which we and at this point we had the proof that everyone, Nicolas and I, Stephen and Irene, were happy about. So this is really a collaborative development. And now you may ask, well, is it complete? What are the definitions that would terminate but that you reject? Of course, there is no sound and complete criterion for the termination of call by name terms with arbitrary recursion, general call by name lambda terms, because it's a Turing complete language, and so it's undecidable. But in fact, if you look at the terms that you get as ML type definitions, they have the property that the parameters of the type constructor are all first order. They are of kind star, never of some higher kind. So as lambda terms, they correspond to a first order fragment of the lambda calculus, in which, for example, you cannot define a fixed point combinator. And I believe that this criterion, termination criterion that we use is in fact complete for the first order lambda calculus with arbitrary recursive definition. But it's not really important. Why is it not? Because whether or not you allow higher kinded parameters is a design choice in your language. So in general, we cannot consider that this criterion is complete. I mean, at some point you will extend your language and it will become incomplete. So you should rather think of it as incomplete. But it is incomplete, but it accepts the definition that people want to write today. Okay, and I think a good deal more, which is good enough for us. Once we get a richer language, and if there is a use case where this criterion is too restrictive, we can think about expanding it. But for now, we are very happy with that. And actually, we think it is complete for OCaml today. Okay, so this is the end of my talk. To summarize, we worked on unbox constructors, which is an optimization, a representation feature that requires some static type analysis to detect whether it's valid or not for a given data type. And this required us to work on the problem of normalizing type declarations, type expressions, in presence of cyclic references, cyclic type declarations. Thank you. Do you have any questions?
All right, thank you, Gabriel. So please don't hesitate to type in your questions in the Q&A tab if you have any. in the meantime, I have some. So you told us that this analysis could be useful for other phases in the OCaml compiler. So my question is, have you already implemented what you just presented in the OCaml compiler, or when will it be available?
So we have a prototype that is like in our experimental sort of the OCaml compiler. So there are two things. The whole feature I discussed and box constructors we have as a prototype that is almost ready for submission of stream to code review, but not yet. And then there is precisely the expansion strategy. When we design it, we realized that it could also be used in an existing part of the compiler that is doing that, and is doing this using Fuel. So instead of trying to check for normalization termination, it tried to expand 1,000 times and then it gives up. So we did submit a pull request with just this part of the logic of our work as a change to the compiler. And this one has been, that's the setting in which the normalization proof was done. It has been proposed, it's not integrated, and there is a fair discussion to be had about, well, the Fuel trick, it's ugly. I mean, as a researcher, we are not so happy to have a system that rely on running out of fuels when before rejecting a user definition, but it's also very simple. And this work is pleasing in a technical sense, but it's also a more complex implementation. So there is a real question discussion to be had about whether it's actually a good thing to put in the compiler or not, and hasn't really occurred yet.
Okay, and how does it work with respect to performance?
So do you mean the performance of the, well, of the normalization?
Yes.
Well, in practice, when people write, would write unboxing annotations or, so I would say it depends in which part of the type checker do you need to do normalization. The normalization we want to do in our work is whenever someone uses an unboxed annotation in a type declaration, and this is rare enough, even if you think of a very large library with many type declarations, there will be maybe 100 unboxed fields or something like that. So in practice, it's neglectable. This being said, in the OCaml compiler today, there is already some logic to unfold definitions for optimization purposes. And there, it has occurred in the past that this logic proved to be a bottleneck because it was used for basically all the types in the expression in the program. And the details are a bit complex, but so yes, we haven't tried our normalization strategy in this context. We expect that it is slower than the Fuel approach. I mean, the compile time performance to be worse than the Fuel approach, but we think that we could make it implement it so that the cost is small for reasonable expression that have a very short expansion anyway.
Okay, thanks, June. Jonathan Potsenko has a question. Have you considered using ugly tricks, like using the lower bits of pointers on x64 to unbox even more?
So no, in this work we were careful to come up with a reasonable and restricted notion of unboxing. And what is the notion of disjointness that we will use? And we decided to use only the tag. Well, there are two sides of this question. There is allowing to unbox more definitions because we have a more refined way to check for disjointness. And this is something that the Rust community has been discussing a lot. And they have schemes that I would consider unreasonable, like, oh, these structs, there is some padding space and we could put magic word in the padding space so that we can distinguish them, the two structs, because they are padded differently or something like that. For now, we are not considering going in this direction. And then there is another question, which is, can you pack more information in the current representation or something like that? So, and I haven't thought much about it, so not considered. One thing that is related to the Jonathan question is that in Haskell, there is an optimization where when you have a pointer to a block, I think you can store the constructor number in this low bit of the pointer so that you can know which constructor you have without dereferencing the pointer. So, and I think this is what Upstream GLC does today. So it's a sort of data representation hack that does not reduce the amount of boxing, but improve performances nonetheless. And it's orthogonal, it's compatible to with what we do.
All right, thank you. So let's thank Gabriel again. And it is now time to listen to our last talk.
Hello.
Hi.
Can you hear me?
Yep, I can hear you all right.
That's good. Yeah.
Okay. Oh, very nice setup you've got here.
Yeah. I guess I'm on YouTube now, so maybe I shouldn't show my living room.
Oh, it's okay. You look as professional as can be for a computer science researcher. Okay, you know the drill. You just need to use me as an assistant and basically run the session. And I'll just like find the videos and get everything started. You'll be sharing the short talk session, so I'll just be on on the lookout for your clue, and then I'll just play the next video, and these will be brief.
Thanks. Yeah. Well, we still have 3 more minutes. I guess
Yeah.
to say the session is about to start.
The session has started, so we're live already. But
I'm guessing the talk would only start in a couple of minutes. Or...
yeah. We're only starting in a couple of minutes. I'm seeing very upsetting results for the poll I just put out. Seriously, people, what is wrong with you?
I don't know. Can I see it? I can see it.
Wow, I can't believe this stuff. I've been like fighting for years to have, top level functions always be annotated, and for some reason it's not popular. Ugh. People have not have enough instances of having to dive in a code base that they don't know without any comments. If types were mandatory, at least that sort of stuff would be easier.
I mean, this is the ML workshop.
Come on, I thought everyone had given up on inference, right?
Well, I think this is the one place. We had a few speakers, right, who talked about principality and inference, so I think it's still great.
Come on, inference is so 2000s. Now, if you add GADTs and effects and a crazy mix, like, don't you want types? Okay, well.
More than IDE features, we solved that problem. Yeah, but once you put a top-level type, then you can synthesize a whole bunch of stuff inside your term, and things are a bit more readable.
All right.
And I guess you'll be inviting the speakers to the stage.
Yeah. Okay, so let me find them. It's someone called Gabriel Scher something. Where is he? Unless yeah, there he is. Okay.
You can filter the names.
Yeah, I ended up doing it.
There you go.
Gabriel, I take it you're presenting?
Yeah.
All right. I'm closing the poll. Trolling is done. Ohad, the floor is yours. Thanks for being the session chair.
Hey, thanks. And thank you everyone for joining us for the final session of the day. And we will start with Olivier Martinon and Gabriel Scher, who are going to tell us about frozen inference constraints. And can we start the video? There you go.
I'm Gabriel Scherer, the fellow on the right. I'm going to talk about work that was done jointly with Olivier Martineau, my PhD student, the fellow on the left. This work is about frozen inference constraints for type-directed disambiguation. Type-directed disambiguation is used in many programming languages to decide the specific meaning of a name, usually the binding site of this name, based on type information that it uses site. And in general, an interesting question is how to combine this with type inference, guessing the type. If there is no type inference, it's very easy to have types at hand for disambiguation. And one excellent solution to this problem is type classes, or rather the inference mechanism that type classes rely on, which are qualified types, which provides very nice type inference through constraint abstraction. So in particular, they support ML-style generalization and provide an excellent approach for operator overloading. But there are some features of the language for which qualified types are not the right approach for disambiguation. One important such feature is the disambiguation of data constructors. So here is an example of a program, two different small programs with a data constructor K, used either as an expression or in a pattern. And many programming languages support the fact that you may define algebraic data types, several of them that have some names of constructors in common, and therefore type information is necessary to decide which of the K of the constructor K you mean. In this case, we do not want to abstract over the choice of K. So if you use qualified types and you had some function that is where it's not the inference of the function code decide does not tell you which K to use, you would get a type that is abstracted over any possible choice of K, and then the user of the function, the caller, at each call site will be able to instantiate it with a different choice of K. But this implies a compilation model where either you do a lot of compile time specialization, or you have to pass a dictionary of constructors at runtime, and we do not wish for this. What we want is that an occurrence of a constructor in the code, at a static place in the code, is disambiguated into one specific constructor at a specific time. Okay. A worse problem than that is that the type of K may not be expressible as a class argument, as a function argument when you want to abstract over it. Maybe K is a constructor for a GADT, so it can have existential type parameters, and your type system does not allow arguments to start with first-class existentials. For example, in general, data constructors tend to have typing introduction rules that can be stronger than arbitrary term-level functions. And then the final problem, which is the most problematic of all three, is that with type classes, with qualified types, the idea is that you basically have the same typing rule for all the instances of the overloaded name. Well, not for example, if you have a plus operator in the type class, you expect it to have type A to A to A for the type A of your class. So it's not exactly the same type, but you have a schema A to A to A that is used to generate all possible types for this plus in a simple way. Whereas here, when we want to disambiguate over a type constructor, well, two different constructors named K in different data types may have vastly different typing rules, and there is no schema that can let you abstract over them. So again, you cannot use qualified types. And so the talk is about other ways to solve this problem. So one way to think about why qualified types are not right here is to think in terms of the layering between type inference information and disambiguation. With type classes, what you do is that first you do the inference without making basically any disambiguation guess, and then so you have enough information from just the name and the class declarations to have the generic type or template for the type of this operator. And then after inference, you can do type class resolution from type information, and you decide the disambiguation. But for constructor disambiguation, you need to interleave the two more closely. You need the program types to disambiguate the constructor K, but you also need the type of K to infer the program types around the use of K. So you need a more interleaved mechanism. The Hindley-Miller type inference, so used in ML family languages, typically propagates type information by unification, which is a rather powerful technique. Okay, but then to implement type-directed disambiguation, a more common approach is to restrict it a bit and to use bidirectional type inference. So typically use bidirectional type inference to propagate information coming from type annotations put in by the user. They will be propagated inwards inside the term. So the root of the term has a type annotation, and then you use bidirectional discipline to push the type annotation inside the constructors, inside the term, towards the subterm, so leafwards, towards the leaf of the tree. This is a robust propagation of type information. And then bidirectional type inference will also do some sort of lateral propagation. Typically, when you have a function application, you will want to propagate information from the inference of the function, more typically, to the checking of the argument. But this is a bit more fragile, this lateral propagation, because, well, actually, there is a choice of direction. You could also want to infer the argument and then use this information to have some partial knowledge about the type of the function, for example. And if the user needs, for the particular program they are writing, a direction of propagation that is not the one that was chosen arbitrarily left to right or right to left by the programming language designer, they are out of luck. Whereas unification has this nice non-directional property that it would work in both directions. So this work that I'm talking about is a work in progress, exploring a mechanism for type-based disambiguation using unification that we call frozen constraints. So let's go back to constraint-based type inference. So the idea is it's a more declarative presentation of typically ML-style type inference, where instead of taking the program and then iterating over it, keeping some, let's say, inference information around, and at the end, voila, you provide the infer type. What you do is you split this in two steps. You take the program, it's an implicitly typed program T without most of the type annotations are not present, are not written by the user. And then from it, you generate a constraint C in some constraint language whose unknowns, whose variables, so you can think of it as a system of equation, and the unknowns are types. So more precisely, you have inference variables that will be solved into types. And then the constraint is that if you solve it, then you can read from the solution a way to annotate your original type T into an explicit type T prime, which is like the same as T with more type annotation. All the type annotations have been solved. And the nice thing with that is that with this decoupling, well, the generator is easy to read and gives you the gist of the type system for your language, and then the solver can be more tricky to implement and has a lot of freedom in terms of traversal strategies and so on, more so than if you were implementing it as a one-pass transform. For example, if you have the function application TU, here is how to generate a constraint for it, so the generator part, with return type variable alpha. That means that I want to generate a constraint such that if I solve this constraint, then the type of TU, the output type of the return type of the function, will be assigned to the type variable alpha. How do I do this? Well, first, it's an existential constraint. So I say there exists a variable beta t and a constraint variable gamma u, such that beta t is a function type gamma u arrow alpha. So the argument type is gamma u and the return type is alpha. And t is well typed and its type is beta t, and u is well typed and its type is gamma u. So when I mean is well typed, I mean the constraint that you generate from t. So if you solve this constraint, then you will get a solution such that you have a valid application of the function application typing rule, whose return type is alpha. So frozen constraints are a new form of constraints that we propose, a new combinator of constraints in this type. So they are of the form angle bracket alpha f, where alpha is a type influence variable, and f is a meta-level function from partial types, that is, types that start with a head type constructor, but whose leaves may be partial types or type influence variables, so morally parts that are still unknown. And so it's a function from partial types to constraints. Okay? And the idea, the intuition for the meaning of this frozen constraint alpha f is that the constraint will wait on the type unification variable alpha to become partially known. So when it becomes partially defined as a partial type tau, then we pass tau as an argument to the function f. We get a constraint f of tau, and we have to solve this constraint. So basically, it's a way to tell, I cannot tell you which constraint you must solve now, but let me know what's the type of alpha, the type inference for alpha, and then I will tell you what the constraint you have to solve. For example, here is how to generate a constraint for disambiguated use of a constructor in an expression in the non-GADD case, so no existential variables and so on, simple ML-style algebraic data types. So if you want to generate a constraint for KT, so T is the parameter of the constructor, with some return type alpha, you will create an existential variable beta T, ask that T will be well typed at type beta T, and then you create a frozen constraint that waits for alpha, the return type of T, to be determined. And once it is determined to be some partial type tau, you ask that beta T be equal to the argument type of the constructor K at the type tau. So the idea is that at this point you know which of the different types K belongs to, and so you can compute the argument type of K and get the precise mapping. So this is how we are expressing the disambiguation question. So this is a very principled approach. We are not guessing anything. We are waiting for the information to be available, and if the information never becomes available, we fail with a type error. So it's principled. We are not making any guess. We get a general solution, and it deals with type disambiguation. And so you can generate a constraint for constructor disambiguation, but a priori, the mechanism of frozen constraint is a bit more general and could be used for other variants of this language feature. So it's principle. It's also very restrictive. So maybe as a language designer, you want to have some more flexible typing rules. For example, maybe you want to say, well, I can look at the typing environment. If there is a single declaration of the constructor K in scope, then I don't need to wait for some external type information. Right away, I know that this is the K I mean. And so then what you do is you change the constraint generator to implement this logic to inspect the typing environment, and in this case, where there is a single K, generate a different constraint. Okay, so it's not necessarily the only way to disambiguate data constructors, but it's a combinator that can be used as part of the solution to wait on disambiguation information in a very principal way. Okay, so this is nice. We wrote some prototypes, we played with examples. It works better in a sense that bidirectional type inference for disambiguation, in the sense that it can propagate more information in places where a bidirectional discipline would possibly not go in the direction you would expect. But we found that it's also a difficult feature. It's difficult to combine with generalization. I will talk about it, and also it's a bit difficult in theory. So let me talk about these difficulties. So the first question is, okay, I said that if at the end a frozen constraint remains unfold, then type inference fails with type error. But what do I mean by the end? When is the end? Of course, at the end of type checking the whole program, well, we are at the end, and if some frozen constraints remain, there is an error. But in Hindley-Milner style type inference, there is another notion of more local notion of end, which is when you reach a generalization point. So in particular, the let bindings. Okay, what you do is you first insert the type of the definition of the binding, and then you perform generalization, which is to say, okay, what are the variables that are local to this type, and I will turn them into polymorphic variables. And in a sense, this ends the type checking of this part of the program. So there is the question of, for example, if a frozen constraint was introduced during the type checking of this let definition, what should I do? Should I fail if it's not resolved yet at generalization point? So yes, what is generalization? The idea of generalization is to look at what type variables are still local to this part of the constraint and can be generalized, turned into for all quantified polymorphic variables. And then any user of this let definition will be able to instantiate these variables with their own choice at the usage site, and which inference variables are global in the sense that they are used by some other parts of the program, and so they cannot be generalized. Okay, so this is a very common operation during type inference. So in Haskell, GHT stopped generalizing local let definitions by default in absence of a type annotation. But still, all the top-level bindings are generalized, and there are many of them. And in ML-style languages, there are a lot of generalization points. In presence of frozen variables, you have to change the generalization behavior a bit. You have to perform what I call frozen generalization. The problem is that when you look at the type tau, and you ask, okay, what are the variables of tau that I can generalize? Well, some variable beta could be blocked by the frozen constraint. What does that mean? It means that it is used. So there is a frozen constraint that is not solved yet. So the alpha that is blocking the constraint is not now. And then the function f that may generate a constraint mentioning beta. Okay. So before you solve this constraint, before you find out what the value of alpha is, and then you go working on the constraint generated by f, you don't know, for example, if beta will eventually be inferred to be a local variable or a global variable. So at this point, you don't know how to solve your frozen variable, and because of that, beta, which is blocked by this frozen constraint, is in an unknown state from the point of view of generalization. And so what you must do is to track these variables. So before, when you generalize, you end up with two categories of variables: the ones that are global, that are not generalized, and the ones that are local, that are turned into polymorphic variables. And now you have three classes: the global one, the local one, and the blocked or frozen ones that are in an unknown state. So when you generalize a type into a type schema, polymorphic type schema, you must remember what is the list of the blocked variables of this type. When you instantiate a schema that has blocked variables, what you do is you say, well, it may end up being a polymorphic variable. So I will generate fresh instances of this blocked variable as if there were polymorphic variables. But I will track these instances and say, okay, this generic schema has a new instance, and the blocked variables were instantiated into this fresh copies. And finally, when beta gets unblocked, later the typing found. So we found a value for the alpha that was blocking the frozen constraint, and then we found out what constraint f of tau we must solve, which may or may not mention beta, and then we solved it, and so we know what this constraint would wanted to teach us about the value of beta. Then we can continue generalization. So we go back to see this blocks scheme. We look at all the instances that have been instantiated, and for all of them, we update their instance of the blocked variable beta. Well, if beta turns out to be a generic local variable, then it's fine. So it should be handled as it was handled as a generic variable. And if beta was actually unified with a global variable, then you need to unify all of its blocked instances as with the same global variable. So you delay the generalization choice on beta, and then you make it after the fact once you learn the value of beta. This is delicate to implement. It was hard for me to explain. It's delicate to implement, and especially difficult to implement if you work with a type inference engine that is trying to be efficient. So it has efficient algorithm for efficiency of generalization. It uses a complex data structure, union find, and so on. And possibly it's using imperative implementation of this algorithm. And then all of this is very tricky to do. We have a partial implementation. We can try various examples, but we do not have a complete implementation yet. And finally, there is a theoretical difficulty. So first, to explain what is the problem, let me talk about how to give semantics to these constraint-based type inference systems. So the way we give them a meaning is by introducing a solution relation or a satisfaction relation. V is a solution of the constraint C. So you have to define a grammar of solution V, and then to define this judgment. And once you have this judgment that is defined, that lets you give specifications to the various parts of your type inference engine. So you can give a specification of a constraint generator, for example. A constraint generator is good if for any program T, the constraint C generated from T is such that all its solutions, V, so the set of V that satisfies C, determine well-typed explicitly version of T. So if I take this V, I can use it to annotate T, and I do get an explicitly fully annotated program that is well-typed. Okay? So there may be many different solutions, but they are all correct. So this is soundness of the generator. You can also ask whether the constraint generated is principled in the sense that there exists a most general solution. And then once you have this solution, you can use this solution relation, satisfaction relation, to define what it means to be a good constraint solver. So there are several ways to define a constraint solver. On paper, if you want, you could do it as a big step function from constraints to solution, or as a small step process that will rewrite constraints into simpler and simpler constraints until you reach a normal form constraint that can be turned into a solution. But in any case, you want to prove something like the fact that the premises of the big step derivation or the small step rewrite preserve the set of solutions of the original constraint. So if you can prove that, you have a good constraint solver. And now here is an example of solution relations for the constraint combinators we have seen in this talk. So for unification, for example, V is a solution of the unification constraint tau equal tau prime. If tau V, that is the type you get, the ground type you get from instantiating the type variables, the inference variables of tau with their solution in V, is equal as a type to tau prime V. Makes sense. And then an existential constraint alpha C, the solution would be a pair TV of where V is a solution of the constraint C if you replace alpha by the ground type T. So you can see that these are fairly simple specifications for these constraint combinators. I'm not talking about how to guess the solution. I'm only talking about how to check that a solution is valid. And so it gives you a very nice specification that you can easily trust. But then the question is, okay, how do you specify frozen constraints in this way? So the most obvious approach is to say that V is a solution of the frozen constraint alpha f if V is a solution of the constraint f of alpha v, that is applying the function f to the solution found for alpha in V. The problem with this specification is that it allows out of thin air behaviors. So for example, here I have the whole constraint I have is a frozen constraint on alpha. Okay, it's waiting on alpha. And then once you give me the value of alpha, tau, I will ignore this value and generate the constraint that forces alpha to be unified with int. Okay, and so this constraint is vicious because there is no way to know by solving the part of the constraint that is not frozen, which is the empty constraint. There is no way to find out what should be the value of alpha. But then once you make a guess, well, if you guess exactly the right value of alpha, which is int, it works. And if you make any other guess, it fails. So this constraint can be satisfied with this judgment by the solution that maps alpha to int, but it's not satisfying because, of course, our solver will not find this solution. It will never inspect the meta-level function f before having found from the rest of the constraint a partial solution for alpha. And also, it does not match the intuition of what we want frozen constraint to do, how we want them to behave. So we want a specification that is more precise and would rule out this out of thin air behavior. So we want to say that alpha v must be determined without looking inside f. Okay. So morally, one way to express this would be to say, okay, if I have a constraint C that contains a subconstraint frozen alpha f, then to be a valid solution of it, V, I ask that first V is actually a solution of C of f of alpha v, so as before, but also that C top, so replacing this frozen constraint by the trivial constraint top inside C, gives me a simpler constraint that determines alpha. So I want this simpler constraint to fix a value of alpha, such that, well, one way to state it would be to say that all the solution of this constraint, for example, give a value to alpha. I don't exactly know how to define this precisely. In fact, I don't think that this is the right way to make this precise, but this is the idea. Okay, it's a sort of local principality condition on not the whole solution or the whole type, but just alpha, which is sort of related to the way in which some work on type inference have to locally require that a part of the solution be principal to justify their inference choices. So this is not so nice. It feels a bit like a hack, and the question is, okay, is there a nice way to specify the semantics, the meaning of this frozen constraint without allowing you the out of thin air solution? What's a way to express this and to have a good match between the specification and the implementation? So to summarize, frozen constraints are an interesting, powerful, but difficult constraint combinator that we propose for type-based disambiguation, and this is all a work in progress. Thank you for your attention, and we will be happy to deal with questions or to get advice on how to solve in particular this second problem. Thank you.
Let's thank the speaker. So there's a question by Didier about in what sense the rule for KT alpha is principal. So you touched on it a little bit on what does it mean for the solver for the solution to solve, but can we think of it beyond just the implementation, but somehow as a more abstractly?
So yeah, I don't have a better answer than the one I gave in the chat, which is well, one formal way to talk about principality is to have such a solution judgment and to prove that you have a principality in this precise sense. And then people can complain about the solution judgment that you took as being too algorithmic or whatever. But we are not at this point yet, as I explained. So we cannot make a precise claim. But I think it's principle in the sense of not making any guesses, which means that in any sensible specification we will end up with, it will be principle. Well, let's take this as a conjecture, but it's a strong conjecture. And for example, the judgment I showed, which was too naive because it did allow for this out of linear behavior, is still it coincides with a better judgment in all the cases where the implementation, the solver, will actually accept the constraint. So we can still look at the set of constraints, and I haven't done the work. We haven't done the work of checking this in details, but I expect that we wouldn't have principality in this relation. Well, Olivier and I did some informal proofs in the specific case of constructor disambiguation, so not all uses of frozen constraint, and there we have a principality argument that is formulated modulo. So we are principal among the solutions that are stable to the addition of new data type declarations.
Okay. There's a question by Matthew Flirt.
Yeah. So the function for the frozen constraint, the idea is that it's implemented in the meta language of the solver. So in our case, we have a constraint generator that is implemented in OCaml and will pass a OCaml style callback. Well, there are some details to look at maybe at the extended abstract, but so it can be very complex. I expect in the meta theory that you need a sort of monotonicity property. I mentioned that in the chat, so that if the type of alpha gets more precise, then the constraints you get gets more precise in a sense. But that would be meta theory for the system to behave well in theory. Even without this property, it behaves well in practice already, at least for the use cases of data constructor disambiguation, because it has a property that as soon as you know just one bit about the type, which is the head constructor, so it starts being just an unknown variable, and as soon as it's not an unknown variable, you can look at the head constructor, and that is enough information to determine what is the output, the return type of the constructor, and therefore how to resolve the constructor, how to disambiguate it completely. So it's a very nice use case for this feature. If you wanted to use these frozen combinators in other cases, like, oh, I really want to know that I have a pair of integers and not a pair of something else, what you would do is to write a nested frozen constraint. So first you freeze on the top level variable, and then you check that it is a product, and then you freeze yourself on within the callback. You create a new frozen constraint on the two leaves of the product node, and you check that they are integers. So you can nest those to look arbitrarily deep in the type in a robust way. Sorry, I have a last thing to do. It's not the same thing as a disjunction. So, and this is an important distinction and question. The problem with thinking of this as a disjunction on all the top level type constructors is that first it depends on what is in your type environment right now, and people in practice tend to open new modules and to add new type constructors in the scope as the program evolves, and you don't want the inference to change too much. And also, as a specification, it encourages you to do backtracking, which is well, not robust and probably not a good idea for type inference. Whereas our specification, which is that it's not about trying many cases that exist. We never make guesses as long as the information is not forced on us from the rest of the constraint solving. I think it's much more robust and can be implemented more efficiently, and is also gives better inference behavior.
Okay, thanks. So in the interest of time, I'm gonna let's thank the speaker again. But I know this is a very active and interesting topic, so we could definitely continue in the social lounge discussing this. And let's move on to the next talk, please, which is by Scott Flaschet, who's going to tell us about an experience report, the domain modeling with F#.
Everyone, this is my experience of report on using F# for business domain modeling. My name is Scott Voloshin, that's my Twitter handle, and I also have a website called fsharpforfunandprofit.com. So just to sort of set the stage, I wanted to differentiate between languages with a mathematical focus and languages with more of a business focus. And of course, on the mathematical side, we have proof assistance, we have functional programming languages, and so on. On the business side, we have COBOL, and nowadays we also have Java and C# and so on. Now, I've had very good experience using F# as a business language, basically using F# as a replacement for COBOL or Java. And so that's what I want to talk about today. So in business-focused development, it's slightly different emphasis than other types of development because understanding the domain is the most important thing. We have stacks of paper, you have policies, you have rules, all this stuff needs to be understood. Getting it correct is actually not as important as getting it right, as understanding what you're doing. And the other thing is these policies and these rules change all the time. So responding to feedback is very important, and you need to adjust your domain model as things change very quickly. So F# is fantastic for this, I think. First of all, the code is very readable by non-developers. I'm going to be using types code. I'm not talking about the implementation in detail. And it's very easy to collaborate with non-developers. I use composable types for domain modeling. I call them composable. You'll see why in a minute. And of course, we've got type checking. It makes it very easy to refactor and change things as the rules and the policies change too. And finally, I want to quickly talk about how you can eliminate errors through at the design time rather than at runtime. And this is often called making illegal states unrepresentable. So let's start with collaboration. I use a process called domain-driven design, and let me just give you some background on that first. Traditional software development was using something called waterfall methodology, where you had domain experts who would talk to analysts, who would write up requirements, who would talk to other people. Eventually, it comes down to the developers who write the code. This is really a bad process because there's no shared mental model, there's no feedback, there's no chance to fix misunderstandings. So often these projects fail due to misunderstandings between the domain experts and the actual code. Now, what's happened in the last 20 years or so is agile methodology, which is much better. It encourages the domain experts and the developers to talk to each other and to have frequent deliverables and fast feedback loops. So that's much less likely to have problems. However, even in agile, the code is still the developer's version of the code, and developers can often mistranslate their understanding into the code. So in domain-driven design, the idea here is that everybody involved has the same shared mental model. There's a shared mental model which the domain experts use, the developers use, shared language, shared concepts. Everybody is using this same mental model. And in my experience, if people do not have the same shared mental model and they do not use the same words and same concepts, the project is very likely to fail. In my experience, more projects fail due to misunderstanding than things like correctness. Correctness is not normally the reason why projects fail. And also, in this design, the code is part of the shared mental model. The code also has the same shared language and the same shared concepts. So people immediately say, well, how can you make code, represent this code? This is what people think code looks like, right? Code looks impenetrable. But let me show you the kind of code I'm talking about. This is the kind of code I'm talking about. This is domain-driven code. And even if you know nothing about F#, you can understand what the concepts are. We have our shared language. The shared concepts are the type definitions, basically. So it's just really easy for non-developers to understand what's going on here. One thing I should just point out is not just data, but I'm using function types to represent business workflows or stories that people need to do. So here I have to deal a card or to pick up a card. These are activities or verbs that I'm modeling with function types. So when I do my domain modeling, I actually work with non-programmers and they can understand this. And in fact, one person once said, there's great documentation, but where's the code? So that was nice. And the other thing is that when you're working with domain experts, they can actually give you useful feedback, even though they're not a programmer. So if you're a poker expert, you would notice straight away that there's actually a deliberate mistake in this design. And a poker expert would point out straight away that you've missed out the ace. And without having to be a programmer, they can give you feedback on the domain, whether you got the domain right or not. Now, as I said at the beginning, getting rapid feedback is a really important part of the process. And rather than getting feedback in days or months, it's really nice to get feedback in minutes. So when I do my domain modeling process, I actually do it as a collaborative process. We have a shared room, and I'm presenting onto a whiteboard or onto a projector or something. Everybody is in this room, not just the developers, but the domain experts, the testers, the product owners, all their stuff. And what happens is I type up, as we work through the domain model, I type stuff up on the screen, and everyone can see what I'm doing, and everyone can give me feedback. So I would say, okay, this is how you deal. This is how I think you deal. And one of the domain experts might actually say, that's not right. We don't deal in poker. We don't use a normal deck. We use a shuffle deck. And I say, oh, okay, a shuffle deck. So I put down a shuffle deck. And they say, yeah, that's right. And then I say, okay, so what is a shuffle deck? Well, it's just a list of cards. So I write down that. So I've learned a new concept that I didn't necessarily know before. And then I might say, well, how do you create a shuffle deck, right? Well, they will say it's really obvious. You shuffle. So it's obvious to the expert, but it's not obvious to me as a developer who's not familiar with the domain. So I now have this concept called shuffling, where the input is a deck and the output is a shuffle deck. So I've just learned 2 new concepts in a couple of minutes of discussion with people that I might not have known before, and would have actually been a bug. Really, using an unshuffled deck could actually be a serious bug in a poker game. So this is an example of the design process happening fast, interactively. We haven't written any code yet, but everyone is sharing knowledge. Everyone is becoming expert in the domain. Now, the way I explain domain modeling to non-programmers is calling it a composable type system, right? We're using an algebraic type system, but I prefer to call it composable. It sounds a little less scary to non-mathematicians. So, and I explained that you can build bigger types and smaller types using and using or. So and would be a product type, a record type, and or would be a sum type. I like to call them choices. So here's an example of how I might actually do this. I might say that we have requirements to accept 3 forms of payment: cash, PayPal, credit cards. And for PayPal, we need an email address, and for credit cards, we need card type and card number and all the other information. So how would I model this in F#? Well, I would use this compositional approach, right? I'd start off with some simple types. I would not use primitives. I always like to wrap to put an alias around the primitives, because people do not talk about strings and floats. They talk about email addresses and card numbers and so on. So we have our aliases. We have a choice, Visa or MasterCard. We have a record type, a card type, and a card number, right? So I'm using a choice and I'm using a record here. And then the payment method would be a choice, right? Cash or PayPal or card. And again, I would call this a choice type to people. I wouldn't call it a sum type or a co-product, right? I would just call it a choice. We can keep going. Of course, you just keep going and going because it's composition. I can add some more basic types, and I can say a payment is an amount and a currency and a payment method. And so what I've done here is I built a big type from a bunch of smaller types. And I find that, again, working with non-developers, this is actually fantastic. They find this very easy to understand. It's actually a much easier model than object-oriented programming for them, actually. It's also very easy to change because, of course, this is actually the all static type. So if I change something here, I get the rest of my code fails to compile until I fix up the errors and so on. So it makes it easy to understand, but it's also very safe from a programming point of view. So the final thing I want to talk about is how to eliminate errors through the design process. And this is often called making illegal states unrepresentable. So here we have an example of an email contact where we have an email address and we have some sort of flag to prove that they've been verified. Like, you know, when you sign up for something, they send you an email link and you have to click the link to prove you own that email. So there's some business rules associated with this. The first rule is if you change your email address, you have to set that flag back to false because it's not verified anymore. And the second rule is that you should really only set that flag when it's gone through the special verification service that you've actually proved that you've clicked on that link. So that's not true with this design because anyone can set that Boolean flag. So this is it's a bad design. It's insecure. You could easily have states in this design which are not meant to be occurring in the real world. So how can we fix this? I'm going to refactor it. So the first thing I'm going to do is create a new type for the email address. I'm going to wrap a string, and I'm going to use a single case union for that, or I could just use a very simple record type for that. But there would be some sort of associated smart constructor which would validate the email address, make sure it has an @ sign in it, and so on. The next thing I'm going to do is create another type for the verified email, and I'm just going to wrap a normal email address. The reason I'm doing this is because a verified email is a different concept in the domain than a normal email. It has a different behavior, different business rules around with it. Next, I'm going to model the verification service, and I'm going to say that is something which takes in an email address and some sort of hash as the input, and the output is an optional email because it might not work. And then finally, I can go back and I can refactor this email content information to be a choice between unverified and verified. So I've got rid of the Boolean and replaced it with a choice between two cases. Now, in the unverified case, I can create that case. All I need for that case is a normal email address, so that's not a problem. But to create the verified case, I have to have a verified email. And with a little bit of tweaking, I can ensure that the only way to get a verified email is as the output of the verification service. I can make it an opaque type or something like that. So if I do this design, I've now enforced the business rules automatically. It is not possible to, if I change my email address, it has to be unverified. And the only way it can be verified if it's gone through the verification service. So I don't have to write any tests. I literally can't have a bug where I have done the wrong thing. So this is really, really nice. So just to summarize, I think algebraic types are excellent for business-focused domain modeling. Non-developers can really contribute to the process, and I think that's key to the success of a business project, of an enterprise-type development. And finally, I think there's so much potential for ML languages here. There's a couple of things that would make my life easier, like make it easier to do smart constructors and so on. But I think there's a lot of potential, and I've actually written a whole book about it called Domain Modeling Made Functional. So thanks very much.
Thanks, Scott. So I don't see any questions in the chat, but I do have a quick question before we set up for the next talk. So you talk about non-developers participating and even contributing. To what degree did you get them to also sit down and write code? Because I know F# has a lot of web programming and interfaces and so on.
Yeah, it's writing actual implementation code is always much more complicated. And I know there are some places like Jane Street. They have the traders review the trading algorithms, which is written in OCaml. I think the average person does not want to look at weird algorithms. It's too complicated for them. But I think just getting the domain, in my experience, most problems are due to not having bad algorithms, but having bad understanding of the domain. So changing algorithms is not really the problem. It's just literally doing the wrong thing. Like in my example, using an unshuffled deck instead of a shuffled deck. That's a serious bug, and it's the kind of thing that you'd learn about from a domain expert.
Mm-hmm.
Yeah.
Okay, thanks.
Thank you very much.
Let's thank Scott again. Always welcome experience reports, and move on to the next talk, where Clément, Gabriel, and Lore would tell us about isomorphisms, making another appearance.
Alistair, I'm going to do a short.
Sorry, yes, I'm Sylvester. I switched.
No, that's me. I'm still struggling to find the video. Give me 1 sec. Sorry. Is it this one?
And I'm going to present how.
Sorry about that.
Yeah, that's the right video, right, Ohad?
Yeah. Sorry about
Thanks.
that. We'll work on search by types in libraries and how to make it scale. This is joint work with Clément Alain and Laure Godin. Every programmer has encountered this problem once before. You're looking for a function, you know what it should do. For example, you want to convert some time to a different time zone, but you're not sure where to find it and what's its name. There is an intuitive approach to this. You want a function on time, so you're going to look in the module named time. Unfortunately, it doesn't always work. The function could be in the date module or in the time zone module or something else. There is an alternative approach to this. Behavior are hard to search for, but there are abstraction of the behaviors that we can search for. And in particular, there is a very, very familiar abstraction for us, the type of the function. And so we've built a tool called dosing, which allows to find function by their types. For example, here I'm searching for a function with a type alphalist, alphalist.alpha arrow pool. And it's going to find the function list.mem with slightly different type, but very similar. Here the arguments are just reversed, and then it's curified instead of uncurified. And so our procedure find types up to order of argument, instantiation of variables, and names, and so on and so forth. It knows about packages and libraries, and in particular it scales to modern ecosystems. So for example, we can search all of OPAM. There are several existing approaches to this problem. The first is search by type modulo isomorphism, which we will describe in more detail later. The good thing is that it's sound and complete, which means that we will find types and functions that actually correspond to the query we entered, and we are going to find all of them. The problem is that it's very computationally intensive to the point that it doesn't scale at all to big modern ecosystem. Another alternative approach, which is very popular in the Haskell community, is Hugel. The problem is that Hugel is neither sound nor complete. It's more akin to a text search in types. It doesn't really understand the semantic of types, but it scales very well, and it works on the whole Haskell ecosystem. So what's search by type modulo isomorphism? Given a type tau, it finds all functions in the libraries with types which are equivalent to tau in some capacity, either equivalent, matching, or unifying, and with a set of simplification, which we call isomorphism. And here we will choose these four isomorphisms. First, we're going to consider tuple as commutative and associative. We are going to consider unit as the neutral element on tuples. And finally, we will consider types up to curification. So here it takes tuple A, B and returns C, or A returns B, returns C. And those two types are considered equivalent here. The problem is that with these isomorphisms, unification and matching are very, very expensive, so matching is NP-complete and unification is p-space for two types. So we can't use directly this procedure for an exhaustive search. So what can we do? First, some remarks. When searching, many types do not match. This is expected since if you're looking for a query, there are lots of types which are not related to it. The problem comes with the second point, which is that when failing, unification is still very expensive. And finally, a third point is that performance of unification highly depends on the types. And there are some types, which are not necessarily the big types, which cost a lot to unify with, or to attempt to unify with. So, given this constraint, we've devised a methodology for our work, which is first to experimentally measure to identify types taking lots of time. We then introduce shortcuts to try to skip unification for these expensive types, trying to decide quickly without resorting to the full unification procedure. Then we pre-process the database of types to compute these shortcuts in advance. And finally, we repeat the process until we've exhausted all the bottlenecks. Here is an example of metric, the head. So the head of a type is the nature of the right-hand side. So here the head of unit to alpha is variable. The head of into list of alpha is the constructor list. We can ask our tool to do statistics when we search for a type. So here into int, and we classify the time, the resulting time and number of unification by head. So here are all the unification for variables, here for constructor, and so on and so forth. Here we can see that a very large majority, 95% of the types are done, do not have a variable at the head, but types with a variable at the head take lots of time, much more than the others. So our goal here is going to try to classify the head to avoid the cases that are pathological. And we can do so because if two heads are not compatible, then the type will never unify. So we can pre-compute the heads for all types and store them compactly in order to do this very efficiently. And if we do a search in a local installation of OPAM on my computer, so around 250 packages and 31,000 functions, we can see that we avoid making lots of unification. So the percentage here is the percentage of unifications that were avoided by this shortcut. And we can see we avoid many unification, except in the case where the query itself has a variable at the beginning. In this case, we do not gain anything. So we correctly avoided many unification in the cases that are not too polymorphic, but we need to work more for polymorphic cases. And so we have introduced more shortcuts like this, in particular some that are better at polymorphic queries. In particular, the number of variables at the tail of the function is pretty good at this. It allows to classify polymorphic functions by how polymorphic they are, and we can cut them. And we plan to investigate and add more of these shortcuts. And now we have many shortcuts. How do we combine them? So to combine them, we use a trie-like structure of features. So the head is a feature. And we, given a query, here, for example, we have a constructor called f. We can select all the subtries with potentially valid types. So a constructor f will never match a tuple. So we can just cut all the tuples directly, and we can cut the subtries containing tuples and only consider the subtries that interest us. And we can stack those trie, and that's how we combine them. So with all the features we've gathered so far, we can do a benchmark, which is presented here, on a database containing containers, batteries, and bays, which represent quite a lot of functions already, 10,000 functions. And we can see that on many of these queries, we obtain times that are less than a millisecond, so under what a human would consider instant. And for more polymorphic types, then it takes more time, but it's still very quick. And so in practice on simple queries, it already works very well. And we can work more on very polymorphic queries. So to conclude, we presented dowsing, a new approach to search in libraries by types. It is sound and complete, and we've formalized our unification procedure, how our shortcuts, and proved the soundness of the shortcuts. With our method scales to medium ecosystems, and we hope beyond with additional work. And in particular, the most important bit is that we now have a good methodological approach to improve this further by measuring the bottlenecks and finding new shortcuts from them. And so everything is formalized and implemented. You can look at it on GitHub. But there are still lots of work to be done to make this practical and to develop it up until it's an actual usable tool by the OCaml community in particular. And so on the indexing front, we hope to add more features and to invent new kinds of shortcuts to make it even faster. On the type system aspect, we need to add more OCaml feature. So far it supports basically the SML fragment of OCaml, which is fairly limited. And there is lots of software development work as well, in particular if we want to plug this into the OpenCI and develop the web frontend and have a database that serves queries for the whole of the OPAM ecosystem. And so if you're interested in this, please reach to us, and I hope we can make this an actual tool that will be very good for the OCaml community. Thank you very much.
Let's thank Gabriel. So there's a question from Jeremy Gibbons. There you go, I can see you. So is the cost of unifying two types to you always a function of the pair, or maybe you can break it down to maybe an additive cost or multiplicative costs, somehow simplifying it? I assume that's what he means here. Or maybe you can pre-compute it for T, and then you can, it only depends on T, it doesn't depend on you too much.
So that's sort of a good question. I don't actually know, and I'm not sure people have studied this in this light. I know that for some T, it's always going to be simple, and for some T, you can exhibit catastrophic use. And it's pretty hard to know in advance. It depends on both types, I feel. So yeah, I don't think people have studied it. I've studied a sort of parametric complexity of this problem. It would be interesting, but experimentally we can answer that it depends on both.
Yeah, I mean, the databases will be the starting point to see if someone has done something similar in terms of matching. Yeah. Okay. I have a question. So sometimes when you look at other types, you just look at pairs and functions, but if you look at user-defined types, right, some of them are very specific, and so you probably don't want to look at them beyond nominally, but sometimes they're a bit more structural, say option type, right, or is another one you can just reuse. Do you have any thoughts how you might take advantage of or try to match that? So someone is saying, okay, I'm giving you a pair of functions, but really you could have given me a pair out of like a function out of bool or something like that, or have another argument that's a Boolean type. So taking advantage of more isomorphism on user-defined types.
Right. Okay. So so if I understand correctly, what you want would be, for example, you're looking for, for example, an option, and you will automatically find types that are functions that uses types that are isomorphic to the option. Is that right?
The argument is an option, but actually it's okay to find a function that takes a default argument and the
right.
The value.
Okay. So yes, it would be interesting. The problem is that every time you add a new isomorphism, you creep towards undecidability. And so it needs to be on a case-by-case basis. It's very hard to answer in general, and it's really easy to tip over and end up undecidable. So, but yes, ideally I would like to have that. Maybe we can do that only for matching. For matching, it's a bit nicer, but for unification, it's going to be indecidable almost immediately.
Didier is asking a related question. Would there be any improvement if you try to normalize that in some way?
We do. We normalize a lot according to our equational theory. So yes, we do that, and it helps quite a lot.
Great. So let's thank Gabriel again.
Thank you.
To the next talk, Sylvester, the unified type notation for symbolic mathematics improved by Alistair Behari.
I'm going to do a short talk today on Sylvester. a unified type notation for symbolic mathematics and proof. So when we talk about doing symbolic mathematics today, there are two general program classes. The first is computer algebra systems, and these allow us to do operations like algebraic simplification, expansion, transformation, and rewriting. We do things like symbolic differentiation, integration, linear algebra. We can do things like solutions of different kinds of equations. We can do things like series and limit operations, and we can also do graphical plotting and visualization. So here's an example of a computer algebra system. This is the Maxima CAS. It's a really popular open source computer algebra system. This is Maxima again, doing some equation solving and visualization. This is the Mathematica CAS. This is a really popular commercial CAS. And this is SageMath, which actually uses Python as its interactive programming language. This is another popular open source computer algebra system. So the second category of symbolic mathematics programs we can talk about are theorem provers. So with theorem provers, we do things like theorem proving from axioms, inference rules, tactics. We can talk about things like the satisfiability of a Boolean formula. We also do things like constraint solving in integer arithmetic or real arithmetic in the context of optimization problems. So this is an example of a theorem prover. This is the Lean theorem prover. This is actually running inside Visual Studio. Lean is a really popular open source theorem prover. This is Lean again, proving a theorem on prime numbers. This is the Isabelle theorem prover, another popular open source theorem prover. And this is Z3 from Microsoft, which is an SMTP theorem prover. And this is also a really popular solver for doing things like optimization problems and satisfiability problems. Now, if you think about the language of these different symbolic mathematics programs, so in the examples we just saw from Mathematica, Maxima, and SageMath, the languages, they generally tend to be script-oriented. They're untyped or dynamically typed. They're interpreted. They generally lack robust modular namespace support. These are not general purpose programming languages. They are really specialized languages. They tend to lack things like user-defined algebraic data types, classes, operators. Again, they're not really general purpose programming languages. And they can also lack things like first-class functions, pattern matching, sequence comprehensions, and other features of functional programming languages. We can contrast this with theorem provers. Theorem prover languages tend to be really sophisticated, and they have features like dependent types, but they tend to have a relatively small developer community and relatively limited commercial adoption compared to more mainstream languages like F# and OCaml, Haskell. So the basic research question that Sylvester tries to answer is, can we use a mainstream functional language like F# as the interactive programming language for both a computer algebra system and a theorem prover? So let's look at Sylvester in action. So this is a Jupyter notebook running an F# kernel. So we're going to load up the Sylvester libraries in our first cell. And the next thing we're going to do is we're going to initialize the Maxima class. So we want to use Maxima as our computer algebra system, but we want to use F# as the interface to Maxima. So we started the external Maxima process. So all we have to do is open up our algebra module. First, we can declare two symbolic variables here we can reuse. So once we declare these variables, we can reuse them. Now this expression is an F# quotation. An F# quotation, this is the main vehicle of symbolic expression that Sylvester uses. So you see here, this quotation evaluates to this structure. And this structure is really similar to an S expression in Lisp. So there are a lot of different operations we can do on these symbolic expressions, or we can just do a simple simplification. We can also do things like a partial fraction expansion. Yes, here, so we're expanding this as partial fractions with regard to the variable r. Now here, we have a simple integer function. This is an ordinary integer function, but by using the formula attribute, we can have access to the symbolic structure of that formula. So if we expand that function f as a quotation, we get the symbolic form of that function. And we can use this function to do things like we can make a numeric sequence from that function. These are just the values we're feeding in. But we can also have we can also make a symbolic sequence. And we can also make a symbolic sequence of functions. So this is, we're just using the same f function that we just defined, and also a symbolic series of functions. So here we just created a series of functions. So the next thing that we can do is we can try to use Microsoft Z3. So we want to use, again, just like how we use the Maxima CAS as an external tool, we want to use a Z3 solver, but staying within F# as the language. So we create an instance of the Z3 solver. We can then do things like check the satisfiability of a formula. So this particular formula is not satisfiable. There's no integer where the square root of the integer is 2. We can also do things like solve equations. So this equation system is a simple equation system. It has a simple solution. And we can use Z3 to find the solution to that system. So we're using both Maxima and Z3, but we're using it within F# and within Jupyter Notebook. And we're using the same notation, the same syntax for the different expressions, symbolic expressions that we want to operate on. So what we saw basically we can do with Sylvester is we can use F# types, classes, functions, operators, sequences, and other syntactic features to represent these mathematical and logical concepts. We can use F# quotations to represent symbolic formulae and expressions and have access to the symbolic structure of functions and expressions. And we can interoperate with external programs like Maxima and Z3 using metaprogramming. We can run this in any F# environment, whether it's IDE like Visual Studio Code or Jupyter Notebook. And later on, we'll see how we can use visualization libraries to actually visualize some things like functions. So one of the things that some of the things Sylvester designed to do is we want to have a unified language for doing these kind of operations in symbolic mathematics and logic. And again, we have a unified interface to these tools, Maxima, Z3, the Prover9 theorem prover. And we want to be able to take advantage of the different language tools for F#, Visual Studio Code, Jupyter Notebooks. One thing that Sylvester is not trying to do is we're not trying to do algorithms for high performance numeric computing or algorithms for symbolic computing. We're delegating all of the symbolic operations to programs like Maxima and GAP, to those specialized programs. So let's look at some of the functions in the Sylvester math library. So we can look at, for instance, probability. So in this case, we're using a finite sequence. We create a finite sequence from a set of values. We then create a probability space from the Cartesian product of those values. We use a first-class function. We just define P as a probability measure for that particular probability space. And here we define a subset. So we're using F# quotations to define a subset of that particular sample space. And this has a finite cardinality. The size is 6. And then so basically once we have a finite size, we can find the probability of that particular event. And here we just do the same thing. We just do another subset. In this case, we're saying we want to find a subset of values where the sum of the two dice rules is 8, and we can just find the probability of that. So these are all types and operators coming from the probability library. You can use Sylvester in things like probability. For linear algebra, the interesting thing about linear algebra is that we're actually using type level arithmetic. So we're defining a vector as a vector of length 4. And this particular vector, the type is actually encoded, the length of the vector is encoded into the type. So we have a vector here, we're declaring a matrix as a 3x4 matrix. So this is a fully symbolic matrix. We can use our variable declared above, our symbolic variable. So now, if we try to multiply m by n, now these two are conformable, but if we try to multiply it in the opposite direction, what happens is we get a type error because those actual matrices are actually not conformable for multiplication in that particular order. Now, in this particular, what we do here is we have a vector and we want to augment a matrix with that particular vector. So again, we use this custom operator to be able to create a matrix. So this is actually, we created a 4x4 matrix. We have augmented a 3x4 matrix. So we created this 4 matrix by using that custom operator. And again, those operators only work with the particular type level dimensions. So the dimensions don't actually work if these dimensions actually don't match. Okay, so this is the type. So this is getting a type error when you try to multiply it in this we try to multiply this non-conforming way. Okay, so here we have an example of real analysis. And we're doing just things like just as we saw differentiation, integration. Here we're actually doing visualization. We're using the XPlot library to visualize. And again, we're using the same common structure that we used before of an expression function that has a symbolic form. Okay, so the very last thing we're going to talk about is just talking about the symbolic logic. So Sylvester uses a theorem prover called SILF, which is an equational logic theorem prover. So SILF is an equational logic theorem prover. It's an LTF style theorem prover where you have particular data structures for theorems, and you're not allowed to construct those data structures or those types if you don't have a valid proof. It uses equational logic, fuzzy logic from a logical approach to discrete math by David Grice and Fred Schneider. And equational logic allows us easy integration and proof replaying from automatic theorem provers like Proof9 and Metis. So you can just look at an example of symbolic logic here. And so we have a theorem in propositional calculus that we want to prove using SILF. So again, we're using F-sharp quotations to try and prove this theorem. Okay, so this is our theorem that we want to prove. These are the rules that we use. Okay, and this is the complete proof that gets printed out. Now, in addition to SILF, we can also use Z3 to find counterexamples. So in this particular case, for this particular formula, we see that there's no model that exists for the counterexample. So we know that this particular theorem is a valid theorem, and we see that. So this is just the distributive rule for multiplication over addition. So this particular rule is axiomatically true in the theory of integers that SILF has. So we can try to do another proof of a simple integer formula, but in this case, if we don't complete the proof, then we can't construct a theorem. So this actually throws an exception, just like what LCF theorem provers do, if we don't provide a complete proof. And this is another theorem. This is another theorem in predicate calculus. This is a longer theorem that shows more of the features of SILF, different tactics and rules, and lemmas and things like that. So this is a much longer proof. So what we've seen is we can use F-sharp quotation as a common symbolic notation for symbolic expressions. We can use F-sharp as a language for doing symbolic mathematics and proofs and visualizations. And we can delegate the computer algebra system and logic operations to external tools and libraries, and just use F-sharp as a unified language interface to these tools. And we can contrast how Sylvester does these things with computer algebra systems and theorem provers like Mathematica, Maxima, SageMath, and Lean. And I think we'll see that in terms of just the language itself is far more capable than the languages of these tools. Sylvester is definitely a viable option, a viable alternative compared to using languages from these tools. So for more information, you can check out the GitHub project, and you can also get me on Twitter at Alistair Bihari. So thank you very much for listening to my talk.
Thanks. Thank you, Alistair. So I have a question. So it's very cool how you bring all these different components together and how F-sharp lets you use them all together. And of course, it's nice to see an ML language used for theorem proving. The language it was developed to use as. Some of these projects that you kind of trying to interface with are multi-year, multi-person kind of efforts. Is Sylvester more of a concept, or is it going to be, it's going to take over the world of symbolic mathematics by somehow having an edge over those projects?
So could you repeat the last word? I didn't catch the last part of the question.
So it's bringing all these projects together, but some things it has to redo itself, like all the algebra system and all the theorem proving and all the libraries. Coq has been around for many decades by now. Right? And it has quite extensive libraries. So is Sylvester bringing an edge over that, and what is it?
Right. So there are two things. Sylvester, as far as doing the theorem proven part, well, like I said, it's going to be relying on external automated theorem provers. So it's going to be relying on theorem provers like Metis and Proof9. Now, the whole point of doing Sylvester was more of a pedagogical focus, as in like basically learning mathematics. Yeah, I mean, languages like Coq are really, really sophisticated. These are multi-person, multi-year efforts. So, you know, anything that Sylvester does can't really hope to compete against Coq right now. But in terms of simply just learning mathematics, just learning, you know, things like real analysis, probability, I think that definitely it can offer something, because equational logic, one of the reasons I chose equational logic for the theorem proof in itself was that it actually, the proofs are actually oriented towards basically teaching and understanding. And so compared to using logics like Coq, so as far as just simply for students or teachers who want to learn mathematics, teaching mathematics, that's really what Sylvester is targeting right now.
Thanks. And we'll have to keep it at that, but we can continue the discussion in the social area. That's a question from the previous session. So thank you, Alfred. The next talk is by Haneli, who's going to tell us about the data-centered user study for JS Coq. And while we set up the video, maybe another special thanks for Haneli, because she's been doing a lot of work this week to make this conference and workshops run smoothly. So yes, I can see a lot of love happening on the screen. So thank you, Haneli.
Yeah, I really wish to second that. I'm so glad you're saying something about it, Ohad. And Haneli has been doing like an incredible job. And I feel really bad that I've sent so many emails and every single one of them has gotten a response or I've gotten help within 30 seconds. Like the server, like the quality of service is incredible. Thanks.
Thank you.
Hope you're all enjoying ICFP 2021 and its co-located events, including the ML workshop. My name is Haneli Tavante. I am a master's student at McGill University, and today I will be talking about a data-centered user study for JS Coq. I would like to start this presentation by asking the following question. Are the tools we use to write proofs any good? And what exactly do I mean by good? According to a NISTA paper from 2006 from Marat Bosher-Nitzan and their collaborators, there are 3 principles for designing a good tool, at least when we talk about tools for writing code in imperative languages. The principles are the following. First is applicability. That means the tool should be able to support real-world applications. The other principle is about scalability and performance. That means when you come up with a production-ready application, your tool should be able to continue to support you the same way it would support if you're just writing a toy application. And the next principle is about usability, which we're going to discuss in detail on the next slide. According to the same authors, when we talk about usability, at least usability in programming environments targeting imperative languages such as Java, there are 3 main directives. The first one is that the tool should be intuitive to use regardless of the user's expertise level. That means a beginner should be able to use the basic functionalities of the tool the same way an expert is capable of using them. The second aspect is about an integration with a pre-designed workflow. For example, when developing a web application, it is expected that the user is going to write some code, refactor it, and push it to production. That's a pre-designed workflow, and the tool should work according to this kinds of pre-designed flows. The third directive is about support refactoring. So that means your tool should be able to help you to rewrite some portions of your code. Since the tools we write are also programs, it is expected they will have issues, and user studies are a good way to detect usability problems. There are basically 2 categories of user studies we can think about doing. One of them being based on qualitative research and collecting metrics from small groups of users. For example, we interview a user and ask how they feel when they use a certain tool. The other way we can think about is creating or formulating hypotheses and confirming them from large data sets. These 2 methods have been applied to tools targeting imperative languages. What about the usability in user interfaces for theorem provers? At this time, there are some studies who target qualitative research, but when we talk about creating hypotheses and confirming them from analyzing large data sets, it looks like we can't do it because apart from GitHub and open projects on GitLab, we don't really have any other open large data set of proofs. So in this talk, we're going to show you how to actually build one of these large data sets using JSCoq, or better saying, a modified version of JSCoq, and which hypothesis one could try to extract from such dataset. If you're not familiar with JSCoq, it is an online interface where you can write your Coq programs directly from your browser. You can give it a try by hitting jscoq.github.io. This is how it looks like. For generating the dataset, we are going to use the same JSCoq you saw in the previous slide, and we're going to wrap it around the Docker Compose. Then, every time the user interacts with one of the arrows at the main panel, either by clicking on them or by using a shortcut on the keyboard, we're going to trigger an event to a Node.js instance. And then this Node.js instance is going to persist the event on a Mongo database. As a side note, at McGill University, a similar strategy has been used to generate large datasets of OCaml programs coming from the LearnOCaml platform. I will leave a reference linked on the slides if you're interested. Every time the user performs one of the events at the main panel, it will generate a record on a Mongo database. This is how each record looks like. It has a timestamp to indicate when the user performed the action. It has all the content coming from the Scratchpad, and it also has information about the user agent, namely what kind of browser the user was using when they performed the action. Every time there is a new event from the user, apart from what we just showed, we also generate other types of records on MongoDB. So we also collect the status of the running workers. We also collect all the information on the Goals tab, and we also collect all the information on the Messages tab. When we analyze the data, what can we do with it? First, we can use the data for educational purposes. Maybe we can analyze this data and draw conclusions about how can we improve JSCoq or similar tools in order to help students trying to learn Coq. Next, we can also use this data to detect bugs on the current interface. For example, if there is an issue with a certain browser, let's say Safari or any other browser, by analyzing this data, we might be able to detect that users using the current browser are actually experiencing some sort of weird behavior, either because they cannot move forward with the proof, or because we can also collect the information coming from the JavaScript log and then detect what is happening. We can also improve the visual aspect of the tool. For example, sometimes the arrows at the main panel can be too small, and if a certain user has some accessibility issues, they might not find it easy to use the menus that they see. So by analyzing the data from this large data set we are generating, we might be able to understand what these issues are and then improve the visual interface for the end user. Given that we're collecting a lot of events, we can technically reproduce every step that the user took as soon as they opened JSCoq. That means, in theory, we can try to understand the sequence of these events and then possibly improve the liveness of the whole environment. It is almost time to wrap up this talk, and I would like to give you a summary of what we just saw. So first, all the code for this modified version of JSCock is available on GitHub. I will leave a link on the video so that you can follow it and maybe contribute to this project. Keep in mind, this is a work in progress. So at this time, there are many limitations. For example, if you're planning to use this generated data set with a group of students, currently there is no way to anonymize the information from the users. Also keep in mind that depending on how much data you generate, MongoDB is not going to be able to handle it all. And that's mainly because the way it is configured right now, it does not support excessively large data sets. Also keep in mind that the data that is being collected can change in the implementation on GitHub. And that's mainly because in data science projects, it is common to start analyzing the data and noticing something is missing. So again, this code is still not fully in a fully final version. The other technical limitation is that currently there is no automated way to keep the JSCock image up to date, and that means I need to manually tweak it every time there is a new release. But apart from these technical issues, which are still being developed and adjusted, I hope you enjoy this idea and maybe embrace it and help us to create a large data set of proofs, which might be useful not only for our community, but also for different communities, for example, the machine learning community. Thanks for coming to this talk. If you want to talk about this idea of creating a data set of proofs, let me know and I will be around during the entire conference. Thanks again for joining, and those are some of the references that you can take a look at if you're interested. See you.
Thanks. Let's thank Haneli again. Is Haneli here to answer questions?
Yep. Give me 1 second.
Yep.
Sorry.
No worries. Hello, Haneli.
Hi.
Hey. So, arguably, the whole the theorem proving community is not that large, right? You could probably put everyone, if you logistically able to, not in COVID times, put everyone in the same room, right? You can even do like a qualitative study that encompasses everyone, right? If you really wanted to, right? So what's nice about this is you're collecting a lot of data on one person, for example, right? Where you continuously yeah. So you think maybe there's room for customizing the experience of a single person or a single group of people rather than trying to make it scale to lots of users and collecting lots of data on lots of users. See what I mean? Yeah.
Yes. So maybe I can throw in a comment or two about that.
Yep.
So it's not fully clear to me what we can do with a data set like this, because it's interesting because it collects partial steps of proofs, not the whole proof. So if you do a scraper for GitHub, which is what a project called CockGym does, you only have some proofs which are from open source code and they're complete and they claim to be right proofs. So if you get what is in your head when you're trying to come up with a proof, well, you're going to get a lot of flaws. And that's what I'm trying to take a snapshot of, because I'm collecting everything that you do. But as a side effect of this, you also get issues with the tool, right? Well, if there's something wrong with JSCock, you can also have this full snapshot. So I think I mentioned that in the talk. There are multiple dimensions we can explore, one being the educational dimension, the other one being the tooling system, and the other one maybe be some sort of guidance. Even if you have a lot of experience with proof, it would be very nice if you could get some level of maybe auto-completion or suggestion, in the same way that, I don't know if you did any web programming, maybe, but you get a lot of extra help from the IDE, which you don't have in the current ITP tools that we do have. Maybe I think my best experience is Lean with VS Code. But apart from that, for Coq, well, I'm not saying it's bad, but maybe it could be better.
Thanks. I don't see other questions. And yeah, we're a little bit over time. My fault, not you are fine in time. So let's move the discussion to the social lounge. So let's thank Valerie again. And since this is the last talk of the last session in ML before the of ML, let's maybe thank the chair for all his hard work. I don't know if you've seen it, he was behind the scenes the whole day. Since very early in the morning, I think, for where you are. 2 a.m., something like that.
2 a.m. So that's why I was a little slow switching like questions and presenters at the very end. It got like I got a little tired, but yes, it's okay.
Yeah, so mash the like button for this one. Yeah, we should say that. Share, like, and subscribe. And really, thanks everyone for contributing. ML doesn't go away from the conference. There's a whole workshop to work for Camel, but this is kind of the ML family workshop. So thank you all for participating, and thanks for the PC as well. So thanks for all the PC who have helped make this happen, and all the volunteers.
Yeah. Big thanks to the session chairs, without whom I could not have managed this workshop. It's very hard to find the videos, juggle people in and out of the stage, and keep an eye on any last-minute surprises. So very warm thanks to everyone who responded positively when I needed session chairs. Thanks to the keynote speaker. It was great to have done, and I'm very thrilled to have chaired this workshop. My first paper ever was at ML 12 in Copenhagen, so I have very fond memories of the ML workshop. So it's been a pleasure working with everyone. Thanks for attending, and I'm looking forward to seeing everyone as a regular participant next year. Bye-bye.